I'm going to hit record and everybody ready? All right, here we go. Good morning, everyone. And I hope everyone's gone to the bathroom because we're not going to take a break for at least an hour. And I hope everyone's got your coffee because we're not going to take a break for probably at least an hour. And good to see everybody and happy Thanksgiving. And hopefully you've recovered from all that turkey you ate and all that other good stuff. And lots of leftovers today. I guess for once we won't have to wonder what people are going to be eating at our lunchtime. It'll probably be something to do with leftover turkey. I know it will in my case. Um, so thanks for being here. And my name is Scott. My call sign is N7JI. That probably doesn't make a whole lot of sense to most of you. Maybe it does, but by the end of this 11 or 12 hours that we're doing, I think it will probably make a lot more sense. And that's kind of the goal. So, um, a little bit about me. I have been a ham radio operator since I was 15 years old, and it was at the end of November in 1984 that I passed my exam. I almost can't remember that. That was a novice license, and from there I went through. After about a year and a half, I really put together a station, started operating, got my code speed up, and in a period of 4 months, passed my technician general, advanced and extra exams, and the 20 words a minute exam, and then became a volunteer examiner. Got very involved in my college ham club, and here I am today. 41 years after getting my first license. And so this is roughly the 50th or so class that I've taught on licensing. Um, Most of them have been technician class because I consider that to be like the most challenging class to teach, but also the most important because that's where everybody has to come in. Y'all got to start somewhere. So if I can give you a good head start, then hopefully you can do well in that. You can also move forward, go to the next level, go to get a general license, get an extra class license, and so far and so on and so forth. So for me, my main focus has been over the last 41 years. I am a hardcore contester and DXer. Uh, I do a lot of Morse code, and I enjoy seeing what I can do with as little as possible. That's part of the fun for me. That's known as QRP, which is a Q signal, which means low power operating or reduced power. And I like to again see how much I can do with how little. Um, let's see. Oh, and there's someone named JD, and I wonder if JD is the same JD. JD, is that the same JD? And I don't hear anything from JD. Okay. Well, let's see. Just a couple of ground rules, so we make sure that this runs smoothly and happily. Notice that if you look around, you'll notice that there are a lot of people here. And as far as I see it, I don't mind teaching a big class. I kind of enjoy teaching a big class. It makes the optimal use of my time, which is great. Can everybody hear me okay? Okay,
Okay.
Georgia.
Yes, sir.
Okay, so if you've got a problem with the audio, crank it up. Um, so I'm trying I try to make the best use of my time. I have a full-time job that gets me traveling all over the country, all over North America, all over South America, all around the world. I always take equipment with me. I do licensing, reciprocal licensing. Some countries have automatic reciprocal licensing. Um, and so I get to operate pretty much everywhere I go. That's part of the fun for me. In addition, um, I also am I advise numerous clubs, college club, University of Oregon club, uh, South Eugene High School, and any other club who that feels like they could use some advice or anything like that. I'm happy to do that. Um, I'm a big proponent of ham radio for education, considering that it was a big part of my education growing up. I'm also the section manager for the American Radio Relay League Oregon section, which is the entire state of Oregon. So essentially, American Radio Relay League is the national organization for amateur radio in the United States. It's the organization that, in addition to lots of other training things and stuff like that, works on Capitol Hill as our lobbying organization because we do exist in a sphere of a lot of telecommunications needs from a lot of different organizations and companies. They have lobbyists, they have money. We need lobbyists, which basically means that somebody has to support them. So the ARRL is our voice on Capitol Hill. Um, we fight in the same spectrum. We fight for the same spectrum that everybody else uses. So what makes us more important? Well, in their eyes, not a lot. So it's up to us to prove why, it's important to have this thing called ham radio. So thank you everybody for being here. Um, as far as mechanics, uh, I don't like having to look at the chat to see whether or not there's somebody asking a question. So if you have a question that you're asking of me, just go ahead and like speak up and ask directly. Unmute yourself and just ask and break in and feel free to talk amongst yourselves in the chat as well. But if you've got something that you want just like answered immediately, go ahead and just ask it out loud. I ask that if you have a barking dog or a roommate or something that likes to watch TV really loudly and you don't have a headset, or even sometimes if you do have a headset, make sure you mute yourself. There's that little button that says audio down on the lower left, and if you click it again, then you are unmuted. So it's okay to unmute and mute yourself at will. If I hear a dog barking or something, then I have to go look and see which little box is lit up, and that takes my distraction away, or that takes my attention away from what I'm doing. So, but again, I will probably ask you guys numerous questions, and feel free to answer them. Um, you know, prepare to unmute yourself, but if you habitually breathe into your microphone really loud and you leave yourself unmuted, it's going to be distracting and loud. So we're going to try to avoid that. All right. Anybody with any questions before we start?
Um, the for the exam, they said in the email that they would call us
Yep.
before the exam started, but
Yep.
since it starts right after this class is over,
Yep.
how would that call work? Do we just leave the Zoom meeting or
No. Well, what'll
okay.
happen is that I will disappear from this meeting, and then I will probably be the ones operating the phones.
Okay. Thank you.
So the thing is that we've got we've got 35 seats in that class in that exam session, and it takes three people, three accredited examiners to give an exam, and we've got 35 people. So it's going to take a while. There's probably going to be 20 people on hand, which means we can run 6 exams at a time. So when the time comes, um, prepare to answer the phone. If you need to go earlier or need to go later, that's a good idea to tell everybody, because then we can sort of prioritize our phone calls and get people in. You're really ready. You want to take this exam right now at the end of class. We can put you right at the top. If you want, yeah, I think I'm going to do a couple hours worth of practice exams. You just tell us you want to do that. Okay. Other questions before we go?
Do we need multiple cameras or one camera is fine?
You need two cameras to take an exam. One is typically the computer that you're working on, the webcam that's on
Hmm.
it. The other one is a phone or something,
Okay.
a phone or an iPad or something. Basically, we need to see your face, and from the other camera, we need to see your hands and the key and the screen.
Okay. Perfect. Thank you.
And there will be a whole process of, going around and scouting out the room, which is why a bathroom's a really good place to take an exam because you can lock the
My
door.
my reception in my bathroom is not very good.
Well, can you control the number of people coming in and out of where you are?
Yeah, I can
Then,
close the door here and
then you're
that's not a
fine.
problem.
Then you're fine.
It said though that we needed to register for the exam.
Yep.
I tried doing that and it told me that there was an error and it would not let me go forward.
Did Kent get a hold of you? I thought that it was fixed. No? Did
I also had the same problem with that.
Oh, oh good, it wasn't just me.
Okay, so what I'm gonna do
I had that problem, but was able to get it fixed. I think you're thinking that's
Yeah,
you.
that was Janice. Okay.
Yeah, yeah, I got it fixed.
Okay.
Or
Well,
he fixed.
do you know what the fix was? Or
I
was it
do
something?
not.
No. Okay. So
That I know.
I'm gonna text Kent right now.
Well, everywhere today. I don't know if people can hear me. The internet's been having trouble everywhere today. I don't think it's your problem. Everything I was doing today was affected by the solar flares.
Was was that for okay, Noah, what was that? That was your audio was really low and you were speaking fast.
Oh, I'm fixing it. I hope so. The whole internet's having trouble today. Everything I tried today was screwed up. We're having solar flares. So try again in a few hours. It might be cleared up on its own.
Well, when you say solar flares, there is no let me look and see because that would be interesting to me.
It's been
Uh,
happening. It's been happening massively many times a day.
yeah, but that's not really typically it should not be affecting this terribly much. Let me see.
Sites are
Uh,
down. So if it's a website issue, that's happening everywhere. That's all I was gonna say.
okay.
If the website,
I was having a real issue with trying to register, but it was because the FCC was shut down when the government shut down.
Yeah.
I had to wait until it opened back up before I was able to register, and I got registered last week.
Can you have you got it? Have you got it now?
Yes, yes,
Okay.
no, I'm all set.
Okay. Good. All right. Let me see. One more question.
Yeah, how do you obtain an FCC number?
You go to the FCC Core's website and you obtain an FRN through that.
Okay, thank you.
Scott, this is
Hmm.
Lillian. I have a question about your advice to take the general exam after the technician exam.
Yep.
How do I do that? I just have practiced for like a day and a half on that one, and I'm getting scores in the 40%.
You're probably not ready.
So don't take it.
Well, I mean, you can try it. No, if there's a reasonable chance you're going to pass it, but if there's not, then you say, I'm just going to wait.
Thank you.
All right. So I just asked Kent to drop in, and hopefully he does. And all right. Any other questions? And by the way, with regard to solar flares, the Space Weather Prediction Center indicates that there are no significant flares going on right now. There's always flares going on, but they mostly affect HF, and that's one of the other things. I am acutely aware of all of these solar flares and CMEs because those have a strong impact on high frequency propagation, which is my main focus in ham radio. So, all right. Any other questions before we go?
Thanks for holding this class.
Okay. Yeah. Thank you for being here. All right. Let's do this thing. Okay. So everybody's seen the book, I assume. If everybody has a copy of the book, it looks kind of like this. Everybody's got this, I hope. It's a free download. It was mentioned ad nauseum in the information packets that I sent you. And notice that the first thing it does is electrical principles, right? That's on page 4. Well, I typically don't like to follow with electrical principles first. The way I do it typically is that I start with the stuff that's on roughly page, let's see, 30-ish. There we go. Yeah, right around 35. And the reason I do that is because I believe that it is important to understand what a wave is and how all this stuff is tied together. So with that, I'm going to, if Zoom allows me to, I'm going to share this whiteboard, which I hope everybody can see. You'll have some buttons across the top of your screen that say meeting and potentially iPad, Scott's iPad. This is Scott's iPad. So here we go. This is the first thing we're going to see. All right. So that is a circle. That is a circle with a rectangular grid system built into it. Notice we have our one axis and we have our two axes. This is a rectangular coordinate system. We call this our x-axis and we call this our y-axis. We're starting with the math right off the bat. Okay, so if we want to think of it this way, now this is the plus axis and this is the minus x-axis, and this is the plus y-axis and this is the minus y-axis. And so because this is a coordinate system, we can define any position on this coordinate axis by an address. We can say 3, 4. That's x-axis first. We go 1, 2, 3 units this way, and 1, 2, 3, 4 units this way, and then connect the dots. And we start at the origin, which is at 0, 0, and we end up at 3, 4. Now, importantly from this, we can also say that there is something called the Pythagorean theorem. Everybody remember the Pythagorean theorem? Okay, so that is where in a right triangle, which has a 90-degree angle in it, x squared plus y squared is equal to z squared. So we're just going to basically start with a little with our trigonometry that helps us explain all of this. So in this case, we have that 3 squared plus 4 squared equals something squared. And we have 9 and 16 is equal to 25. What's the square root of 25? Is equal to 5, because 5 times 5 is 25. Okay, so the length of that line is 5 units on this coordinate system. We also have an angle. We start at how many degrees are in a circle, everybody?
360.
360. Okay. By definition, our 0 angle is on the horizontal positive x-axis. And we wrap our angle around in a counterclockwise direction. No, I don't know why it's counterclockwise, but it is counterclockwise. So our angle goes in the counterclockwise direction. And what is the first interesting angle that we get to if we're doing that? How many degrees?
90.
90. Yeah, okay. 90 puts you all the way at the top. So this is 90 degrees. What's the second really interesting angle?
180.
180. 180 degrees. And the next one?
270.
270. And what's the next one?
360 or 0.
360, which is the exact same as 0 because it's exactly where you started. So you basically go all the way around the circle and you end up right where you started after 360 degrees. So we can also say that this line right here compared to the flat line on the x-axis makes an angle. And we use something called the tangent to define that. Now, we also have a sine and a cosine. So those are our trigonometric functions that allow us to say what proportion of the angle that we made are in the vertical direction or in the horizontal direction. So the sine is the proportion in the vertical direction, so we'll call that y. And the cosine is in the horizontal direction, and we'll call that x. So, and it's a proportion, so if we had a distance of 3 and 4 here, well, we could say that our cosine, or we'll do our sine first, is equal to the vertical portion, which is 4 divided by the length of the long side of the triangle, 0.8. And we can say the cosine is equal to the horizontal portion divided by the length, which is 0.6. So this is actually pretty profound stuff. We actually have values that translate to how far up and how far over we're going. Which kind of makes sense in a 3, 4, 5 right triangle. Okay, so now that we've drawn all that, I hate to do it. I'm going to erase it and we're going to start it again. Okay, because practice makes perfect. So here's our 0 degrees. What's our next interesting angle?
90.
90. What's our next interesting one?
180.
180. And the next one?
270.
270. And then we're all the way back to 360. Okay. So if I say that this very special circle that we drew has a radius of 1 unit, how far is every point from the center point?
1 unit.
That is exactly 1 unit. So this is known as the unit circle. And what if we think of this as a merry-go-round? And we have a very unfortunate person who happens to be sitting on the merry-go-round right here as the thing starts spinning. Well, right? Okay, well, that's not necessarily good or bad, right? The person's going to be spinning around because they're at the unit circle. So when they get up to the top, how far away from the center are they going to be?
90 degrees.
And what distance?
1 unit.
1 unit. Okay. How about when they get all the way over here to the left-hand side?
1 unit.
1 unit. And how about when they get back down here?
1 unit.
1 unit. And when they get back to the starting point?
Unit.
Still 1 unit. So the only thing that's changing is the fact that they're going around the circle. Well, if this is a person sitting on the equator of the Earth, you don't really notice that terribly much, right? Well, that's because it's relatively slow in comparison to, gravity and things like that. But let's say this is a merry-go-round and somebody gives you a slow push, right? Is it possible that you're not going to get nauseous? Sure. How about if somebody comes along and gives you a big push?
Vomiting is pretty considerable.
Yeah, it's not going to be pretty, right? Okay, but let's say you're tied down, you can't move, you're stuck here on this point, and you're spinning around with it as it's turning around. What is the only difference that you experience between the two situations?
Going faster.
Going faster and going slower, right? You can say, okay, well, let's say that if I'm going slowly, it takes 100 seconds to go all the way around. And we call this thing all the way around one time. We call that a revolution. Okay, so how long does it take to do one revolution at that slow speed?
100 seconds.
100 seconds. Could you also say that I go around 1/100th of a revolution in a second?
Yes.
Yes, it's the same thing. Okay, now let's say that this other one, they spun me around at a rate of 1 second. I will do one revolution in a second. Well, okay, so we have also now a thing that is a rate of the number of things that happen in 1 second. That is known as a frequency. The number of things that happen in 1 second is a frequency of something happening. I go to the zoo once a year. I jump up and down every 3 seconds. I jump up and down twice a second. That is known as a frequency. The amount of time that we do something in, we use this letter. T for time. The number of things that happen, for instance, one revolution, that's our units. And our little letter F is our frequency. So, if we now have something that is things per unit time, and let's say a revolution per second, that is known as a frequency. So now, what we have is we have a frequency is equal to things per unit time. And for time, we usually use seconds. So our frequency is actually 1 divided by seconds. We have another name for our time to do one thing, and this is called a period, also known as the big letter T. Not to be confused with the little letter t. So that's our period. So now we can take a look at the big letter T and the little letter t, and we can say that if we have a frequency of one revolution per second, what is the period of this? How long does it take to make one revolution?
1 second.
Okay. If we have a frequency of 100 revolutions per second, what's our period? How long does it take to make one revolution?
100 seconds.
1/100th of a second. So we now have that frequency and period are inverse to each other. So now if something has a frequency of 1,000,000 times per second, what would our period be?
1/1,000,000th of a second, or 1 millisecond.
No, 1 microsecond.
Microsecond.
So
now mil is 1,000.
Yep, we will be covering that too. Okay, so now we have managed to relate time and frequency. Now here's the next thing we're going to do. We're going to get rid of that. And we're going to draw our unit circle again. And now we're going to look at, here's our 0 degrees and our radius of 1. And what are our first what's our first interesting point?
90.
Yep. Okay. And our second one?
180,
Yeah. And our third one?
270.
270. Okay. 90. And we have 180. And we have 270. Circle looks pretty bad. Kind of looks like a kidney bean. Or a cardioid. So, okay. So now, how far away are we from the middle of the circle at any point in time?
1.
We're 1 unit away. Okay, perfect. So now what we're going to do is we're going to make a graph because this is math and I can do anything I want in math so long as I follow the rules. Okay, so what I'm going to do is I'm going to mark those interesting points. So here's 0 degrees. These are going to be on the x-axis of this graph. This graph is displacement, which is how far away something is from something else, versus angle. Okay, so at 0 degrees, we're going to draw this thing called the x-axis and the y-axis. This is the plus and minus, plus and minus. We're going to look at the x displacement. How far left and right are we from that 0 point? At 0 degrees, how far are we away from the 0 point, from that origin?
Right.
We're 1 unit, and which direction? To the left or the right?
All right.
To the right, and we define that as our plus. So we're going to start at a value of 1. Okay, how about when we get to the 90-degree mark? How far left and right are we?
0.
We are at 0. We have not moved. We're not left or right. We're right on that vertical axis. How about at 180 degrees?
-1.
Yep, because we've now moved to the left. We're negative. Okay. And how about at 270?
We're at the 0 again.
We're at the 0 again. Okay. And how about at 360?
So, 1.
We're at +1 again. Now, what we're going to do is connect the dots. And we could do it with straight lines, but we have this idea that it's not going to be straight lines. And it looks like this. Now, what happens if we keep going to the right?
It's just continual.
It just repeats. How about if we keep going to the left? We can wind the circle backwards, and what happens to the angle? What happens to it? It just keeps going. Okay, so now we're going to look at, I'm going to make sure this color is right. We're going to look at,
Now, am I jumping ahead, or ultimately this is what we're doing is a wavelength?
yes. Okay, so
Okay.
now we're going to look at y displacement. Okay, so we're going to start at that same 0 point and say now, since we're looking at the y-axis, we're moving up and down. How far up and down compared to the origin are we when we're at 0 degrees?
At 1.
No, we're right on that same line. So our reference point is that we're at 0. We are
Right.
we are at sea level, basically.
Right.
Okay, how about at 90 degrees?
You're at 1.
We're at 1. Okay, how about at 180 degrees?
0.
We're back at 0. How about at 270?
-1.
-1. And at 360?
1.
We're at
0.
0 again. All right, and now we're going to take a different color and we're going to connect the dots. And we can extend this forever, either direction. Okay, so the x-axis, the x function, That's known as a cosine. That's what the x means. And the y is known as the sine. Well, if you're on the ocean, what do you call these things that we've just drawn?
Waves.
They're waves. So these are known as a cosine wave. And this is known as the veritable sine wave. A sine wave and a cosine wave are just basically pictures of what happens when you look at a particular displacement as a circle spins around and around and around. It makes that nice pretty picture because that's what they're continuous, they're not choppy or anything like that. That is what it actually looks like. So if you look at these two sine waves, or sorry, look at these two waves, what do you notice is the only difference between them?
They're offset.
They're offset from each other. All right, so you'll notice that the sine wave is shifted that way. And how many degrees is it shifted?
90 degrees.
Yeah, because the 0 point, for instance, is here, and the 0 point is here. This distance is 90 degrees, so this has a 90 degrees phase shift, as it's called. Okay, so we now have different waves, and we've shown that there are a couple of intrinsic features, intrinsic properties to a wave. So you take a look at this wave, for instance. What are some things we can do to this wave?
You can stretch it and shrink it.
You can stretch it. Yeah, okay. You could shrink it. How would you do that?
Increasing or decreasing. Increasing or decreasing the frequency.
Yeah, basically, well, that actually doesn't work yet because we haven't, we're still looking at angles. That's not really going to change. Yeah, you can change the amplitude. You could move it so that you're sitting way out here at 2 units away from the middle, in which case it gets twice as big. Now, here's the other thing about this. We could also do what? We could start on a different point. Let's say that this is our 0 reference point, and we start sitting on the merry-go-round way over there. We are going to be at a different point from the person who's starting at the 0 point, the 0 degree point. That will cause our angle to be, or our sine wave to be shifted in phase from that, which is exactly, as you notice, what happens when we're doing the sine wave, which starts at the 90 degree point, versus the cosine wave, which is the 0 degree point. What do you know? They're shifted by 90 degrees from each other. Okay, so now one thing we can do, because we have not really looked at what happens when we change our speed. Now, if you think about it, what'll probably happen is that it will squish and stretch that wave. Agreed?
Right.
Okay, so in order to do that, though, we have to have some other variable thrown in there. And that other variable has got to be time, because we want it to be squished and stretched. So we're now going to say that here's our merry-go-round again. And how many degrees are in the merry-go-round?
360.
360 degrees. Okay. And okay, so that's our 360 degree rotation. And we're going to assume that we're at a distance of 1 unit away. And now we're going to say that we cover 360 degrees is equal to 1 revolution in a unit of time. Okay, so what we're going to do now is say this now becomes a frequency And what can we do with this? If we speed it up, what happens to our time?
It decreases.
It gets smaller, that's right. If we slow it down, it takes more time, right, to finish that revolution. So let us say that we now have 1 revolution per second. And we draw this wave. We're starting up here. We're doing a sine wave. Okay, so 1 revolution per second. How long will it take to do that?
1 second.
1 second. Okay, let's say we increase our speed to 2 revolutions per second.
Half a second.
It'll take half a second, exactly. What happens if we increase it to 10 revolutions per second?
1/10 of a second.
1/10 of a second, right. Okay, so at 10 revolutions per second, we now take 1/10 of a second to finish that whole thing. Now, if we were to stretch this out and stretch our graph a little bit, we would see something that looks a little different. We're going to make it so we have 1 second. This is now a time of 1 second. 0 to 1 second. Okay, so at 1 revolution per second, how many waves are going to fit in there?
1 wave.
1 wave. At 2?
2 waves.
Yep. At 10?
10 waves.
10 waves. Let's see if I can draw it. So that is basically what happens to our wave. Okay, so now we now have a different number of waves happening per second. Okay, that's interesting. By speeding it up and slowing it down, we've changed our frequency, which changes the wavelength. But now we got to add something else. We got to add something else to this, because this is great, but it doesn't really relate to things that are physical. So we have to find some way to relate this to something physical. So what we're going to do is take that circle, which looks like this, and we're going to rotate it so that we're looking at it edge on. Here's our circle. When we're at 0, we're here. When we're at 1, we're here. And when we're at -1, we're there. And now we go up, and then we go down. And if we're watching the dot, what does it look like it's going to do?
Bouncing up and down.
It's just going to bounce up and down. Okay. Now, what's going to change the rate at which it bounces up and down?
The frequency.
Frequency, right. That just changes how the dot bounces up and down. It goes up, it goes down. Here's the dot at any given point in time. It's somewhere along that line. So now what we're going to do is take this and we're going to add another thing. We're going to do this with it and move it to the side. At a certain velocity in meters per second. So now what's going to happen when we move it to the right? What path is it going to make?
Well, you're going to get your sine wave, won't you?
You're going to get another sine wave, right? And in fact, it'll look like this. I'm going to unshare this, hopefully. Come on. Fussy. Okay, so can everybody see the light?
Yep.
Moving up and down. Right? With a frequency. What happens if I go slower? It just takes more time. If I go faster, my hand gets tired, but it still just goes up and down, right? But now I'm going to take it and I'm going to move it to the side. or I'm going to go faster and still move it to the side. Or I'm going to go really slow and move it to the side.
I don't seem to see anything.
I
didn't see anything move on the screen.
You had to look at his window.
You see a bright light in my window?
No, I don't.
Okay, if up top there should be like a speaker view or something.
I'm in speaker view. I am in speaker view.
Okay, you don't see a bright light right in the middle of my screen?
But that's okay. Keep going. I'll figure it out.
Okay.
Find Scott's name in the participation list and click. So reach him. Find Scott's name in the participant list, and if you click his name, it will focus on him.
Should be. All right. So what we've now done is we've related something to the speed of something. We now have a frequency, which is how fast something is going around this circle. And we also have this circle now turned on its side, the dot moving up and down, moving at a velocity in meters per second. Okay, so how do we measure the frequency of the circle going around?
Per second?
Revs per second. And now we also have this other thing, which is
meters per second.
Meters per second. Okay, so what is the common thing that you see in both of those?
Time.
Second.
You see time. That's right. Okay. So we now have, because it's math, and what's the rule in math? I can do whatever I want so long as I follow the rules. I'm going to create a new thing because I can do that, because it's math, and I can follow, so long as I follow the rules, I can do what I want. So we're now going to divide arbitrarily this, call this our frequency, and our velocity. Okay, and we're going to say that we want meters per second divided by revolutions per second. And when this circle goes around one full time, what does it make? One complete wave. Everybody agree with that? We proved that that does work, right?
Right.
Okay?
Yes.
There's no argument that it made that. So we can actually say that this is a wave. And one revolution makes one wave. So we can actually take this revolutions per second and we can change this to a wave per second. Okay. I just arbitrarily created this weird unit because I can do that because it's math and it lets me. What happens if I divide meters per second divided by waves per second?
It's meters per wave, and you're getting us to hertz, right?
Well, not yet. There's meters per wave. Okay? So now, if I know what something's velocity is, what do I now see? I can see that at a given speed, I have a physical length of this wave. What would be a good thing to call that unit?
Wavelength.
That would be a wave length because it's the length of a wave.
Okay, Scott, I'm a little bit lost between the revolutions per second and the meters per second.
They have nothing. They have nothing. That's right. They have nothing to do with each other.
Isn't revolution per second a kind of velocity, or am I not understanding velocity?
It's an angular velocity of the thing, of the circle. It's how fast the circle is spinning around. It has nothing to do with how fast I move the circle sideways. They are completely unrelated.
They're completely unrelated. So one is how fast something is going around in a circle, and the other one is how fast it's going through space?
Yep. Here we go. This unit called wavelength, we assign a Greek letter to it, which is the little Greek letter lambda. And because it's based on one wave, what is the unit of a wavelength?
Distance, meters.
We use meters. That is our wavelength. That is how long a wave is as it's traveling in space, or whatever you travel through. Okay, so now that we have established this unit called wavelength, we can write a formula for this. Well, we know that wavelength is in meters per wave is equal to velocity in meters per second divided by frequency in waves per second. Okay, so everyone agree we now have this formula? This is always true for any wave and for any frequency and and this gives you a wavelength. So let us go through and actually figure out what something is. Do we have any musicians?
Yeah.
Does anyone play guitar?
Used
Okay.
to.
Okay. What's a concert tuning A? How many hertz?
440.
440. Excellent. Okay. And what is that measured in?
Hertz.
Hertz. Okay. Hertz is the unit that we have for frequency, named after Heinrich Hertz as an honor, in order to honor him for all the work he did. Our frequency is measured in hertz, and it's things per second. Okay, so we now have our frequency for our A for tuning our instruments. All right, so now we have a wavelength and a velocity that we have to figure out. So, how fast does sound travel at the Earth's surface?
Speed of light.
No. How fast does sound travel? Speed of sound.
Speed of light.
Speed of sound. Right? Sound travels at the speed of sound. That is approximately equal to 330 meters per second. Okay. So, what is our wavelength of our concert A? Going to use our formula. Lambda is equal to V divided by F is equal to 330 meters per second divided by 440 waves per second. And what's 330 divided by 440?
0.75.
Yep. So if you were to map it out as sound was traveling through the atmosphere, as you're sitting and tuning your guitar, or your flute in my case, or your clarinet or whatever, here's a wave. How much space would it actually carve out?
3/4 of a meter.
Yep. Which is about 3 feet long. And about 2.5 feet long. So, anyone play a wind instrument? Anyone?
Yeah.
I played the flute for all those years. Anyone?
Play clarinet.
Clarinet. Okay. How do you tune your instrument?
To C.
How do you tune it?
I tune it to.
No. What happens? What happens if it's sharp? What do you do? If it's sharp, you lengthen it because sharp means the frequency is too high. How do you tune it if it's flat?
Shorten it.
You shorten it. Okay. That is because what you now have is a resonant cavity that looks like this. That resonant cavity develops a wave, a standing wave that is propagated in the resonant cavity. If the resonant cavity is too long, the frequency is too low. If the resonant cavity is too short, the frequency is too high. So now we have a relationship between physical wavelengths and the wave that is propagated from it. Okay, so now we're going to move to something else. We're going to now say, here's our circle going around again. And here's our circle now turned on its side. And now we're going to move it at a speed. Okay? So now, instead of a sound wave, which travels at the speed of sound, we're now going to create a light wave. How fast do light waves travel?
Speed of light.
Speed of light, which is roughly 3 times 10 to the 8th meters per second. Okay, we use the little letter c for that, like E equals mc squared. It's the very same c, it's the speed of light. Okay, we can use the same formula that wavelength is equal to v divided by f, except that in this case we have the letter c for the speed of light. So our wavelength is now c divided by f. Okay, so now we have let's say we have a frequency of 440, let's say 400 hertz. All right, we're going to be a little bit lower, but I want to use something that has a lot of zeros. So, okay, so now what we're going to do is we're going to figure out what the wavelength is. Wavelength is equal to the speed of light, 300,000,000 divided by 400. Okay, the easy way to do this, we start canceling zeros. 0, 0. Okay, so we now have 3 million divided by 4. We got rid of those zeros. Is 750,000 meters long. So we now have a wavelength of 750,000 meters for a frequency of 400 hertz. And what makes it so different? What speed is it traveling?
The speed of light.
Speed of light. And because, why have I done that? Because this right here, we're going to call a light wave. Going to arbitrarily say that that is light. And light can have any frequency that I want it to have. So, right? So we're saying that our light wave is has a frequency of 400 hertz. At that frequency, it travels at 750,000. One wavelength is 750,000 meters long. Okay, that's a really long wave, right? So what we're going to do is instead say, okay, that we're going to take a frequency of 400,000. Yeah, everybody try to keep the chat down. It's getting really, really crowded. So we're going to have a frequency of 400,000 hertz. And also, you can send private chats to each other as well, if you insist on doing that. Okay, so there's our frequency, and here's our speed of light, 300 million meters per second. So our wavelength is equal to 300 million divided by 400,000. And we're just going to cancel zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we have 3,000 divided by 4 is now 750 meters long, which is still really long, right? All right, so we have all these relationships between frequencies and wavelengths. Well, let's pick a different frequency. Let's go for 4 million hertz. Well, a million of anything is the big letter M, which means mega. We can actually take this and replace this with 4 and then times a million hertz. We can now replace this million with a big letter M, and now this is 4 megahertz. Right? We're using units to do that. Okay, so now what we can say is we can figure out the wavelength for that. It's 300 million divided by 4 million. Cancel zeros. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have 300 divided by 4 is 75 meters. Okay, so what has just happened is we have now seen how fast or what length a wave has at a certain velocity, in particular at the speed of light. Because we have now just experienced changing all these different frequencies of light and showing all these different wavelengths. Anybody disagree with that so far?
Yes, sir.
Okay, well, so we have light we've now shown at 400 hertz and 4,000 hertz, or 400,000 hertz and 4 megahertz. And what do you know about all those wavelengths? They're all very, very different, aren't they? Well, okay, well, just because they're different, does that make them not a form of light? Does that somehow make them not light? If I say that they're light waves, I can do that. It's science class. I can do that. They're all forms of light. I just say I'm going to change the frequency. So by doing that, what I have now done is I have created light with all these different frequencies and all these different wavelengths. Well, as it turns out, light is a very special kind of wave. Anyone know what light is? What kind of wave? Sound waves are sound waves. What are light waves?
Photons?
Well, photons.
They're made of photons, and
The spectrum.
They're electromagnetic.
Light waves form the electromagnetic spectrum. Light waves are electromagnetic waves. They have an electric component and a magnetic component, and they travel through empty space. They don't need a medium. And notice that they have different names when we do this. What we normally think of as light is all the way on the right-hand side, which is in the terahertz, which is very, 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 very short waves and high frequencies. Those are in the order of nanometers. 600 nanometers is a form of 650 nanometers is red. Right? The reason we call it red, why do we call red red?
That's just how we perceive it, right?
That's how we perceive it, yeah. How about green? Green is about 500 nanometers, 550. It's just because our eyes are tuned, by and large, to know that a wavelength of 550 nanometers or so turns up to look like what we call green. Same thing with blue at about 450 nanometers, purple. By agreement, we have decided that those things have those names. All right, well, shorter wavelengths, higher frequencies, we call ultraviolet. Even higher frequencies we call X-rays. Are they still forms of light? They're all
Yeah.
parts. Yeah, they're all electromagnetic radiation. They're all part of the electromagnetic spectrum. As we go lower in frequency, we get to infrared. We go lower in frequency, we get to these things called microwaves. Anyone ever seen a microwave oven? Did you know that was a radio transmitter?
Yeah.
Yeah. Okay. Everything below about 300 gigahertz in frequency we call radio. They're all forms of electromagnetic wavelengths, electromagnetic radiation. They're all forms of light, just in different colors. We can't see them, but those are their wavelengths. Light waves are in the range of nanometers. Radio waves, we typically measure from there's 1,000 meters long, 100, 10, 100 millimeters. And notice that as we go up in areas in denominations of 10, this goes from like 30 to 300 to 3,000 to 3 30 to 3 to 30 to 300 to 3,000 and so forth. These get smaller in wavelengths by the same factors of 10. How come we have that number 3 thrown in there? Why do you think we have
the
that
speed
number
of light?
3? Yeah, and what was the speed of light again?
Three times 10 to the 8th.
Yep, 300 million meters per second. There's that number 3. So, since we have that, we can now say we can make this little convenient circle, 300 million meters per second frequency in hertz and wavelength in meters. The reason I like to draw this circle is because it's very easy to replicate when you actually take your exam. If we have something that says we have a frequency of 30 megahertz, well, we can take that and we can write in 30 right here, and we say here's the one we don't know. Well, notice we have a number here and a number here. This is actually 30 million. And we divide those. There's a divisor bar. And we can say lambda is equal to 300 million divided by 30 million. Does anybody think that it's a great idea to keep all those zeros, or are they just going to get confusing? Personally, I find them terribly confusing to keep around. Well, notice what we already have here. We already have this mega, right? So if we just say, you know what, we're just going to, instead of hertz, we're just going to put in megahertz, then we can get rid of all these 6 zeros up here. And we can rewrite this formula. 300 F and lambda, where our frequency has an implicit number of zeros, so we now call it megahertz. So now what we can do is, let's say we have a frequency of 15 megahertz. Well, we know that it fits in right there. So we're going to write in 15. We don't know our wavelength. So what's 300 divided by 15?
20.
Yep, 20 meters. And we're going to get to why that's important pretty soon. And Kent just showed up. Kent, I assume you're still here?
Yes, I am here.
Okay, so there's Kent. Kent runs the Anchorage ARC VEC. And he will answer right now the questions that you had about signing up for exams. Okay, who had questions?
I was curious, did you say that we have to have 2 cameras on and have them be able to be moved so you can see our whole room around us?
Try to get closer to the microphone. You're really hard to hear.
Did you say we need to have 2 cameras and have them be able to be moved around so you can so we can scooch it around and show our whole room to you?
Okay,
Like
so
we-
real quick explanation. You're going to have two cameras. You're going to have two Zoom connections. Typically, most people use their laptop computer as their primary device, which is staring right at your face. So that's camera one. Okay. And then most people use as their secondary device, most people use their cell phone to load Zoom on their cell phone, join the same Zoom session with their cell phone, use that as their second camera. But you can use a laptop or a tablet or anything else you want to use. And that camera needs to be focused. It is permanent in its final position so that we can see your desktop, the monitor that you're taking your examination on. Okay, and your hands, that sort of thing. But before we start the test, we will ask you to take that second device, stand up, and swing around your room and take a look at the ceiling and the floor beneath you and the desktop. We want to make sure, basically, we don't want to see anything personal, private, or confidential. So please don't let us see that stuff. But so clean it up. And and then once we're just verifying that there's nothing there that can help you with the exam. Okay. And once that's done, you'll put the camera back into its final position. Does that make sense? Somebody
Yes.
asked me a question.
That helped.
and I
Thank
just
you. I
had-
appreciate it.
Oh,
Yes,
okay,
I'm sorry.
very good.
It takes a minute to unmute.
No worries.
I have a question.
Sure.
I signed up to take the exam and I was filling out the agreement, but when I went to go put my name and my signature, I misspelled my name but I didn't notice it until after I pressed send.
What was your last name, ma'am?
Kellogg, Kellogg.
Oh, no problem, Talisha. I've got you in there. You're just fine. Not a problem.
Okay, thanks.
You bet.
Okay, now who was saying that they had trouble getting the system to accept their application?
I had a problem earlier, but I went back and it seems to be going through now. I think this
Okay.
past my area.
I got an error message that said that the website was down and it wouldn't let me go to the place where I could pay for the test.
I would give it a try again. There's always things that happen from time to time, but it seems like everything's running like it should. The payment stuff is all handled through a PayPal interface of sorts. You can pay with PayPal or credit card or whatever works for you. Okay. But please, there may be, all of you should have also, if you've registered, if you've paid, you should have also completed your examination agreement form. I think there's only one, possibly two people that don't have that done yet. So.
Okay. Because I did get my FRN number, so I'm partway there.
Okay. And what was your last name, ma'am?
It's Bells, Belles.
Oh, okay. Yeah, I don't see you registered yet. Okay.
And I'll be able to do that after this class. Is that correct?
Yeah, so there are 35 examination slots. We still have a few slots available. So if you want to be sure to test tomorrow, you probably want to get in there and get registered, okay? Because I am getting registration sort of continuously here. We're at about 30 right now.
Okay.
You get your FRN number from FCC by going on their website?
Yeah, I got that.
Yeah, and just for clarity, so you can go out on your own and get your FRN, and you will ultimately do it on your own, obviously, but you can just figure out your own way to go get your FRN. But also, when you register for the examination slot, the website will help you. It'll give you the links and whatnot that you need to go get your FRN. So just go to the registration page for the examination slot, and it'll guide you from there.
I went to the registration page and it asked me to log in with my FRN number.
Well, it wouldn't ask you to log in with it would ask you for your FRN. It asks you if you're currently licensed or you're a new licensee or whatnot. So if you don't have an FRN, if you take a look there, it'll say it'll help you go get your FRN. Okay?
Okay. All right. Thank you.
Yeah. Anything else?
I thought that I was signed up for this class, and apparently I was not. So I may not be signed up for that. So how do I do that?
What's your last name, sir?
Loveless, Loveless.
Yeah. So, Scott,
I don't
did you share?
because I sent you the link for this class this morning.
Right.
In there is a link to get to where you sign up for the exam.
Okay.
They're
Thank
separate
you.
things.
And I'll drop the link into chat here in a second for signing up for the exam. They'll start the process. And just know, for any of you who have not yet signed up, there are 3 steps you'll accomplish. One, you'll register on the examination platform, and part of that may be you going out to get your FRN, but you'll register on the examination platform. 2, you'll pay for your examination seat. And 3, you'll complete an agreement, the examination agreement form, because we have you do that because it advises you that we're going to use cameras, are going to be looking at your house and all this other stuff, or in your testing area. So we want to make sure you're okay with all of that. So there'll be those 3 steps, and you'll receive an email when you register that has a link to go do the other 2 things. So the registration on the examination platform, you get an email that says go do these 2 other things. Please do those 2 other things as soon as feasible. That way we'll get the examination team ready to go a little bit easier if we know what's coming at us, okay?
So 2 cameras mean no cheating.
Right.
Well,
exactly.
we hate to have to do that, but it's just a prudent practice for us to make sure all is well.
Are we allowed to keep a notebook next to us to use for any formulas or anything?
You'll be
Like,
able to
just a
bring
blank?
you'll be
Blank
able
sheet
to
of paper.
a blank sheet of paper. And if you need a blank sheet of paper, then we're going to ask that you show it to the VE team is going to ask you to display front and back on that sheet of paper. You'll also be able to use a calculator if you need one, but really if you review the questions and think about it a little bit, I think at the end of the day, I could convince you that you do not need a calculator for this examination. But if you need one, that's okay. We'll just have you hold the calculator up and show the team that the memory is cleared. Okay? And please have your desktops clear. Just pretend you're the examination proctor, if you will, and you're administering a remote exam, and you're like, geez, I hope that area is clear of all all the funny stuff. You would want that area clear of all the extraneous stuff, right? And materials. So just think of it that way. Pretend you're the examination proctor.
So once we're in the exam, can we make a cheat sheet?
Sure.
Once the exam starts, you could write anything you want on that sheet of paper. And
I once went into an exam in college, and I was like, okay, I know this formula is going to be on there. I know this formula is going to be on there. I'm never going to remember it. And then right before the exam, I'm like, I know this is going to be on there. And I just practiced it every time. I practiced writing it down. And then I put all my books away, and the exam started, and I grabbed a corner of the exam and I just wrote down the formula. That's perfectly fine.
Yep, it absolutely is, Scott. I got to tell you, that's how I passed my advanced exam back in the days. I figured out that if there were 7 formulas I had to know to pass that exam, and when that exam started, I just started writing formulas down. I didn't look at any questions. Yeah,
this was like a physics exam, and it was some weird formula that had a number that had like a 3/8 and a cube root. I'm like, there's no way I'm going to remember this, but I know they're going to ask.
Yeah.
And they did.
Outstanding. So we've got a lot of people testing tomorrow. Basically, we'll have probably 5, 6, or 7 examination teams. We can test one person at a time with each team. So it'll take us a little bit of time to get through these. How long does it take to take the test? Well, you've been taking practice exams, hopefully. And you have a sense of how long it takes you to take your exam. So that would be the answer to that question. And it takes us a couple minutes to process things afterwards, and then we'll send you on your way. Once the exam is all done, once we're all done, we'll prepare an application file. We'll send to the FCC. We won't send that in till Monday morning. They don't operate on the weekends, and it'll just be better. And then once that's accepted by the FCC, you should receive an email from them directing you to go to their pay site to pay them your $35 or their $35.
Yep.
And then once you pay, everybody listen, once you pay the FCC and they've accepted your payment, typically within about 24 hours, you'll be issued your license. Okay? That's what we
And no, you don't have any choice as to what call sign it is going to be.
Not initially.
If by some chance, can we take a second test if we need to?
Oh, if you're close, yeah, it's the VE team's discretion. So we're gonna let you, if you're close, we're gonna let you try again. I want you, please understand this. We, as the examiners, we really want you guys to pass these exams. We want you to become part of this great fraternity. So we're rooting for you. We're really on your team. Okay. So yes, if we think you can do it, then we'll let you test again. Okay.
I've been doing my practice test. I'm just really nervous. I have really bad test anxiety. But I'm really nervous.
Okay, well, know that when you're in that room testing, I know it's not the normal feeling, but consider yourself to be with friends, okay? Because we're there rooting for you. We just have to make sure it's done right, okay?
So here's the other thing. When it comes time to taking the exam, if you're taking practice exams, if you are scoring consistently above 85%, you're going to pass. And the other thing is, let's say that you are already prepared. You find yourself like at, that point already. If you know you're going to pass the technician exam, for the same price, if you pass that, you can take the general exam also. The material there's about a 50% overlap in material, and I recommend doing that. Kill two birds with one stone.
I have a question.
Yourself.
Sorry.
Go ahead.
If I registered for the test with my legal name, but I don't use my legal name, is that a problem?
The FCC needs your legal name. So.
Right? Okay. Well, okay. Here's how this goes. We, as the VE team, have to ensure that the person taking the examination is who the person is identified on the submission we're sending to the Form 605. Since we don't know you, we need your name to be the same as on the government issued photo identification document that you're going to show that VE team. And no problem. If it's not the same right now, we can change it at exam time. There's no issues with that. Okay.
Thank you.
You bet.
I have a question. So you say 2 cameras, right? Do you have any recommendation on how those should be set up?
We'll figure that out when the time comes. Yeah, okay. I mean, it's your computer and a cardboard box to hold up your phone at a 90-degree angle. The second
Kent, I have a question for you. I've registered for the technician one, and I am scoring pretty high in the practice exams. I just heard this week that we could take the general as well, but I haven't been studying that and testing it. What's your recommendation?
Okay, our experience is that if you're not prepared, if you've not studied for that exam, you will not pass. Now, what you can do, you can go start taking practice exams for element 3, the general. Take practice exams, and if you're scoring, if you're getting close, hey, we'll let you take a shot. But yeah, we don't want you to waste your time and our time. You can take practice exams ad nauseum, so you don't need to take a practice exams with us while we're trying to get a whole bunch of other people tested. Right? So do everybody a favor. Take your practice exams, now, And if you're ready to go, say, hey, we can keep going and let's get you done, you know?
So are all
Okay, JD. JD first.
so are all tests on Zoom, or are there some that are in real life?
We do in-person exam sessions, sure. In this case, we're offering a remote session for you folks. We test remotely every day, twice a day, Monday through Saturday, and we have VE teams, in-person examination teams at numerous locations. We are one of the 14 VECs. And other VEs, so I don't have a testing team in every city in the United States, but other VECs do have teams, typically in most areas where your clubs are at. If you want to test in person, reach out to your local club and find out. There's also a tool on the American Radio, or well, the ARRL, used to be known as the American Radio Relay League.
It still is.
Their website, yeah, kinda, right? So their website, if you want to find an in-person testing session, they have a tool that will help you find that. It's not just Google's your friend. Okay.
Okay.
Okay. Who else was asking?
And
that was my question too. That was my question already.
Let me see here. I'm gonna try to drop something in chat here. Let's see if this works. There we go. There's a photo. So I've dropped two things in chat. One is the link to register for the exam, and the second thing is an image. It's a photo, basically, of how we want that second camera to be able to what it should see. So hopefully that helps everybody.
Your hands on the screen.
No.
All right.
One last thing I'd ask everybody. On the exam on the screen on the computer you're going to take your examination on, do yourself a favor, shut down all of the extraneous applications you have running. We really only want you to be running your browser and stuff that your computer needs to maintain its security and that sort of stuff. Okay, so we don't need all of those other chat applications or Facebook or all that other stuff that doesn't need to be running. Okay.
I have a question with the agreement form. The receipt number for the purchase receipt, is that just whatever I got off Venmo or the credit card?
Yes, sir.
Thank you.
You bet. Anything else? Oh, yeah. So, no, I think I already talked about that. Sorry. Anything else for Kent while I'm robbing Scott's valuable time?
I have a question.
Yeah.
So for this registration, I'm actually relatively new to this, and I know I won't be able to take the exam tomorrow because I know I'm not ready. Will I be able to still do it over the summer?
Sure,
do it anytime you want.
Yeah, we test.
I mean, there's no requirement for anyone to take any class ever. I offer this to give you guys reinforcement and help you out on the theory. I studied for all my exams out of a book.
Scott, may I?
Yeah.
So Scott's putting on this examination preparation course. It's a 2-day intensive, right, Scott?
Yep.
Okay, so the notion with a test for a class like this, the notion is it's an intensive preparation to help you pass an exam. Take the exam immediately after you've done this prep. And if there's some areas you're having troubles with, study up on those, but take practice exams now. And really, if you're not even, or at least tonight, if you're not close, let's reschedule you, give you a little time to digest this, and we can test you in a week or whenever you want, and you'll have in your registration, there's a link there, tells you how to reschedule if you need to. And if we're talking right now, if well, I know I'm registered to test tomorrow, but I'm not going to test. Well, please reschedule now, so we could free up a slot for somebody else who might want to test. Okay.
One other question I would have is, if I've already made my payment, do I have time to finish that form? And will my seat still be reserved?
Yeah, once you're registered on an examination platform, we know it takes a little bit of time to get the other two things done. Just get it done as soon as you can so that we can get our stuff together, okay?
Gotcha. Yeah, I'm just trying to juggle between doing that and paying attention to the class.
No problem. Don't let filling out that form mess you up and learning what you need to learn. Just get it done as soon as you can. Okay?
So I got a question. Is their practice test just to pertain to the technician's license?
Yes.
And that's actually what I sent you guys.
Yeah.
When you go to hamstudy.org, for instance, or you download that app that I forwarded to you guys,
yeah, when you go to hamstudy.org, it's sort of right in your face, right up front. You kind of can't miss it.
Yeah, I just want to get through this, and then we'll revisit for the general after some time. I want to digest this and understand it.
Mm-hmm.
Oh, listen, one other thing, guys, and try to get this out of your head. Or this is Kent's philosophy on this, because and Scott, I think, will back me up on this. If you're a professional if you're a member of a professional organization, oftentimes you have to pass an exam of some sort. And the reality is, you're going to take and pass this exam, and some people say, well, I want to understand everything before I take the exam. Listen, Scott, how many years have you been a ham?
41.
And I've been a ham over 35 years. And you know what happens to me every single day in this hobby? Is I learn something new. So the reality is, you're not ever going to understand all of this stuff and be, you're the one who knows. Yeah, omniscient. You won't. And so your objective here is to pass the exam and, quote, become a member of the club. And the club is someone who holds an amateur radio license. Once you have that, then you really get to dive in and do stuff, and real learning will happen. Okay?
Yep.
So Scott's probably already given you that speech, but I'm sorry.
I haven't,
Scott.
actually. We haven't. We just dove right in. All right. I want to take a 5-minute break. And I will be back in like 2 minutes, and I can answer questions and stuff. So.
Okay. And I'll hang out here for a couple minutes if anybody has any more questions.
Hey, Kent, I sent you an email.
Okay, who is me? Who is
Webster,
I?
Chris Webster.
Oh, hi, Chris. Okay. You sent me an email. I don't see any enough.
It would be under C. Webster.
Let's see here.
805 at iCloud.
Okay, and yeah, that's no problem. Just let us know. Yeah,
Right.
I'll make a note for that. Yeah,
Perfect. Thank you.
you betcha. Thanks for letting me know.
Of
Yeah,
course.
and Mr. Webster's question was Mr. Webster's question was about when he could test, because we are going to have people, we're going to be staging you through here, so we're just going to kind of go down the list. So you are going to have the link to join the Zoom session for the exam. Please don't join that until we call you. Okay? So make sure that the phone number we have that you provided in your examination agreement form is good. Please don't join until we call you. But Mr. Webster's question was, he's got something he's got going on. He needs to test at a certain time, or early or late. Some people need to test early. Some people need to test later because they got stuff going on. If you have a situation like that, please let us know and we'll make it work.
Thank you.
Any other questions?
There's a good one in the chat. Where do we go to register for the general exam?
Okay, well, here, I'll send you another link. Okay.
All right, I've returned.
And if you're ready to test for, I mean, you test with us tomorrow, but if you want to test for general later, just a second, I'll give you a good link for that.
Heck, if you're ready to take a test tonight, you can take a test tonight. I don't care. Good for you.
I'll drop the our normal remote registration link in chat here in just a second. I'm pulling it up.
All right, so while Kent's doing that, does anyone have any questions? I promised that I would answer questions during breaks. Does anyone have any questions about the stuff we've covered so far? Because it's like a big pyramid. We just built the base.
I still don't see where I register.
To what?
For the test.
Did you just click on that link in the chat?
Okay. Above, okay, do you see?
Wait. I sent a link. That's sessions. There's a link in the chat that I sent, which is to register, go to the following link. Here, I'll put it in there again. That should be the one specifically for this class. There it is.
All right. Okay.
You click on that.
Well, the one that I sent is also that link.
Is it? Okay.
Yes, it is. Yes.
And that should just take you right to it. It says there's 30 of 35 spots, and then it says register.
Yes, thank you. I'm registered.
Very good.
Thank you.
And if you aren't going to take an exam, please let us know. You know, if you're not taking the exam and you're scheduled to take the exam tomorrow, let us know so we can take you off the roster and free up the spot for somebody who wants to.
You can reschedule.
Yeah.
We like to. Typically on the rescheduling, we like to have those done within 90 days of the original scheduled date. Okay.
Okay.
So we want to keep the fire going under you.
Oh, so can I throw something else out there, everybody?
Yep.
I have had numerous people come in and take the class and say, "Well, I'm not ready to take the exam." And I mentioned this in the email that I sent out last night that said, "Hey, Kent, that's for you." You see the chat. So the what ends up happening in a lot of cases is someone says, I just came to class and I'm not ready to take the exam and I'll get back to it in a month. And then a month goes by, and then 2, and 3, and 4, and then someone says, "Well, I didn't get to take it. I'd like to sign up for another class." And you just end up in this cycle. Don't let that happen. The easiest way to force yourself to take an exam is to just, even if it's not tomorrow's exam, if you're not ready, schedule one 2 weeks from now and say, "This is my line in the sand, and I'm not going to effectively have wasted those 12 hours that I spent after Thanksgiving with Scott by forgetting everything. I'm actually going to use it and move forward." Don't let that happen to you.
Somebody's asking me if they're registered for the exam. You should have received an email from the system when you registered, but I don't have your name. I just have a screen name you're giving me here.
And also, Maya says I'm ready to take the exam today. There should be many slots open. And I showed you guys that there are, if you go to Ham Study, it doesn't have to be with Kent, right? It doesn't have to be with Anchorage. There are 14 volunteer examiner coordinators. There's, a dozen exam sessions online every day. So you can sign up for any of those, including the Anchorage ones.
Yep. Our primary remote session manager has given the team a few days off for the Thanksgiving holidays. So our next scheduled remote session is actually for your guys' group.
Hey, Scott.
Yep.
Is a iPad good enough to get a FRN? Does it have enough memory?
Say the question again.
Can I use my iPad to register for an FRN?
Oh yeah, you can do it on a phone. I mean,
Okay.
it'll just give you a 10-digit number
Okay.
when it's all done.
All right.
All right. Any other questions before we move on to the next exciting topic?
I'm gonna stay on here for a few minutes. If
Maybe you'll
anybody
learn
has
something.
any questions, yeah,
right?
I might. I always learn stuff when I'm Scott. I always learn stuff when I'm hanging around with you.
Same. And by the way, thanks for the lift to the airport. That turned out to be very, very important.
You're welcome, and it was fun to work your lovely daughter during the contest.
Yeah, that was pretty cool.
One quick question. If you said this already, I'm sorry, I missed it. Is there a different study book for the general exam?
Yes.
Yes.
Did we have that in the chat, or could we get the link, please?
There's if you go to that. Well, are you talking exam like the questions or a book?
Oh, we got a really nice study book because we're taking this class for the technician.
It's not
but if
free.
we want to try to do them both,
it's not free. If you look up KB6NU, no nonsense.
KB6NU.
He's for $10. He's got the general book.
Oh, well, that's almost free. KB6NU.
Yeah. And for any of you folks, for resources for this, Google is your friend. Yep. There are a lot of resources out there.
But don't necessarily believe everything the AI tells you.
That would be I would agree with that.
So when I went to KB6NU, it's just the technician class, and there's nothing else.
No,
There's not even.
There's another one. He's got one for the general and one for the extra too. You go to his main page, and there's a link to each of them.
And did you put that link in?
PDF out there.
I don't have it up.
Because the actual address KB6NU only comes up with that booklet. There's nothing else I could click to get anywhere.
No. Well,
I'm staring at it.
I'm
dropping it in. I've got it right here. It went right to his page.
I did it too.
Wasn't it in the email you sent, Scott?
The email was to all of them, or to the specifically the technician. But if you just go to the main page, it has links to the general and the extra also.
How can I verify to see if I'm registered for the test?
Can't. What's your name?
Wayne Prince.
Well,
it's Michael Wayne.
If you didn't get a receipt, you're not registered.
Well, no,
right?
But he's not even registered on the exam platform. He's not registered.
Oh, well, there you go.
At all. No, not at all.
Thank you.
Do you have an FRN, sir?
Yes, I do.
Okay, good. So it'll be easier for you to register. But yeah, you've got to register for the exam. You haven't done it.
Thank you.
You bet.
Okay, so here we go. I'm gonna shoehorn this in because I got to get things going again. Thank you, Kent. Okay, so now we're gonna basically now take this XY axis that we have, and everybody hold up your right hand and stick out your three first fingers. You got your thumb and your index finger and your middle finger, and make them all so that they're all at right angles to each other. Your thumb is the x-axis, your index finger is the y-axis, and your Z finger is your middle finger. That's going to be the z-axis and shows the direction of motion based on something called the right-hand rule. On this drawing, we're going to have the x-axis and the y-axis. Those are plus and plus. This is the z-axis, and that's going to be in the plus direction. So this is how electromagnetic waves, there are two components to an electromagnetic wave. There's an electric portion and a magnetic portion. The electric portion usually goes like this. It's a sine wave on the x-axis. The y-axis is the magnetic portion, and it is perpendicular to the x-axis. It's perpendicular to the electric portion, and it is in phase, so it goes like this, and like this, and like this, and like this. And the z-axis is the direction of movement of energy caused by the electromagnetic wave. So the z-axis, this is actually known as the S vector or the pointing vector, which takes the energy and moves it in the z-axis. That is how energy propagates through electromagnetic waves through space. If you look back at how this works, you have your x-axis and your y-axis. Essentially, you have your sine wave and your cosine wave. And the x-axis represents the cosine wave, and the y-axis represents the sine wave of something that is basically spinning around in this direction. It generates electric and magnetic fields. Those electric and magnetic fields oscillate in those patterns that are shown. So this is the electric field, which we use, down here. This is the E field, and the other field, the magnetic field, is known as the B field or the H field. Now, the reason they're called the B field is that apparently when Maxwell, these are governed by something called Maxwell's equations. When when he was working on electromagnetics, there was no such thing as the electromagnetic formulas. They didn't exist yet. So he didn't know what the fields were going to be. So just starting off, he had no idea what to call them. So he just called them A, B, C, D, E, and so on. So that is why the magnetic field ended up being what we call the B field. Doesn't make a lot of sense, but that's how it ended up being the B field, and he never went back and changed it. So, okay. So now, as we have electromagnetic waves that are traveling through space, we can do certain things with this. We're going to erase this, and we're going to show an electric field that looks like this. What are some things we can now say about this wave? What are some things we can do to it? Everyone, what are some things we can say about it or change?
You can shrink it.
You can shrink it. Yep. You can make it a lower amplitude. What else?
You can compress it or expand it.
You can compress it or expand it. That would be the equivalent of changing the frequency and the wavelength. What's another thing you can do to it?
Change the phase.
You can change the phase. You can shift it a certain amount, in which case it becomes offset, like this. Or you can change the phase in the other direction, in which case it let's say moves here, and it starts later. And again, these exist through space. All right, so you can change all of these functions about an electromagnetic wave. What's another thing you can do with it? If you can change the amplitude, which is the size, could you change the amplitude and make it look something like this instead of like that? Could you make it look like something like, let's say, this?
Oh, if your frequency alters, or
Could you do that?
if the math works.
The math works. This is called amplitude modulation. You're changing the amplitude. Could you change the frequency so that the amplitude stays the same and it goes like this?
That's,
You
yeah,
can do
that's,
anything where the math works.
You're changing the frequency. That's called frequency modulation.
Oh, that's what that means.
Could you change it so that it looked like this?
that's phase modulation.
That would be phase modulation. You're changing where it is in the sine wave. You're changing it spontaneously. That's known as phase modulation. To modulate something means to change it based on some rule book that you have. So what's nice is that you can take these waves and you can put information on them by changing certain things about them. You can change the amplitude, you can change the phase, you can change the frequency, if you have a code book by which to do this, you can make it behave the way that you want. When it gets to the other end, hopefully it looks kind of the same. If somebody with the same code book has the exact same code book and sees the exact same thing, they can do something called demodulation. So you have a modulator and a demodulator. There's a name for a single box that does both of these. What's it called?
Modem.
MODEM is known as a modem. If anyone's ever heard of a modem, there you go. Modulator, demodulator. It puts information into something and takes it back out on the other end. That's known as a modem. Everyone has seen a modem at some point, unless you're really, really young. But modems still work. They can be written in software. They can be physical in hardware, etc., etc. Okay, so now we have established that there are these things called waves that travel through space. So what we're going to do now is we're going to go to the book and we're going to go to, I believe, page 35-ish, somewhere around there. And I will leave it up to you guys to go through the actual exam questions because we've already basically established that we're covering everything. What I'm going to do next, as you're looking at the white blank screen, is I'm going to put this up. Notice that these frequency ranges and wavelengths have different names. 3 to 30 megahertz is known as HF, which is high frequency. 30 to 300 is known as very high frequency. 300 to 3000, we use gigahertz because that means billion instead of million, is known as UHF, which is ultra high frequency. And then in the microwaves, there's SHF and EHF and SHF. And then down low, we have medium frequency and low frequency and very low frequency. So where's the end to all this? Is there a minimum frequency?
Yeah,
What would be the minimum frequency?
zero.
Zero, yeah. Zero, also known as direct current or DC. Is there a maximum frequency?
I don't think so.
No, in fact, if you pick one, I can always pick that plus one. You can always go higher. So the things that are important to remember are these right here. HF, VHF, UHF, because these are the ones where most ham radio operations occur. And these are the ones that will be on your exam. HF, VHF, UHF. Okay. So now, what we're going to do is we're going to shift gears a little bit and we're going to draw something that would be called the big blue marble. And it's got some green on it and it's got some brown on it. Any idea what this might be called?
Earth.
That's Earth, yeah, okay. So there's some continents and there's oceans and okay. So for the most part, we can look at radio waves, and radio waves are another form of light. Right? Let's say we take a red laser and we shine a laser beam, which is an electromagnetic wave, at let's say 660 nanometers, and we aim it in a particular direction. What direction will that continue going?
Same direction unless it
Same direction unless it runs into what? Let's say we
something
have
that doesn't conduct electricity.
well, let's say we have something that looks like this.
An antenna or a prism?
Prism, okay. Right? So let's say it runs into a prism. What will happen to that red light?
It'll bend.
It'll bend. As we know from the album of the Pink Floyd Dark Side of the Moon cover, it will bend at a certain angle based on the frequency. The reason being that inside the prism, a prism is typically made of glass, you have a different index of refraction. To refract means to bend.
Doesn't
Okay,
it change the speed?
it changes it actually changes the velocity of the wave. It doesn't travel at the speed of light in that material, and it causes it to bend. So, if it never encounters something like that, what direction will that light wave travel?
Straight.
It'll travel in straight lines, exactly. Okay, so that being said, if that wave travels exclusively in straight lines and a radio wave is just a really long wavelength form of light, let's use this purple, like this, and this wavelength is, let's say, 40 meters long, as opposed to 660 nanometers. If this wave is traveling in this direction, which direction will that wave want to continue traveling if it never encounters anything?
Straight.
It's just going to travel in straight lines, right? Because a radio wave is just another color of light, right? They're really the same thing. Radio waves, light waves, all electromagnetic waves prefer to travel in straight lines unless there's something that gets in the way. So we have available to us a large number of different frequencies. And these large number of different frequencies look like this. This is a small portion of the band plan. And notice that we have lots of different wavelengths that are now given in meters, and there are frequencies that go along with them. And if you look at them closely, you will see that these numbers, the wavelengths in meters, are not always exact. For instance, 15 meters would be 20 megahertz. The band itself covers from 21 to 21.45. Okay, so it's an approximate wavelength. We call the bands by their approximate wavelengths, and it's easier to talk about than a lot of other things. But by and large, we have all these different frequencies available to us. And in fact, we have frequencies all the way up to 300 gigahertz. And those have a very, very small wavelength compared to, let's say, 2,200 meters in length. When those get into space, they all behave radically differently. So, fundamentally, what do they want to do? What radio waves want to travel in what direction?
A straight line.
Straight lines. Okay, they want to travel in straight lines. So let us take a look at, for instance, VHF, which is 30 to 300 megahertz, and UHF, which is 300 to 3000. These usually travel in straight lines, unless there is some compelling reason to be bent. However, if you look at the atmosphere, there is very little in our atmosphere that causes VHF and UHF waves to get bent and do weird things. They like to travel in straight lines, which means that let's say that I'm a person operating right here, and I send out radio waves as low to the horizon as I can. What is the likelihood, using direct communications, of me being able to talk to this person on the other side of the planet? What do you think?
UHF?
UHF, which is basically line of sight because the atmosphere does not usually affect these waves at all.
That'd be zero then, right?
That's pretty much zero. Yeah, you have very, very little chance. Now, it turns out that sometimes VHF, UHF, it will hug the ground a little bit. What would normally be the horizon, the radio horizon's about 10% further than the light horizon. So occasionally you will be able to get a little bit beyond the horizon. It'll follow the curvature of the Earth. The lower the frequency, the less curvature you tend to see compared to the wavelength, so it curves a little bit more. But by and large, it's really just line of sight. So VHF and UHF are line of sight. Okay, now, because of that also, it turns out that that line of sight on those particular frequencies and the fact that this atmosphere that we live in has very little to do with those frequencies as far as affecting them. What happens when we get those signals up into the atmosphere? They typically Well, they typically go straight through. At those frequencies, our atmosphere has very little impact. Now, we do have a couple of interesting things that happen. The atmosphere is broken up into the D, E, and F layers in this thing called the ionosphere. And this actually is broken up into F1 and F2. And so what you can have happen sometimes is that you can have changes in the ionosphere in the E layer that will take those VHF signals, and you'll have refraction that bends them back to Earth, and that's known as sporadic E. You can also have sporadic E because it's in the E layer, and you'll have sporadic E layer propagation. Another thing that can happen is that you can also end up with these things called auroras, which cause these shimmering clouds. We were talking about coronal mass ejections and stuff like that. Those will typically cause things to happen in the E layer as well, and will cause those signals on certain frequencies to refract back to Earth, and that's known as auroral. So we have sporadic E and aurora, and we also have this thing called MS, which is called meteor scatter. Meteors, when they hit the Earth's atmosphere, they burn up. When they burn up, they create a bunch of ionized atoms. Those ionized atoms, ions are electric. They're basically an atom with an electron ripped off. And what happens is they form a refractive layer that refracts certain frequencies. And the most common frequency for this to work on is 6 meters. Okay, so here's our opportunity to figure out the approximate frequency given the formula of 6 meters. 300 F and lambda. Okay, if our wavelength is 6 meters, what's our frequency going to be? 300 divided by 6.
50.
50 megahertz, roughly. So we can take a look back at our frequency spectrum chart, and that is available as a free download from ICOM and lots of other different places. And look at that, 6 meters. What do you know? 6 meters covers from 50 up to 54 megahertz. So at 50 megahertz, we can have these kind of weird propagation things that happen. What band is the 6 meter band a part of? It's at 50.
HF.
It's covered in the VHF band, exactly.
VHF.
VHF. All right.
Scott, are band and frequency synonymous?
Can be. A band is a group of frequencies. Or a group of wavelengths.
The wavelengths are like the instruments in a band.
Yeah. Okay, so another thing that can happen is that we can have the 2 meter band. We can have signals that get caught in the very low layers of the atmosphere. This is the troposphere, which is where we live. The very lowest layers. And if anyone lives in an area where there are temperature inversions and they say it's getting really cloudy or smoggy today, or we have all that wood smoke that's collecting, that's because you have temperature inversions that trap air at certain temperatures. Normally, as you go up in altitude, your temperature goes down, but it may not be true. You may actually have a warm layer somewhere. And warm air and cold air have different refractive indices, and what happens is that your wavelengths, as you send them up, can actually get caught and bounced around a few times, and then exit someplace far down the line. And this is known as ducting, because it literally forms like a duct, like a heating duct, except that it's a duct in the sky. This is often true on the 2 meter band and the 70 centimeter band. And you can also have another one where you can also have scatter. which is kind of unusual, but scatter is basically you get your signal up into the sky and it refracts in a way that you're not really expecting to, and the signals are not very strong, but it can also end up coming down beyond the horizon also. On UHF, these things are really uncommon. Most UHF signals go up into the atmosphere and do what?
Up and out and talk to Space Center.
Oh
Space,
yeah, think about that. Okay, so what can we put up there in space?
Satellites.
Satellites, yeah. And what can a satellite do? It can take a signal and retransmit it back to Earth. And in fact, we have amateur satellites that are put up in space, run by hams that do exactly that. The International Space Station actually has an amateur repeater on board which does exactly that. It's basically a repeater station 220 miles above the surface. In the Eastern Hemisphere, the Qatari Amateur Radio Society actually got a satellite. They got permission to put up a satellite at 22,000 miles, and it's geostationary and basically covers the entire Eastern Hemisphere. So you need a little more power to get there because it's 22,000 miles up, but it covers a very wide area. So now the question is, since you have these satellites up there, these typically will work at 440 megahertz and higher. The reason being that the signal usually punches right through the atmosphere. So it makes sense that VHF and UHF would very often be used for satellite communications. Okay, so we can play with all that, but now we're going to take a look at things that we don't expect to happen, but happen anyway. So now we're going to draw the Earth again, and here's half of the Earth, and here's some trees and grass and land masses and things like that, and then we have oceans, and okay, so here's the Earth, and now we're going to draw our layers of the atmosphere again. This is the ionosphere. We have the D layer and the E layer and the F1 and F2 layers. And then by that time, we are out into space, what we would typically call space. So, okay, so now basically we have these layers in the atmosphere. The D layer starts at about 50 miles up. And this is about 100 miles up. This is about 200 miles. And this is about 600 miles. Okay, so what ends up happening is the atmosphere is made of what? Come on, everybody. The atmosphere is largely made of what? What gases? What are the predominant things in the atmosphere?
Nitrogen.
Nitrogen, nitrogen and CO2. Oxygen. Okay, so these are the predominant species in the atmosphere. 78% nitrogen, about 21% oxygen. As you increase in altitude, what happens to the densities?
You drop.
It drops drastically. Yep. So, which is fortunate because we have a lot of air down here that where we need it. When you get up to the top of the atmosphere, there's not a lot up there. Okay, so let's look at the structure of nitrogen. A nitrogen atom, 7 protons, 7 neutrons, 7 electrons. Electrons are basically whizzing around in different orbits that we can't see. They're based on probability, and we just have to we know they're there, but we can't actually see them. We can see their effect though. So this is a nitrogen atom. So what would it take to take one of those electrons and force it to leave?
Energy.
It takes a lot of energy, yes. Electrons don't like to be ripped out of nitrogen atoms very easily. So what is it? What actually has enough energy in it to cause an electron to physically fly out of a nitrogen atom?
Light.
Okay, well, there's something that we learned from Einstein, which is that photons, for instance, a gamma photon or something, contain a lot of energy. They have no mass and they have lots of energy. So, what is our nearest source of photons?
The sun.
That would be the sun, yeah. Okay, so the sun does all kinds of things to us. The sun gives us heat in the form of infrared. It gives us sunburns in the forms of ultraviolet. It also gives us visible light. So here's the sun. And it's consistently throwing radiation. It also makes lots of radio waves. The sun is consistently throwing all kinds of photons, X-rays, infrared, ultraviolet, at us on Earth. Our atmosphere works as a filter for most of those things. Most of the ultraviolet gets trapped before it gets to the surface. Believe it or not, most of the ultraviolet gives up its energy before it makes it down here, which is a good thing. Most of the X-rays give up their energy before they get to the surface. If they made it to the surface, we would have a lifeless planet. So that's a really good thing. Most of the visible light, some of it gets scattered up here. Some of it makes it down to the surface, keeping us nice and light. So that would be infrared and visible light, and some of that makes it down to the surface. So, fortunately, most of the ultraviolet and X-rays do not make it down to the surface. So, what happens to their energy? Where does it go?
It's refracted.
Nope.
Heat?
Nope.
Ionizes nitrogen?
It takes a nitrogen and oxygen up there, and it ionizes it. Most of those photons, because each one is a packet of energy, manages to crash into an electron somewhere and cause it to fly out of something. Nitrogen or oxygen. Okay, so now what we have is a situation where we got all these nitrogen and oxygen atoms which make up the atmosphere, and some of them have had this terrible thing happen to them, where we now have nitrogen with a plus and an electron with a minus. We might have an oxygen atom with a plus and an electron with a minus. So we might have a nitrogen free with a plus and an electron with a minus, and an oxygen with a plus and an electron with a minus. The densities at higher altitudes are going to be lower than at lower altitudes, but what do you see that's floating around up there?
Electrons.
Electrons. What are radio waves? A form of what?
Electromagnetic rate.
Yeah, okay. And what happens when light hits a prism? It changes its speed, it changes its direction, causes it to refract. Well, electrons, when an electromagnetic wave of the proper wavelength and frequency hit a bunch of electrons in the form of a cloud, they cause it to do this. Sometimes they will pass through, sometimes they'll bend and go this way and eventually disappear. Sometimes they will go here. Depending on the angle at which it hits, they will, if you want to see what this looks like, you can take a spoon and put it in a glass of water and look like the spoon is bent. It's really cool. Okay, so now you have all this electromagnetic radiation which is bending at different rates based on what? What's actually causing it to happen?
How many electrons are up there?
Yeah, the mere presence of electrons up there. And what is causing those electrons to exist?
Sun.
Solar radiation. Okay, so what happens during the day is that you have a lot of this happening. And what happens at night?
Not very much.
Not very much. And in fact, what happens to those electrons and those positive ions? You get a plus and a minus floating around in space. Does it matter where the electron came from originally? No.
No.
Eventually, an electron is going to find a nitrogen ion and
Combine.
combine, and then you basically, that now is no longer in play. And then sometimes an oxygen ion will find an electron and cause the electron to disappear, and it's no longer in play. So now
Okay,
your
I have a
densities
question.
are changing. Go ahead.
But isn't everything up there moving and it circles the whole Earth? Do they stay
Yes.
where the sunshine is? The other side's dark.
Yes. Yes, it does.
Oh.
Everything moves. Okay, so what we now have is a situation where our frequencies our frequencies and wavelengths that were being properly carried all of a sudden might find that the situation has changed, and what happens to them?
They just keep moving out forward. They don't.
Yeah. So if you are this person on the surface of the earth who is relying on these things for, let's say, information to get transferred from place to place. Let's say that I'm kind of running out of colors here. Let's say you're this person, another person's over here. That path that existed previously that gave you information that would allow you to talk along these distances all of a sudden disappears. Well, it might turn out that a different frequency happens to be able to be propagated by the new condition that you found, or maybe nothing works. Right? This is known as propagation. It's how radio waves move from place to place, where they show up. And so let's think about a couple of things that could cause these to change. Time of day, right? Where the sun is. That's time of day. How about some other things?
Weather?
Not so much. Weather, all the weather happens below this.
Ionization in the atmosphere.
Okay, caused by what? I mean, time of day, because it's caused by the sun. The time of day directly overhead changes. It changes where the sun is, right? How about other factors?
CMEs.
Seasons. Yeah, okay. You can have CMEs, coronal mass ejections, and you can have X-ray flares. If you have a big influx of X-rays, that changes everything. Right? What else?
What the energy that you use when you send it up?
Nah.
No, that's not part of it.
I mean, yes, but no. We're going to assume
Weather?
that's constant. Now, well, again, weather's below all this.
Can other signals interfere?
Nope. Yeah, I mean, yeah, but not really. It takes a lot of energy to ionize the upper atmosphere.
What about meteors?
Yeah, meteors. That's more localized, but how about solar cycle?
Oh, aurora borealis.
Yeah, that would fall under CMEs because they're generated typically by flares. How about solar cycles? The sun undergoes an 11-year solar cycle every 11 years, where the amount of ionizing radiation comes out of it goes up and goes down. We're on the downward slope of the peak right now of this particular solar cycle. So, why is it that time of day makes a difference?
The sun has to send in the radiation to split off the electrons.
Yep, and then suddenly it's not there anymore. And how about
tilt of the Earth is seasons, right?
Tilt of the Earth is
Seasons is the same as tilt of
seasons.
the Earth.
Directly overhead causes more than at an angle. How about meteors? Again, that's typically going to be something that happens in the evening. right? Although that's not necessarily true. Meteors happen all the time. We just can't see them.
Scott,
Okay, so
I can't hear the questions that you're answering from the other speaker, the other people. Can you repeat their questions?
So the question is, what would cause these things to change? What would cause the conditions to change? Okay, so does everybody see this map that's on the screen right now?
Yes.
Okay, super important to see this map. Okay, so this is a map that is generated from an operation from a mode that is known as FT8, which is a digital mode. One of the cool things about FT8 is that when you are using FT8, let me refresh this one. When you are using FT8, we're going to go to an FT8 frequency right now. And I think, oh, come on. Why do you have to be like that? Sorry, give me 1 second here. We're going to pick a frequency that should be active. Can everybody hear that?
Yes. Yes.
Okay, so we are zoomed in. Sounds like a lot of noise, right? Each one of those individual stripes that you see is a data stream from one being transmitted by a station. Anybody who is listening, for instance, like me right now, listening to these range of frequencies, is decoding all of them at once.
I can't see the map.
You've got to work on on your view if you can't see the map. Oh wait, this map you mean? Is your view working? Can you see this?
All I see is you.
Yes.
Okay,
yes.
then you've just got to pick a different view. Up at the top of the screen, there should be the ability to view different things. Okay, so now we're looking at this map, right? And I'm going to mute this because it's really loud. Okay, so just as we are listening to all that, if I had a decoder running, I could be decoding everything that I'm hearing all at once. In addition to that, everybody else who is listening to those frequencies would also be decoding everything they hear all at once. Well, with all that data, given the information contained in the signal, you know where it's coming from. Looking at your signal strength, you know how loud it is. Well, knowing all that, you can take all this data and we're going to say received by grid square, and we're going to look at people in Seattle over the last 15 minutes, and we're going to look at the 15-meter band. Okay, here we go. This is the aggregation of everybody in Seattle who is on this particular frequency band, and everybody they have heard. Every single station that they have heard and put up on this database. Now, what is significant about this? They tend to agree on something. What is it that they tend to agree on?
The distance.
Yeah, okay. Well, how come they can't hear anybody in Boise?
Just skipping over.
It skips right over them. The angle that would be required to make that trip is too steep, and it doesn't work. This is part of propagation. So another thing that happens here is, hold on, let me stop that share. Okay, so now this is on the 15-meter band. Let us change bands and look at the 10-meter band. Well, what do you notice is different here? It's very pronounced that about 1,500 miles away is where you first start to hear stations looking east. But what else do you see happening?
Going way south.
Yeah, look at that path to South America. That's because there is a good propagation path because the sun is where right about now? Somewhere right in the middle of the Pacific Ocean. The sun is moving from right to left on this screen as the Earth is rotating under the sun, which means that the sun is basically now leaving a trail of ions that are good for these particular frequencies to hop from North America to South America and from North America to New Zealand. Oddly enough, if I were to go down to a lower frequency, let's say the 20 meter band, where is the propagation between, you would think if there's enough to cover a higher frequency, you would think that there's enough to cover a lower frequency too, right? That would make sense. Actually, typically what's happening is probably that there's probably enough electrons floating around there and ions that it's actually absorbing the signals and making them not be able to be carried. But notice on this particular band, which is 20 meters, which is a lower frequency, what have we got? We have a path to Europe. We've got a path into like Murmansk. In fact, it's Murmansk. Notice it's almost directly over the North Pole. We've got a path that opens up to Japan. Okay, so now we're going to pick another frequency and we're going to go lower in frequency. And what do you think we're going to see? Notice that they're getting kind of thin, and we're going to go to a lower frequency and we get, what do we got?
Not much.
We got nothing. Okay, but now we're going to pick another one. We're going to go to Germany on that same exact frequency. What do we see? On that same exact very low frequency that does nothing during the daylight. What do you see?
A lot of it, but it's relatively local.
It's pretty local. Well, I mean, it's still, 3,000 miles. And we can stretch that out a little bit. We can go to 40 meters. And what do you see? You see those same kind of local patterns, but you also have paths that go through the darkness all the way to Australia. So it looks like there are definite high and low frequency bands that work better at day and night. And in fact, that is the case, that you end up with different high frequency bands that behave differently during day and night. Some are daytime bands, some are nighttime bands. You actually, with a technician class license, have access to these frequencies through this frequency spectrum chart. So if you look down here, you'll notice that this says Novice and Technician Voice, Novice and Technician CW, which is Morse code, and CW and data, that anywhere that you see this hatched pattern, you actually have some privileges, which is why you have to sort of learn this stuff. So 80 meters is a nighttime band, 40 meters is a largely nighttime band, 15 meters is a largely daytime band, and 10 meters you can actually use voice. That is an almost exclusively daytime band, typically when there's a lot of sunspots. So, propagation, how radio waves travel through space. Any questions on that before we move on?
What was the, it was PSK Reporter?
PSK Reporter.
Somebody put it in the chat.
Yeah, yeah, I'll do that. pskreporter.info. Okay.
.info. That's what I was missing.
Yeah. There's another one actually. Does everybody remember the Voice of America? You might have to be a little older to remember Voice of America. Right. Voice of America was the United States propaganda service to the rest of the world. It's like all the other shortwave broadcasters did. And one of the things that came out of Voice of America was that there are many tools that the Voice of America used to figure out where to send their signals from where and when. So let's say that we want to be in Oregon and we want to talk to somebody in Europe. This tells us at a certain power level and a certain mode of operation what frequency bands work best for those times. The brighter the picture, the brighter the square. Notice you have, this is your time around the clock, starting at 0 hours universal time, all the way around to 24, and then 10 meters, 12 meters, 15, 17, 20, etc., etc. For each of those, it gets filled in, and it basically says if I want to talk to the United Kingdom on the 80-meter band, my best shot is at 0400, which is 8 o'clock at night in Oregon. The reason being that it's 8 o'clock at night here, and it's been dark in England for the last 8 hours, 9 hours, 10 hours. So your ionization has gone down. Lower frequencies travel better at night, largely because the D layer dissipates and allows them to be propagated. That's the same reason that you can't listen to AM radio stations from 1,000 miles away during the day, because the D layer builds up during the day and it absorbs everything. Okay. Questions? Speak now.
So you said there was one talking thing on the 10-meter band. Are there any other talking things on other bands?
All the VHF and UHF frequencies you have complete access to. But HF, high frequency, the only band on high frequency which covers 3 to 30 megahertz where you're allowed to use voice is on 10 meters.
Okay.
Okay, so now we are going to talk about antennas a little bit. And
I had a quick question, sorry.
Yep.
If we want to reference this in the future after we get our ham radio license, is there a place that we can reference this and relearn all this?
There's so many references out there. I mean, you mean as far as like the band plan and stuff?
Yeah.
Or propagation or what?
Just kind of like specifically like what you covered most recently about what time you need to be on the radio to talk to someone somewhere else.
The best way, what do you think would be the best way to learn it?
Doing it.
Doing it. That's exactly right. I mean, everything gives you a guide, but by and large, the best way to learn something is to use it and develop a good feel as to when something works. Like, I know that there are certain times that, like right now, 15 meters, if I want to talk to Europe, 15 meters between 9 and noon, 9 a.m. and noon. If I want to use 15 meters to get into Europe. If I want to talk to Japan, it depends on the band I want to talk on. If I want to get into the Indian Ocean, that is right at sunrise and sunset. You just...
I have one quick question.
Yeah.
Oh, sorry. If we use the wrong band, what happens to the person that doesn't obey these rules?
Nothing. You just won't hear anyone.
But no, I don't mean like I got the wrong band. I mean like I access bands my license isn't supposed to use.
Well, I mean, if you're, this actually does happen, and the first step is that if somebody hears you doing it, you'll get a nasty email saying your privileges don't cover this. If you're a habitual doer of this, what'll happen is that eventually it'll go up to the FCC. The FCC is the one who granted you your license. At a minimum, they can revoke your license. At a maximum, they can give you massive fines for violating the rules. Most people who have licenses don't have any interest in doing anything that would get them in serious trouble, so they typically are pretty well behaved. But the fines that can be levied are tens of thousands of dollars a day. If you do something egregious and you know it's wrong, they can put a lien on your house. They can do all kinds of stuff. I mean, they can take you to court. Criminal charge, civil court, criminal court.
Scott?
Yep.
Could you please post in the chat the link for the PDFs?
Which one? The band plan?
Yes.
Okay.
And possibly the map.
Okay. The map, I mean, that's going to be vocap.
Hey, Scott.
Okay.
Yeah.
Yes, Ken. Can I just offer?
Yes,
one
please, because
comment?
that gives me a minute to take a breather.
Yeah, you bet. So that's a really good question. What happens if you operate out of the band? Well, potentially, as Scott suggested, you could be, there's monitoring that's done in the bands. You could be detected by the FCC or one of the folks that help the FCC monitor, including folks in the amateur community.
We're
And you
largely
can get it.
self-policing.
We are a self-policing service as Scott says, to a great degree. And you could get just a little notice, or as Scott said, you could get fines. Now, here's the reality. We all make mistakes, okay? It's one thing to be operating out of band a little bit, and it's another thing to be saying vulgar things, operating in bands you're not supposed to, not having a license, all these sorts of things, which will get you in a lot of trouble. But you have to pay attention to where you're operating. And here's a really good example. Scott and I are both extra class operators, right? And so extra class operators, we think we could pretty much go and operate anywhere we hear another amateur operating. But Scott, is that true?
It is not. And in fact, I know that because when I was on Wallace, it's a different it's a different ITU region, and the rules are different.
And so even the Canadians have, like, for example, on 20 meters.
Yep.
We've got privileges. They got different band edges. For voice, for us as amateur extras in the United States, our voice privileges start at 14.150 megahertz. Correct, Scott?
Yep.
But Canadians have voice privileges below, and other countries have voice privileges below 14.15 megahertz. So as a big shot extra class operator, we might be working a contest or a DX station or whatever that's operating out of our band and think we could just roll down there and work them. And all of a sudden we've worked out of band because we weren't paying attention. So anyway, but was that intentional?
No.
Of course not. It was a little mistake. Okay. So anyway,
here's the other thing. Everybody can everybody see the spectrum chart that I put up on the screen?
Yeah.
This is the neighborhood that we live in. What do you notice about the neighborhood that we live in?
Oh, it's very blue.
It's really crowded, isn't it? It's really crowded. And anywhere that you see these teal sections that say amateur, those are our allocations. So, like, here's the 6-meter band. Notice this little sliver, which looks really big on our chart, but when we go and look at it on the big chart, this is spread out into, right here, 3 is high frequency, VHF, UHF, etc., etc. There's a lot of space out there, and most of it is not ours, is it? We have to be good neighbors. That's a big part of getting an amateur radio license, is understanding that we are just a small sliver of the big neighborhood, and that everybody somehow has to coexist.
Can we use our license in another country and then use their bandwidth, or are we limited to the U.S. with our license?
If you have been authorized by that country to operate there, then you use their rules.
Well, I can't just bring my ham radio, if I have one, up to Canada. I'd have to get permission to use it there.
Actually, no. Between the U.S. and Canada, it's automatic reciprocity.
Oh, okay. So we obey the rules of wherever we are. We're allowed to use it. Thank you.
It depends. It depends where you are.
Oh, okay.
So we look then at the frequency chart over here, and we see here's our little section of the spectrum. Right? We follow the rules in our section of the spectrum, but here's an interesting question. I was actually on the 20-meter band, which you see 20 meters, and it was during a contest, and I heard these guys having a conversation on upper sideband at 14.349 on the dial frequency. This is one of those things that we're going to cover. 14.349 is the dial frequency, and it's upper sideband. We are allowed to be pretty much anywhere inside this window. Here's the 20-meter band right here. It says 20-meter band. We are allowed to operate anywhere inside this window. Unlike virtually every other service, we do not have channels. We are allowed to tune our radio anywhere, so long as the only rule is that our entire signal is contained inside the goalposts. in between 14 and 14.35. I saw this guy, I heard him. He was having a conversation with someone on 14.349. That sounds okay because it goes up to 14.35. Except that it's not, because he was on upper sideband, which means that his signal extended up to 352. And I heard it, and I wrote down his call sign, and I mean, he was having a conversation. It's not like it was it's not like it was silent or anything or in private, because there's no such thing as privacy. And I sent him a note saying I'd rather you find out from me than from an official observer or volunteer monitor, or from the FCC. You were transmitting out of band. Here's the time. Here's the frequency you were on, and the reason you were transmitting out of band was because you were on upper sideband with a dial frequency of 14349. You probably just want to hear it from me that you really shouldn't go above 14347 because it violates the FCC rules. And I'm happy to tell you, and he never answered me back. I assume it made it because it didn't get returned. And he probably, put his tail between his legs a little bit and just carried on and hopefully understood what I was saying. I'd much rather he hear that from me than from somebody more official. And that's where he's saying, self-policing.
Scott.
Mm-hmm.
It's Kent. I have something that is germane to this, if you don't mind. It's kind of cool. Would you mind me showing it? Could you let me share my screen?
Yeah.
Then I will leave you alone. This is kind of a cool thing to give everybody a little perspective.
You can share right now, I think.
Okay, here we go. There we go. Come on, baby. Okay. Whoop. Trying. You guys see my screen?
Yep.
Okay,
Yes.
good. Let me slide this out of the way real quick. All right, so this is the radio spectrum, and let's see if we can show this a little bit more precisely. Okay, so you saw this slide earlier, right? From Scott?
Yeah.
So let me show you a couple things here. A couple more things on this. This shows each one of these strips represents different bands. So there's ELF, VLF, LF. It's listed on the left side of the screen. Okay, so this is just the electromagnetic spectrum. That's all that's showing. Here's a little bit more information. So that's where AM broadcasting is. There's FM broadcasting. Here's TV.
Yep.
Okay. There's aviation radio. Now, ham radio and a couple other services, I'm going to show you here now. So here we go. So there's CB.
Tiny little sliver.
Got it? There's another radio service called MERS. It's another radio service.
Multi-user radio service. Multi-use radio service.
And it's on VHF. There's FRS and GMRS. These are all unlicensed services. Here's ham radio.
Ken, sorry, GMRS,
Wait.
you do need a license.
Yeah.
Sorry.
Yeah, you did not, but you don't have to test.
But Kent is marking all the ham bands.
Oh, I get it. Apologies.
Okay. So I always like to show that. Why get your ham radio license? Well, if you're in the radio, you got a lot of opportunity here. We got a lot of spectrum. So anyway, I thought you'd find that interesting, Scott.
And all those bands do different things. Thank you.
You're welcome.
Scott,
I'll leave you alone.
Channels. What's a channel as opposed to what you're describing?
Okay, a channel is a standardized frequency that you have to obey. Like if you use Family Radio Service or GMRS, you're on channel 22. That is a standardized frequency that everybody has programmed into their radio, and you are not allowed to change that frequency unless you go to another channel. We don't have channels, with a very few exceptions. We are frequency agile. We have a lot of privileges that a lot of other radio services do not have. We can do a lot more and a lot different things than other services. All right, and wait. Before we get there, The next section is going to be basic electronics. So we just did propagation. We haven't done antennas yet. So we're going to do basic electronics first, and that'll feed into antennas. Okay, go ahead, Sarah.
Do you have time to share strategies when you have unauthorized operators on the airwaves? I know you can't chat with them, but are there strategies to deal with them?
No,
Do you have time?
you have to. You just ignore them. They don't. You're not allowed to talk to them, so you just ignore them.
So
All right.
We can listen to anything, but only some things, only some places we can talk. There's no problem with listening.
Correct. All right, 5-minute break, everyone.
Yes, thank you.
To the person that asked that last question about like strategies, I would suggest just make a note, like of times and maybe how long, and then if you have the time or if you're like paying that much attention, maybe like the content if you're willing to do that, and then try to jam up like a report. You could send that to the FCC if you have no means of contacting.
Yeah, it's not usually, well, if it's an intentional problem and not a repeater, I don't deal with it because the repeater owners here are really good, but sometimes there's some unintentional stuff that gets really kind of interesting and fun to try to figure out how to deal with. Usually I can email the people afterwards. But anyway, thanks, Gabe.
Yeah, no problem.
This is Kent still hanging around here. If there's any more questions about the testing tomorrow, I can entertain them.
Hey Kent, I didn't really have a question about that, but sort of there was that gentleman earlier that was trying to figure out how to register a new FRN number, right? And you were trying to walk him through that. I was on the for about the last week. I've been trying to get my FRN number on their website, and every time I submit it, I go through and put all the info, password, email, all that jazz, and then it just pops up. There's a problem on the FCC website database end. And earlier this morning, I actually called them and asked them if they have a known problem, and they said no.
Well, I'm not sure. Okay, so let's go back. So you're unable to register for the exam session. Is that what you're saying?
No, I'm not even trying to register for the exam. I was just trying to see if anybody else in the class maybe was. It's the actual FCC website. When I try to get my FRN number, I hit the submit on my registration form, and it says there's an error on their end. And then I called them, and they said that there wasn't one. So I was just putting it out to maybe the class, not even you, that maybe if somebody else is having a problem with that, or if it's just me.
Well, did you clear your history and your cookies?
It's
usually your computer doing it.
Well, but I tried on 2 different laptops and my phone. Same error.
Okay, we're on the FCC's sites all the time. They do have problems from time to time. Normally they're short-lived, and they have been struggling to get everything back online since the government shut down. I can assure you of that. But everything generally seems to be up and running okay. If there was a problem, it should have been short-lived. Or like there might have been a typo. There could be any number of things. For example, what was for example?
Okay.
Sorry, there was somebody asking me a question.
I haven't seen any coupons in a while. We might have.
Okay.
Somebody else. Yeah, I don't know.
At any rate, what I was trying to say is that I have seen people register when they fill out their examination form, and we do verify. We go in and check the FRNs. That I've got typos on the FRNs that have been provided to us, and so I've had to dig a little deeper, do a little research, and I've actually found your correct FRN and corrected in our documentation. So anyway, any number of things could have happened.
Hey, Kent, I got a question. Dennis here. Do you have me registered for the exam tomorrow?
Well, Dennis, let me see. But anybody who's asking these questions about it, are you registered for the exam tomorrow? 3 things you would have had. 1, you would have received an email back after you completed your registration from Exam Tools. It would have been very clear. 2, you would have gone onto our pay site and you would have paid us $10. And 3, you would have gone to a form online where you completed something called an examination agreement form. If you didn't do those things, you're not registered. Okay?
Okay. And
does anyone need the registration link? We still have a few slots remaining.
yeah, I do. Dennis does. Apparently.
Okay.
And that's where I will pay and go down that road, right?
Well, that's where you're going to start. Once you register, you're going to get an email back from the system saying, okay, you're registered now. Go do these 2 other things. So be sure to read that email because it's got the links for your other steps, okay?
Okie doke.
So, okay, look, I'm putting the link in here right now. That's the registration link to start your registration to take your exam tomorrow. Remember, you don't have to take your exam tomorrow. You can take it at another date and time, but this is for the session tomorrow we're going to offer, okay?
Okay.
All right, so let's see.
Sorry, Scott.
I am back. Do we have any questions before we move on? Any questions about the stuff we've been covering before we move on?
Scott, I'm getting out your hair.
Kent, thanks for being here.
Yeah, just in case anybody's wondering, Scott and I are about, I don't know, 10 miles apart. So anyway.
Well, you are now.
I am now. Yeah, I am now. All right, you guys have fun. Pay attention. He knows what he's talking about. Ciao. See you tomorrow. Good luck on your exams.
Thanks a lot, Kent.
Bye.
All right, any other questions before we go on? Okay, here we go. We are now moving into basic electronics. Okay, so now that we've covered what an electron is, which we have, and we've covered what an atom is, we can just draw our atoms, and we can make an atom that looks like this. Here's our nucleus, and here's our s and p orbitals, and all kinds of electrons flying around. The number of protons equals the number of electrons. So we look at nitrogen. Nitrogen would be N, and it would be a 14 and a 7. 7 protons, 7 neutrons. It would have to have 7 electrons. Well, as it turns out, we have lots of different atoms available to us. These could be in the form of hydrogen. It could be helium. It could be beryllium. It could be copper, it could be gold, it could be lead. There's lots of different atoms. There are 92 naturally occurring different atoms in the world, in the universe. So these all have different characteristics because the electrons like to form they like to fill up different gaps that have 2, 8, 18, 2, 8, 8, 18, 18, and 32 spaces in them. Well, the fuller something is, let's say you have 2, 8, 18, that would be a total of 18, which is known as argon. Argon is a noble element. It doesn't react with anything because all of those are full. The next one would be 36, which would be krypton. Again, noble element. The next one would be 54, which is xenon. Same thing. 10 would be neon. 2 would be helium. So these guys are really just completely out of the picture. They don't react with anything. They're inert for the most part. So we're pretty much going to ignore them. The other ones, however, all fall in different categories. Some might have an electron that's an extra one floating around, like there's only 1 available. Some might have 7, in which case there's 1 missing, and it would like to pull it in. So some are right in the middle and we'll decide, oh, well, maybe I can give one away, and maybe I can take one away. So what we're going to do is look at atoms as the fundamental building block of everything that we're doing, right? Anybody know why to never trust an atom? Because they make up everything. Come on, no one? No one's ever heard that before?
No.
Never trust an
Oh.
atom because they make up everything. So
My brother has it on his shirt.
yep.
Only
Okay.
in mathematics.
Okay, so what we're going to draw is the nucleus, and then we're going to draw some electrons flying around, and then we're going to draw another atom with a nucleus and a bunch of electrons flying around, and another nucleus and a bunch of electrons flying around. Okay, so electrons are the fundamental thing that we care about in the case of electric stuff. Electric, electron, etc., etc. So what we're going to do is establish the electron as the fundamental object that we are interested in when we deal with electromagnetism. That kind of makes sense, right? Okay, so an electron is a particle, or sorry, it's an electron is a fundamental particle. It cannot be broken down any further than that. It has a negative charge to it. So there are two things that can happen. If you have a bunch of electrons, you have a net negative charge. If you have a place where electrons used to be, you have a net positive charge. Things that are negative and things that are positive do what with each other?
They're attracted to each other.
They attract. Things that are negative and other things that are negative will do what?
Repel.
Repel. Same thing with positives. Things that are positive, 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 those will repel. So this is called electrostatics. It's very important. It is the fundamental. It is a fundamental feature of how electrons and electric charges behave. Okay, so now we have another thing happening here, which is, let's say we take an electron and we try to shove it into an atom. Now, certain atoms will just suck up the electron and it'll disappear. Certain atoms won't take it at all and it'll bounce back outside. However, some of them they're kind of loose about these things. They'll take the electron in, but at the same time, there's another loosely attached one that will make up for it and will pop out the other side. Well, if you can do that, and you can line up a whole bunch of these atoms, you can have an electron that basically, when you push it in, it pushes one out the other side, which pushes out another one, which pushes out another one, and you have movement of electrons, a net motion of electrons. This is called a current. Movement of electrons is current. That is the definition of current. We measure this using the letter I. The units are amperes, or the big letter A. 1 ampere is 1 coulomb of electrons per second moving across a certain point. That is like 10 to the 19th power, because electrons are really tiny. So what we do is we ignore that fact and we just instead call it 1 amp, named after Ampere, who was an old-timey 1800s, maybe even 1700s scientist. So we now have the need to take electrons and move them from place to place. So if we can line up a bunch of atoms such that we can put an electron in one side and it moves another one and another one, another one, and another one, and it comes out the other side, this is conduction. The easier it is for these materials to pass electrons from one end to the other, the better the conductor we have. So certain things, which are usually in the form of metals are typically very good at sharing electrons and moving them from place to place. You take one in, you kick one out. These are known as conductors. Okay, so name some things that are good conductors of electricity.
Copper.
Gold.
Copper, gold. Other ones?
Silver.
Silver,
Aluminum.
Ag. Aluminum,
Tin.
aluminum is actually very good.
Yeah.
Tin, yep.
Water.
Copper. We said copper. Okay, so we got some good ones. Notice they're all metals. The only problem with aluminum is what?
Fragile.
Actually, it's not. Aluminum wire is great, but you have to treat it.
Temperature?
You have to treat it very. You have to treat it in a very special manner.
It has something to do with the way that it conducts heat.
What happens with aluminum is that aluminum is a very reactive metal, and aluminum likes to form this. It oxidizes very quickly, which means that a piece of aluminum, which is nice and shiny when it's new, will very quickly turn black, which is aluminum oxide. The problem with aluminum oxide is that aluminum oxide is not conductive. Something that's not conductive, we have another name for it. What's it called?
Insulator.
An insulator. That's right. It is electrically insulating. So, aluminum, if you're going to use it as a conductor, you have to make sure that it stays away from oxygen. It's actually a very good conductor of electricity, though. Okay, so things that are insulators. Let's hear them.
Glass.
Ooh, I got glass.
Wood.
Another one.
Plastic.
Wood if
Ceramic.
it's dry.
Plastic.
Yeah, plastic.
Phenolic.
Air.
Phenolic.
Sand.
Ooh, I heard air. I don't usually get that one. Very good. Sand.
Rubber.
Rubber. All right, excellent. I don't usually hear air, which is great. Who said that?
Me.
Yeah, I don't usually get that one. Air is actually a very, very good insulator, so long as it's dry. How about water?
We forgot to say humans for a good conductor too.
It can be. How about water?
Not distilled.
No, distilled water is actually a very poor conductor, so it forms so it's actually an insulator.
Salt water.
But we can put water over here, and that would include people, because people are 90% or 70% water. And what is the significant factor that makes people conductive?
Salt.
Salt water, yes. Salt water is an excellent conductor, and people are mostly salt water, which is why we work in the first place. People generally work by electrical means. All the electrical signaling in our body requires the salt water in order to work properly. That also means that we can be electrocuted and stop working. So, okay, so now that we've established the difference between conductors and insulators, we are going to introduce another thing. So here's a block of a material. And all we know about this material is that it's a black box to us. And we know that in order to achieve a certain amount of current going through it, we have to give the electrons a certain amount of force. We need to push them at a certain rate. We need to push them with a certain push. We have to accelerate them, give them lots of energy to achieve the kind of current that we want to achieve. This is known as a voltage. And that's measured in volts. We use the big letter E for electromotive force. If you look at the word electromotive, that is the force required to electromotive. Motive, move, electron. So this is also known as EMF, or electromotive force. We measure it with the letter V for volts. The material itself, one of the intrinsic properties of a material is its resistance, or how much it resists the flow of electrons. The formula that relates these two, we are going to be asking you to memorize this over and over and over and over and over.
Ohm's law.
This is Ohm's law. This is Ohm's law. Named after
Ohms.
Named after Georg Simon Ohm. He's another one of those early scientists. If you were a scientist in the 1800s and you came up with something cool, you got to name it after yourself. So, notice I said laws, plural. There's actually another Ohm's law, which is power, which is measured in watts. And power is equal to current times voltage. So, Ohm actually got 2 laws named after him. Okay, so we now have these 2 formulas, Ohm's law and Ohm's law. Okay, so what we're going to do is we're going to start with a simple circuit. Circuit comes from the word circle. It means a loop, where we're going to draw a battery. This is known as a schematic. A schematic is how things are laid out in a drawing. It is important to know what schematic symbols are. A symbol is something that represents something real using a layout drawing. So this is a battery. This is a resistor. This right here, that's a ground. Ground is a 0 reference point. So this is going to be a reference of 0 volts. That's our 0 reference point for our circuit. A circuit is a loop. Okay, now the assumption is that this is a piece of wire, and we are going to make an assumption about this, that this is a perfect conductor. If something's a perfect conductor, how much resistance would it have?
0.
No resistance, 0 ohms. Resistance we measure using, look at that. They're called ohms. Ohm got really lucky here, didn't he? He's got 2 laws and a unit named after him. Okay, something that has 0 resistance is a perfect conductor. Something that is a superconductor also has 0 ohms resistance. And you will see why that is important. Okay. So now we have drawn our circuit. It has 0 ohms resistance in all the wires. And what that means is, by Ohm's law, what's Ohm's law again?
E equals I times R, or P equals I times E.
Well, E equals I times R. We're going to draw it like that. This is the same thing. Notice that circle again. This is a very convenient way of dealing with things, and you'll see why. Okay, so a battery is a pusher of electrons, which means that a battery has a voltage assigned to it. Depending on the chemistry inside, it has an E, which is electromotive force, and we measure that in volts, and we'll say that this is a magical 10-volt battery. It has a plus terminal and a minus terminal. Where do the electrons come out of? The top or the bottom?
The bottom.
The bottom, that's right. Okay, so the electrons come this way. They go around the circuit, and they go this way, and this way, and this way, and back to the positive terminal because they are attracted by the positive. Okay, so just to be confusing, which way does the current flow?
Counterclockwise?
No, it goes from one terminal to another. By convention, current always flows from plus to minus. This was called a mistake. That was caused by a lack of understanding of the fact that electrons were negatively charged. The assumption was that at the time that current was theorized, there was no such thing as a negative particle. There was no such thing as an electron because people hadn't found it yet. So they guessed, and it made sense that things that were plus went to things that were minus because, you always go from higher to lower, right? Well, it turns out they got it wrong. And almost 200 years later, we are left with that mistake, and that is the way that we all teach everything. That is the way it works in engineering. That is the way it works in electronics. That's just the way it works, and you just grow to accept it. You know, deep in your heart, that electrons go the other way, but current goes from high to low voltage. This is a resistor. It has a resistance, which is measured in ohms. And in this particular case, we're going to say that this resistor has a resistance of 10 ohms. Okay. Now, another fundamental thing is that when we are looking at simple circuits, we have no accumulation of electrons. So if you have a certain number of electrons here, they have to go through the resistor, they have to go through this wire, they have to go here and here and here. They don't accumulate. So this is actually known as Kirchhoff's current law, or KCL, which says that the sum of all the currents going into a point has to be the sum of all the currents going out of any point. That point is called a node. But you don't have to know that for this. But for the sake of doing this, we have to figure out we have a 10-volt battery and we have a 10 ohm resistor. Well, okay, because we have no resistance by Ohm's law in our wire, if our resistance is 0 and E equals I times R, and that's equal to I times 0, and we have current flowing, which is greater than 0, what must E be to make this true? It must be 0, which means that we have no voltage loss across this piece of wire. So with respect to the bottom, the ground, what voltage exists right here? 10 volts. What voltage must exist right here? 10 volts. If we're at 0 volts right here, what voltage must exist right here?
10 volts.
10 volts. And this is because we have a perfect, oh, sorry, no, 0 volts.
No, 0 volts.
0. What voltage must we have right here? 0 volts.
0 volts.
Okay, which means that across the resistor, how much voltage do we have?
10 volts.
We have 10 volts, which means that since we have that, we can do Ohm's law for the resistor and figure out the missing thing. What is the missing thing? We don't know the current. But we do know that still E equals I times R. We don't know the current. We know that the E is 10 volts, and we know that the resistance is 10 ohms, and we know that we have a divisor bar there, so I is equal to E divided by R, which is 10 volts divided by 10 ohms, and a volt per ohm is an amp, and that is 1 amp. So that is our current. We have 1 amp flowing in that circuit. Okay, so now, using the other part of Ohm's law, if we have 1 amp flowing out of the battery, and we have 1 amp flowing through the resistor, and 1 amp flowing back down into the battery, how much current do we have everywhere in that circuit? How many amps?
1 amp.
1 amp. Okay. So if we know that we have 1 amp, can we calculate the power?
Yes.
Okay. Power is equal to E times I, or I times E. Doesn't matter which way you write it. We can do another circle. P, I, E. We don't know the power, so we can cross that out. Then we have I times E down here is equal to 1 amp times 1 volt is equal to 1 watt. So how much power is the battery supplying?
1 watt.
10 volts.
No, how much power?
It's 1 watt.
1 watt. How much power is the resistor using up?
1 watt.
Okay, excellent. So here's the most important part of this question. A watt is a joule per second. A joule is a unit of energy. That means we are producing energy at a rate of 1 joule per second. That is how much, and that is how fast we are delivering energy from the battery. What is making that energy?
The electrons moving.
Yeah, no, but what is actually making the energy?
The battery?
Yeah,
chemical process in the
There's
battery.
a chemical process in the battery that is making that energy. And it is making it at a rate of 1 joule per second. And what is happening to the battery's capacity at the same time?
Decreasing.
It is decreasing because you are using it up. It only has a certain amount of energy stored in it. When you use it up, it goes down. Okay, so now, what is the other device in this circuit that is either generating or using energy?
Resistor.
Resistor, okay, and at what rate?
1 watt per
1 watt. Okay, so the resistor is using energy at 1 joule per second, or 1 watt. Okay, where is that energy going?
And heat.
Comes out as heat. Resistors convert energy and power into heat.
Heat and light if you do it really wrong.
If you do it really wrong, yeah.
Or smoke.
It can generate smoke. Usually that's caused by carbon when you make it too hot and it burns up. So the resistor is generating power at a rate of 1 watt. Okay, so let us say that that resistor has a rating, because of its size, of 1/2 of a watt of power dissipation. What will happen to that resistor?
It's going to get really hot.
It's going to get really hot, and if you keep going, it will turn black, and it will probably catch fire and start smoking, at which point the smoke comes out of it, and then it doesn't work anymore.
Hard to put the smoke back in.
You can't put the smoke back in once you've let it out. That's exactly right. So things have power ratings. That's actually very important to note, because we're going to draw another circuit. And here's our next circuit. We're going to draw a battery. And this is a 100 volt battery. It's a much bigger battery. And here's a resistor. And we're going to close the circuit, and we're going to ground the negative terminal, plus and minus, and we're going to make this a 10 ohm resistor. Okay, somebody take on how to set this up. What are we missing?
We have to start knowing how many watts are coming in.
No, we need to know what. What's our missing value?
Current.
Because our E is 100 volts. Our R is 10 ohms. We have current that has to flow. And what formula do we use?
E equals IR, so there would be.
Okay, and we don't know our current.
E divided by R.
We don't know our current, so it's, I is equal to E divided by R. Is 100 divided by 10 is equal to 10 amps. Okay, now let's say that at that time we want to calculate our power. What formula do we use for our power?
E equals
I.
P equals I times E. Okay, we have now 10 amps. Okay, and how much current is the battery delivering? How many amps?
10 amps.
10 amps. And what's the battery voltage?
100 volts.
Okay, so what's I times E? It's 10 times 100.
1,000 watts.
1,000 watts. That's a lot of heat, isn't it?
1 kilowatt.
1 kilowatt. Any idea what that might be used for?
Space heater.
A space heater, yeah. You take that resistor and you blow air past it, and it would cause it to heat up. You could also use it as a cooking element for a heating element in a cooking element on your stove. You could use it in your oven. So you're generating 1,000 watts of heat. Okay, so we're going to add a device to this and say, what is our normal current that's flowing in this circuit? Everyone? What's our normal
10
current?
amps.
10 amps. Yep, okay. So what we're going to do now is we're going to say that something went wrong in this circuit.
Hello?
Hello? Can you still hear me okay?
Yes.
Okay.
Yes, sir.
So what we're going to do is assume that something went wrong in this circuit. And we're going to say, instead of 10 ohms, you had a partial short across the resistor, and it is no longer 10 ohms. It's actually 5 ohms. All right, so now your new circuit resistance is only 5 ohms. we're going to do our calculations again. What's the first thing we do? Because it's not 10 amps anymore. What formula?
100 divided by 5.
Okay, E equals IR. Always rewrite this. We don't know our current. I is equal to E divided by R is 1,000 divided by 5.
Is 100 or 1,000?
Oh, yeah, sorry. 100 divided by 5. There we go. Okay, 100 divided by 5 is?
20.
20 amps. Okay, what's our power? Go through our P equals I times E. What's our new power?
2,000.
So we have 100 volts. It's I times E.
2 kilowatts.
20 times 100. Yes, is 2 kilowatts. Okay, so what will happen to our resistor if that happens? Remember, what was it designed for?
For cooking or lights.
1 kilowatt.
It was designed for 1,000 watts. And how much power are we now putting through it?
2,000.
What's going to happen to it?
Smoke.
It's going to burn.
It's going to burn up.
It's going to overheat and burn up. And what happens if that is, let's say, inside a piece of equipment inside your wall? What will it do?
Hopefully blow
All
up.
Smokey Bear.
Yeah, well, no, hopefully it's not going to blow up. Hopefully it's...
Pop your circuit. Pop the circuit breaker.
Yeah, well, I haven't gotten there yet. So what's going to happen is that now we have too much current being pulled, and let's say that you are unlucky enough that this doesn't burn up that fast.
Ooh.
And you have a wire that's running through your wall. And how much is that wire designed to carry? How many amps?
20.
No, it's not designed to carry. Well, how many would we have designed it for?
10 amps.
10 amps. And suddenly it's carrying 20 amps. And now a real wire does not have 0 ohms resistance, does it?
The real wire melts.
And the real wire, let's say it has a resistance of 0.1 ohms, and previously the wire was carrying that, and now that and it was doing 1 watt of heat, and now it's carrying 2 watts of heat. Right? And there's a threshold at which, let's say 1.5, at which the wire gets really hot. What happens to the wire?
Melts.
It gets hot. And what happens if it is leaning up against a piece of wood inside your wall?
Fire.
It burns your house down. That's right. So what we do here is we add a device that will basically prevent overloads. We go in right here and we throw in a device that looks like this, which is a black box. There are 2 things we can use here. What would they be?
Fuse.
Okay, we can do a fuse or
Circuit breaker.
Or a circuit breaker, which is an overload device that looks for current, compares it against what's actually there. If it's too much, it gets hot and it trips. Or in the case of a fuse, it melts on purpose, thus protecting your house from everything else, protecting your house from burning down. So why is it important if you have let's say a 10 amp fuse right here? If you have a 10 amp fuse right there, why would you not want to replace that? It's like, oh, well, I'm going to put a 20 amp fuse in here. Why would you not want to do that?
Because the wire's not great.
The wire's not designed to carry that much current, and then you burn your house down. Mm-hmm. Anyone know anybody who ever put a penny in their fuse box?
Yes.
Yep.
Yeah, you know why you don't do that? Because there's no overcurrent protective rating on a penny. It might work for a bit. Yeah. Okay. So that's your basic electrical stuff. Okay, now we're going to move on from direct current. Didn't even know you were talking about direct current, did you? So
Got the resistance on a penny has gone down with inflation.
it has, yeah. Well, and actually, it used to be all copper, and now it's copper and zinc. And actually, you can't even get them anymore because they stopped minting them.
Yeah.
So, if I were now to draw this battery and have a plus and a minus, and I say that this is Okay. Which direction? Oh no, penny in a fuse box? Not a joke. It used to be these little round fuses, and people, if they blew a fuse and didn't have a replacement, they would actually stuff a penny in the fuse box as a fuse.
Yep.
Yeah,
Seen it done.
that's not a joke. People did that.
Yeah.
Pennies are cheap compared to a fuse. Okay, so let's say you have a voltage and a current and a resistance, and actually it might have worked for a very long time until your house burned down. Okay, so which is this direction ever changing? Is this current ever changing direction? Yes or
No.
no? No, it is always going in the same direction. Okay, that would be known as direct current. Okay. How about if I had somebody who was very, very well paid, who I could convince to take this battery and let's say every 1 second until I told him to stop, take this battery and flip it upside down.
Alternating current.
Yeah, well, I'm paying somebody to alternate the current, and what would happen to the current direction?
It would still go the same way.
No, it would go this way. Because it goes from plus to minus. I'm paying somebody to flip the battery upside down, and then after another second, I pay him to do it again, but flip it now the other way, and I have to redraw my battery, and it looks like this. Now the current flows this way. Basically, that resistor is having the current switching directions in time. It goes one way, then it goes the other way, and then it goes the other way, and then it goes the other way, and keeps flipping back and forth. So that is no longer direct current. What would it be doing? It's alternating direction.
Alternating.
So that would be called alternating current. And that would be AC. So there's DC and there's AC. Okay. So now it gets really, really, really expensive to pay that guy to do that all the time. So what I instead do is I build a device that does this. Notice the picture of a sine wave. The current, or the voltage there, looks like this. It goes plus, and there's a minus side. And notice it's in the picture of a sine wave. What thing made a sine wave? Where did we get a sine wave from?
Frequency? Motor?
Something turning, right? Making a circular pattern. Well, it turns out that a motor, when it's being turned by something else and run backwards, essentially does this. A motor generates a current that has a sinusoidal pattern that looks like this. When it's run backwards, it will generate a sine wave. And in reality, a three-phase motor will have, when run backwards, it operates as a three-phase generator, and it produces sine waves that look like this. Three of them at once. That's known as three-phase AC. The reason we do that is because if you add up all three of them together, the end result is zero, so you don't need a return wire. They add up to zero. It's very cool. Okay, so let's say that we take one of those phases and it has a sine wave. And what can we say about this voltage? It goes positive and it goes negative. What else can we say about this voltage? It has an amplitude. And it has what else?
A frequency.
It has a frequency. How many hertz is our typical wall voltage?
60.
60 hertz.
60.
How many volts?
It's 100. Roughly.
Well, that's kind of true.
119.
No, actually, how many volts?
120 RMS.
Ah, there we go. It's 120 volts RMS. Okay. So, what I'm going to do is digress briefly right before we take lunch, and we're going to discuss this thing called RMS. Okay, so if I have a battery right here, and we're going to have a battery that makes 120 volts. What's the voltage on that battery?
120 volts.
120 volts. Okay, excellent. How about if I have a resistor that's 120 ohms? What is the resistance of that resistor?
Still 120 ohms.
It's 120 ohms. Does it matter which way the current's flowing?
Yep.
Nope, doesn't care. Okay, by Ohm's law, we're going to have 1 amp. What is the power being generated or dissipated?
Oh, by wattage.
It's 120 watts. Everybody agree with that?
No.
Okay, but now we're going to take a different power source. We're going to take this and replace it with one of these.
Oh.
Okay, that has a voltage that looks like this. So let's say that we have 120 volts up here at the peak and minus 120 here. When we're at 120 volts, how much current is going to flow?
1 amp.
1 amp. Okay, so power at the peak is 120 watts. I think we all agree with that. How about when the power is down here?
Is this maximum, what, lower?
No, it's still going to be, because the current changes direction and the voltage changes direction, and negative times a negative is positive.
Positive.
So your power is going to be 120 watts. But when is that true? It's only true at two
Only
times.
at the peak.
Only at the peaks, yeah. What about the rest of the time? How about like here?
Am I losing you?
Huh?
Yeah, lost you.
Yeah, I'm losing you too.
We're losing you, Scott.
Uh-oh.
Maybe your headset needs charging?
Oh, no, it shouldn't. Can you hear me now?
You're
Yeah,
good now.
Yeah.
Okay. So what happens when it gets below the peak? How much power do you have at that point?
0.
Not as
Less
much.
than 120
Less than
watts.
120 watts. And how much do you have when it crosses over at 0 volts?
0.
You have 0 volts. Uh-oh. Okay. Well, how much power does the DC circuit make? 120 watts. And how much of the time does it make that?
100%.
100% of the time. This one only makes 120 watts at the very peak. So what you need to do is you need to take... Can you guys still hear me okay?
Yes.
Yes.
Yeah.
Okay, I just need to make sure. I'm going to do a little...
RMS.
Okay, the audio is still there. That's good. Okay, so what this means is that at your peak, you have 120 watts, but everywhere else it drops down, which means that you've got this. Up here, you've got that same flat line. How do you fill in all these gaps?
Capacitor.
Yeah.
How do you fill in all those gaps?
Oh. But a different phase.
Well, you can't. You only have one sine wave.
Oh.
When you plug your circuit into the wall, you only have one sine wave available to you. That's it. You get what you get. How do you make it so that your power is the same?
So how do you smooth it out? I'm not getting what you're saying.
How do you make it so that you still get the same amount of power all the time? Well, there's no way to. But what there is a way to do is make it so that your average power averages out to that 120.
Right.
And the way to do that is you instead don't have 120 volts, you actually have this.
Yeah, way over.
Where you have plus 170 and minus 170. And what it turns out is that at the peaks, that accounts for all that loss of power.
The true RMS would be 120.
That is known as root mean square, or RMS. So when your voltage in your wall, you plug your meter in and it says it's running at 120 volts, it's actually not. The average equivalent that would make the same amount of power is 120 volts DC. That's known as 120 volts RMS of your AC. And what you find is that you need 170 volts peak. If you actually measured the voltage that was coming out of your wall socket on an oscilloscope, which is a nice little thing that basically makes a graph of voltage versus time, it would actually peak at 170 and negative 170. You're like, wait a minute, we have 120 volts. Why do we have 170? And that's because it's actually doing something called an RMS calculation. So
why isn't it 240 for the peaks?
Okay, that is a really good question. Here we go. What is power?
Watts.
Yeah, what's the units?
Oh,
I times E, right? Well, it's I times E, and
Okay.
it's in watts. You got the watts right. Sorry about that. It's I times E. What's Ohm's law? The other portion. E equals I times R. These you have to be able to recite from memory. I work as an electrical engineer. I build machinery. 90% of problems that I encounter are Ohm's law. They are solved by Ohm's law. Truly 90% of my debugging comes down to Ohm's law. Ohm's law is like super important. Okay, but now if I have P equals I times E and E equals I times R, can I substitute the letter E? Yep. So now I have P equals I times R, or I squared R.
Okay.
So to get the same amount of power, I need the square root of 2 times current,
Oh, okay. That
which
makes
is actually
sense.
1.414. Which is why 120 volts, and it works for voltage too, goes up to 170, because that's roughly 1.414 times 120 volts.
Or you need a really good meter.
That is why, yes, that is why when you buy a meter, okay, so anyone ever been to Harbor Freight?
Yes.
Doesn't everyone love Harbor Freight? For
Too
some
much.
things? Okay.
For some things.
You go to Harbor Freight and you get a meter and it's $3.99. You can get a multimeter for $3.99, right? Okay, so you plug that into the wall. It doesn't blow up, which is good. Sometimes it might, but you measure, here's your sine wave, and it says your wall voltage is 120 volts. What happens if you plug that in to a circuit and you want to measure a square wave with the same frequency, the 60 hertz, but notice a square wave always makes peak power, doesn't it? Because it goes up to full and down to full. The RMS value is totally different. What will happen is that this meter will say your RMS, your voltage is 170 volts.
Call that pulsating DC.
Or basically, or actually, this case, it'll say it's 120 volts. Sorry. It'll say 120 volts. If I go to a company called Fluke, which makes the meter that I have for work, which is a $499 meter, it will say that this is 170 volts.
This is the 289. This is $1,000.
Yeah. It'll say this is 120 volts and this one's 170. Because for this, you get something called true RMS reading. It actually goes through and analyzes the waveform and figures out how much power is delivered and gives you a real number. Doesn't guess.
So for $3.99, you can get a guess. For the $4.99,
you get a real answer. Right. But notice it's $499.
Right.
Right? Okay. All right. So now we are into capacitors and inductors, and we are going to do that we're going to start that really quick and then go get lunch. Okay. You know what? I'm going to save capacitors and inductors for after lunch. What we're going to do next is series and parallel. So here's our Here's our battery. Here's a resistor. Here's another resistor. Okay, by Kirchhoff's current law, any current that goes in must come out here. Any current that goes that way must go through this. Any current that goes out through any point must go through every other point. So if I have a current, whatever it is, going this way, how much current is going through the second resistor?
Same.
Same. How much current is going down here?
Same.
And going back into the battery, it would be the same. All right. Okay, so what that means is that each of those resistors experiences the same amount of current. Well, what if I have R1 is equal to 1 ohm and R2 is equal to 1,000 ohms? And I have my battery generating a voltage. How much current does each one of them get to experience? Whatever that value I is, they get to see the same thing, right?
Right.
Okay, so now how much power, let's say that this is 1 amp. That's our current. How much power is dissipated by this one?
1.
Yeah, it's E equals I times R, P equals IE. This would be 1 volt, and it would also be 1 amp. Or sorry, 1 watt. How about this other one?
It'd be 1,000.
It'd be 1,000 volts.
Right.
And P equals I times E would be 1,000 watts. Okay, so of those two resistors, which one's going to get hotter?
Oh, R1.
Yeah.
The one on the right.
The one on the right, yeah.
Hotter?
E equals I times R, P equals I times E.
Mm-hmm.
It's going to experience a lot of voltage and a lot of resistance. Are they equal in any way? Not even close. So what that means is that if I have, let's say, a circuit that has a light bulb and circuit that has another light bulb, these are in series. Anyone ever have Christmas tree lights?
Mm-hmm.
Okay. This has a resistance of, let's say, 10 ohms. This one has a resistance of, let's say, 10 ohms. They would experience the same amount of current. What happens if I add another one to the chain?
Same. Chris remains the same.
It would have the same.
10 ohms. But they're now all splitting that voltage. They would all get dimmer, wouldn't they? What happened if I put a resistor, a light in here, and it was, let's say, 1,000 ohms? What would happen to the other lights?
Very dim.
They would get very dim. What would happen if this light bulb, instead of being a light bulb, was an open circuit because it blew out? What happens to those other ones?
They all die.
They all die, yeah. So this is the problem with a series circuit, is that if you break the circuit, you no longer have a circuit. Okay, so this is the way Christmas tree lights are done. So let us now draw it the other way, which is known as in parallel. In a parallel circuit, each resistor experiences the same amount of voltage. So if I have, let's say, 10 volts, this resistor sees 10 volts, this resistor sees 10 volts, independent of what the resistances are. Each one sees the same voltage.
Mm-hmm.
That being said, if I were to have two different brightnesses of light bulbs, like this was, let's say, a 10 watt bulb and a 100 watt bulb, which one would be brighter?
About the same.
No, the 100 watt bulb. It's a brighter light bulb. It draws more current. What would happen if I took this light bulb out?
You'd still have a circuit.
Yeah, I'd still have a circuit.
Yeah.
And
So
what would be nice would be that, right, I remove this light bulb to replace it, and did all the other lights in my house go out?
No.
They did not, which is great. That's exactly what we want. Can I add another one that's 100 watts?
Yes.
so long as my power supply is able to source the power.
Right.
Can I add another one?
Sure.
Right? Until I get to the point where I'm pulling too much current and too much power, at which point, if I have a fuse,
it goes.
The fuse will blow. This is what happens, let's say, when you have your microwave running on the same circuit as your hot water heater, running on the same circuit as your hair dryer, and everyone decides that they're going to run them at the same time. You pull too much current, the fuse trips out, you have to go reset the breaker, something like that. Remember I said 90% of problems come down to Ohm's law? This is a parallel circuit. This is how your house is wired. 90% of problems come down to Ohm's law. Okay. And let me see if we need anything else. Yeah, okay. But the next thing is going to be decibels and stuff like that. We're going to add one more device before we go to lunch. Here we go. Here's our battery. Here's our plus, and here's our minus. Current flows this way. Now, let's replace this and say that we no longer have this. We have alternating current, which goes like this. It goes plus, and then it goes minus. Sometimes the current goes up, and sometimes the current goes down. We're going to add another device, which instead of that looks like this. This is known as a diode. It has an anode and a cathode. It physically looks like this, where you have a stripe. The stripe is the cathode end, which is the negative terminal. And a diode is a piece of semiconductor material. Notice we had conductors and insulators.
Mm-hmm.
Semiconductors are usually made of silicon or germanium or gallium arsenide and things like that, which are elements that have like usually 3, 4, 5 electrons, some phosphorus thrown in there that has 5. And because they have a few extra electrons or a few missing electrons, you typically start with silicon, which has 4, and you add a little bit of other material, one of these other ones, to it. And what that does is it creates silicon with a couple of extra electrons floating in, or a couple of extra holes, as they're called. And a hole is a missing electron. And if you put voltage across it, and typically for silicon, if the voltage exceeds 0.7 volts, it will cause it to conduct forward. If you don't do that, if you don't put voltage across it, or the voltage goes negative, you get no current flowing. So you get a big X if it tries to go backwards. What that means is it's essentially a one-way street for current. It only turns on when the current is positive. So if I have voltage that looks like this, where it goes positive and negative for the whole circuit, when it goes positive, I get current flow, and when it goes negative, I get nothing, which means my voltage now looks like this. That has a
That's
name.
your flashing Christmas tree lights?
No. Well, I mean, possibly, but this has a name. This right here is AC because it alternates. What is this called?
Pulsating DC?
This is called ugly DC.
Yeah.
Right? Because it never flips the other way. It either goes to 0 or it goes positive. So a diode is a very important thing because what has it allowed us to do?
Pass current in one direction.
Send the current positive.
It allows us to convert AC into DC. And when we get back from lunch, we're going to go a little bit further with that. This is super, super important because most power comes into our houses in what form? AC. Most of our electronic devices, like my phone,
everything DC,
is DC. How do you convert AC into DC?
Bridge
Semiconductors.
rectifier.
Yep. Well, yes. It can be a half-wave rectifier too.
Half rectifier, yeah.
And what the basis of a rectifier is this device right here.
A diode.
A diode.
It could be a tube.
It could also be a tube. Yeah, it doesn't have to be a semiconductor. You can actually have a vacuum tube.
Yep.
A little older school. All right. How about half an hour?
Okay.
So 20 minutes after the hour, whatever that hour is for you.
Okay.
Is this making sense to everybody?
Sort
It's
of.
getting there.
Yes, sir.
Is it fun?
Sort of.
I definitely have to repeat this class.
No, you just got to study it and then start using it.
This one, that had a selenium rectifier in it.
Which one?
The Grundig on the floor there, the console.
Oh, yeah.
That's 1958. It had a selenium rectifier in it. I put in a full wave bridge rectifier.
Okay. Well, selenium is another one of those things that is a semiconducting material.
You can see that one there. That's a 57 lobe opta. It also had selenium.
Yeah.
And the rest of these up here, I love the German stuff, but most of these are American.
Hey, 1930s, there was no such thing as a semiconductor. They all had like OB2 rectifiers and stuff.
I probably have 1,000 tubes.
Mercury rectifiers, gas-filled rectifiers.
So, Scott.
Yeah.
Are we becoming electrical engineers?
No, unless you want to. But I mean, I do cover this class from the viewpoint of somebody with an electrical engineering degree. And I'm not afraid to dive into those waters because I think the fundamentals of electrical stuff are really important to understanding, what it is that you're studying.
So how much of what you're telling us now is going to be on the test?
If it's in the book, it's on the test.
Okay.
So next week is chip design.
No, that's more like next month. Oh wait, that is next week. Yeah.
Yeah, next month is next week.
No, I never took a class in semiconductor design. That was more like electronic devices. That was physics. I never did that. I did more communications and electrophysics, and basic computer architecture and stuff like that. But the communications and electrophysics was all of the electrostatics, electrodynamics, wave propagation, transmission lines, antenna design.
I can tell you I spent 37 years in electronics, put 3 kids through college, and they're all in their 40s. I took that practice test 3 times and I failed it.
Yeah. Well, because a lot of it's rules and regs. But you know what's really interesting? If you take a look at the extra class exam,
yeah,
you will find that it looks more familiar to you.
Okay.
Like I actually about a year and a half ago I took my Canadian license exams because I was in Canada and I was encouraged to do so. So I studied up and ahead of time. The basic exam, which is basically like the rules and regs and basic electronics, I found way more complicated and harder to prepare for than the advanced exam, which was all like, RMS voltages and power and stuff like that. That was like easy for me.
Made me feel silly. I'm really good at what I do. I've been retired 8 years now, but my brother passed the test and my other brother passed the test and my uncle in BC there passed the test and they want me to. So
yeah.
Yeah.
Yeah, and if you have a technical background, the higher class license exam is actually easier, I think. Because, it's the tough part about this is, okay, you got to start with like, here, let me just put something up. Like, okay, you've got a voltage and you've got a current. That the current looks like this. Okay. Well, obviously these are not in phase with each other. So E equals I times Z. And we're going to get to that. This is an impedance. We're going to get to that after lunch. Yeah, lunch break is happening now. We're just BSing now. So
No,
you have an amplitude and you have a phase shift, right? So if your E is 1 equals 0.5 times an angle of, let's say, 130 degrees.
This is how AC brushless motors run.
Well, that's how capacitors and stuff work. I mean, basically they all cause phase shifts, and then you have your P is equal to I times E cosine of theta, or cosine phi, which is your power factor, and then you have, so that's your real power, and then you have your volt amps is equal to I times E, not including the cosine of theta, cosine of phi, and then you start dealing with power factors and phase shifts and all that other cool stuff that makes life so interesting.
You engineers.
Yep. Well, actually, it's not just us. It's trust me, the power company doesn't want to deliver power that you're not going to use, because it costs them money too. I mean, they have to push current whether you're using it for power or not.
I use very little of the grid. I have a 34 solar. I'm in Apple Valley, California, by the way. So I'm in the desert, and we have 34 solar panels on our roof.
Perfect. That means you've got an inverter.
Yeah, got 2 inverters, both of them
big inverters. Yeah.
But I also have a large pool and central air and a lot of. I'm a big user. My garage here, which is my shop, also has a split system that put icicles on the ceiling if I want. So yeah, I'm a big user, but I don't use the grid.
Mm-hmm. But you do make your own. But do you make single phase or two phase, or 240 center tap, or?
Yeah, the pool and the AC runs on 240.
Okay, so it's 240. So those are that. So that's an A phase and a B phase with a center tap.
Yeah.
Yeah. Okay. So you don't have a 3-phase system, like a 108, a 12208, or.
No, it's 240, and you're right. It's a single phase 240.
Yeah. Which, yeah, again, if you pull a hard neutral from the center, you get your two 120 phases.
Basically the same thing. You can split that up.
Yeah.
But this is a house.
Right. And we do the same thing in industry too.
Yeah.
Well, I mean,
many of the charging systems and whatnot I worked on were 480, 480 volts.
Mm-hmm.
Your hair would stand on end of your arms as you walk past it. Lockout, tag out whenever you worked on it.
What industry was that?
So split. When I graduated in college, I started working on camcorders, VCRs, cash registers, ham radios, and all that kind of stuff. And I couldn't make any money to save my life. I had thousands of equipment back in the late 70s, early 80s. And a friend of mine went to work on electric forklifts, and I did not want to work on mechanical stuff. But I got talked into going there, a career and a pension, and put all my kids through college. Best thing I ever did. I had no idea that electric forklifts and heavy equipment, electric exclusively, was all PC-based software.
Yeah.
They're much more complicated than you ever could imagine. And I was the go-to guy for that.
So what company?
Well, I worked at Caterpillar and Crown Equipment.
Yeah.
Okay.
Yeah.
It's got 15,000 employees, and Caterpillar at that time had over 30,000 employees. I don't know what they got now, but
I'm around electric forklifts all the time.
Okay, well, I work with you engineers all the time. Most of them are based out of Ohio or and that back east, Midwest, whatever. I worked with a lot of engineers, but I was just a tech. But I made some engineers very famous because of feedback and problems that between their education and experience. And I had a lot of field experience, and so 99% of what I did was in the field until the last 10 years or so. I moved up into management. But and I did a lot of training, but none of this had anything to do with radio stuff and measuring heads.
It's all the same.
Around it, as the older I get, and I'm getting old, the older I get, the harder it is to retain this stuff.
Yeah.
Put aside the wrong education or whatever, and just learn it, absorb it, retain it, and pass the damn test.
Yeah, exactly. All right, lunchtime.
Sorry to take up your time there.
Nope. See y'all in 20 minutes for me.
All right.
Okay, as promised, if anybody has any questions for me, I am here to answer.
So, Scott,
Yeah.
it's Sarah.
Hi, Sarah.
I am the only one here, and I've been shoving off being sick. And what I'm really interested in is review of connectors, review of regulations and antennas. And I don't know if I should go home today and come back tomorrow, or if you're going to be talking about those things later on this afternoon.
Well, my goal today is to get through capacitors and inductors and tune circuits, and then that feeds us into antennas and feed lines.
And that's being done tonight?
Hopefully today. Oh, wait, when you say tonight.
Well, it's tonight in New York.
Yeah, it's only 1 o'clock here, so.
Yeah.
Sarah, what happened to your crew?
Well, one of them had to get ready to go to a LEC board meeting. One of them had who knows what, and the other one, who's actually pretty good, but she has a relatively complex life. So I thought that was a sort of long shot, even though she's, if you need her, she's around. If you don't need her, she's not around. They're mostly GMRS folks. So that, and I have a couple other people who said not this weekend, and so I told them, are you going to do a class on Christmas, do you think? You don't know? Okay. Yeah, I basically, I don't.
I might do a general class.
Oh, yeah. So I have my general, but I'm not doing
If you do your general, please keep me on the email list.
Well, if I have your email, you're already on my email list.
Yeah, you got my email. I do have a question, actually. It's kind of along the lines of...
let's see. Sarah, did you have anything else?
Oh, sorry.
You got real students and not just hangers on.
Okay.
So take the other folks first.
All right.
No. I didn't mean to cut you off, Sarah.
Go ahead, Christopher.
All right, real quick. So if I have a call sign with my GMRS, is that going to change with the ham, or am I going to?
They have nothing to do with each other.
So I get another one.
Yep.
Outstanding.
They're tied together through your FRS, but that's all. Or your FRN.
FRN.
Yeah, that's all.
Okay. Yeah, I seem to be doing good on the test. Ironically, even being an electrician, my circuits are what's killing me.
Hopefully not literally.
No, not literally. Not literally. When I heard trig, though, I was quite concerned because it's been about 40 years since I did that.
Yeah, but it's important to know.
No, it is.
I mean, power factor. Power factor is trig.
Yeah. So right now I'm at a relative's house getting ready for an 80th birthday.
Oh, cool.
So it's like, all right, I know this part I've been testing good. I can step away for a few seconds with my earbuds on.
So where are you located?
So currently I'm in Pennsylvania on the border of Maryland, the Mason-Dixon line.
Where?
York.
York. That's still Pennsylvania.
Yeah.
That's up 80. That's up 83.
83. I'm from Long Beach, Long Island.
Okay. But yeah, York is still 25 miles inside Pennsylvania.
Yeah, I know. But and I mean, anywhere from where I live, like you got to cut through Staten Island in the city, and that's like 2.5 hours.
Oh, and go across the outer bridge crossing.
Oh, yes.
Mm-hmm.
It was funny. I was actually listening to the 2-meter in my truck on my way, and it was actually quite active. It was keeping me awake.
Yeah, well, you can probably tell that I have some experience with those areas. I've been across the Verrazano many times.
Well, they just had a jumper down. I got in the middle of the
God.
I was like, oh.
Well, he made it over the edge.
He made it over the edge.
He didn't survive it, I'm sure. Nobody survives that.
No.
Yeah.
I was actually a hyperbaric technician during the making of that. So I worked with the scuba divers in the bends.
Yeah, nobody survives that fall.
Mm-mm.
I mean, not even in Saturday Night Fever.
It's not the fall that kills you. It's
the landing.
Stop.
Right.
Yeah, that stop.
I forget who was the name of the kid who jumped over in Saturday Night Fever.
I don't
He
either.
couldn't take it anymore.
Okay, I hate to break in, but
Yeah.
I have
No.
questions and I'm not sure how to ask here.
Oh,
All right. Well,
okay.
deep breath. Nothing can be that bad.
Yeah.
The hardest part is figuring out how to jump in. So Scott, I want to go back to the schematic drawing with resistance on it. It's the resistance part I am struggling with.
Okay, so here it is. Here's the easy way to describe it.
I don't think the schematic, I mean, there's something that's not being accounted for.
Here's the easy way to think about it. All right. You're pushing a couch across the floor.
I understand the concept of resistance.
Yes. Okay.
But in the schematic, there is the squiggly line that
That's a
you're
resistor.
calling the resistor.
Yeah.
That's the thing we're trying to get to do the work. Maybe the radio?
Yeah. It's a load.
Okay.
Also
But
known as a
it's
load.
connected to wires, and the wires have resistance, and they're not included in this in the equations.
Not
Why?
yet. Because I chose not to start. Because that doesn't come until later. For now, you just assume they have no resistance because that gets in the way of learning the theory. We add that when you actually start to build stuff. And we're going to do that maybe today, probably tomorrow morning when we're doing station design. And that's why you select certain gauges of wire because of ampacity, and when you start looking at cross section of wire, cross section and length determine overall resistance on a macroscopic level. That's why we like to use big fat wires to carry lots of current because they don't get as hot because they have lower resistance.
Okay, I'm good for now.
Oh, that can't be it. I like the pushing the couch across the floor, pushing the couch across the floor thing. That's why we put sliders underneath the couch.
Thicker than shag, more resistance.
There we go. A little more comfortable.
Scott, do you like the old tube stuff?
You know, I appreciate it, but I don't like the size. I mean, I know I have a lot of I have friends who collect boat anchors. There's a boat anchor right there.
HQ 145. I restored.
Yes, it is. Does it work? And it works.
Oh yeah, absolutely. My father was an engineer. He worked on the Apollo program and the shuttle program for North American Rockwell and Downey.
Yeah.
I thought I'd do the same thing, but after graduating from college, I realized I'm never going to be as smart as he already is. Not going to happen.
My dad was an engineer on the he was a avionics engineer on the Blackbird.
Oh wow. SR-71?
Yeah.
I got to go on the one at Wright-Patterson in Ohio.
He got to do some pretty cool stuff in his life.
Got to sit in the cockpit.
Did you really? It's not very comfortable, is it?
No, I'm talking about the one that's at Wright-Patterson Air Force.
It's still not comfortable.
They dragged that out of mothballs, and they actually made it flight ready for some event or something. I don't know.
It's still not comfortable.
You know, this thing was leaking oil from every direction. And
yeah.
It says normal.
Well, they leaked fuel.
Because like a certain altitude or something.
Yeah, because all the panels expanded so much that they had to be left essentially separated by a certain amount at the ground when it was cool, which meant that the fuel tanks all leaked.
Sounds like you're talking about the SR-71 Blackbird.
Yeah, we are. My dad worked on the SR-71 on the avionics stuff.
I worked on the avionics for the F-18, the 15, and the AV-8B Harrier for McDonnell Douglas.
Yeah, we were talking about the leaking fuel tanks. That was part of the design. Because the skin expanded and sealed everything up. They said the skin got up to like 600 degrees Fahrenheit or something.
I did a little work on the guidance system for the standard Tomahawk and cruise missiles for General Dynamics Naval Ordnance.
See, I just build machinery. Hey, it's 1:20. You know what that means?
Bring it on.
It means it's time to get started again. Oh boy. Okay. So we have talked all about wavelengths and frequencies and Ohm's law and stuff like that. And now we are going to add a couple of new devices to our zoo of electrical devices. Okay. So everybody stretch out. Get all that digestion done. All right, so what we're going to draw now is a plate made of metal. And we're going to connect this to a wire. And we're going to connect this to a battery. This terminal of the battery is the positive terminal. So what do you think is going to accumulate on that terminal, on that metal plate?
Ions?
Electrons?
You'll have pluses that move from the battery. And if we put another metal plate here that looks like this, I don't know why I drew the bottom part. It's not really three-dimensional, is it? It looks like this, and that's connected to the negative terminal. This fills up with negatives. Right? Okay, so now, what do we have going on here?
Magnetic field.
Not magnetic.
Oh. Oh, an attraction field.
Yep, you have an electric field. There's an electrostatic field that forms. And what what is it attempting to do with those two metal plates?
Jump.
Well, ideally, they're not going to jump, but what's it trying to physically do with those plates?
Bring them together?
It's trying to smash them together. That's right, because they're charged. Okay, but now that you have that, what if you now have a material that you now use to fill up the gap, which is not crushable, and also is an electrically resistive material? What will that do? It'll physically separate the two plates, keeping them from smashing into each other. So, what do those two plates still want to do?
Go together.
They want to crush that stuff. That's right. It could be filled with air. It could be filled with plastic. It could be filled with a vacuum. It could be filled with any number of things, so long as it's not conductive. Right? That's known as a dielectric. We typically use that to separate our two plates. Okay, so.
Hey, Scott.
Yes.
Is this being recorded, or did you turn that off for lunch?
Still being recorded. Yep, still recording.
Great, thanks.
Okay, so now what have we created a situation of? There's a lot of tension in here, isn't there? Mm-hmm. Would you agree with that?
Mm-hmm.
Right? They really want to get together, and physical space is separating them. This is stored energy.
Is that capacitance?
That is capacitance.
Oh,
okay.
My goodness.
And this thing is known as a capacitor. Capacitor stores energy in the form of an electric field. That electric field is trying to pull those things together. So, a couple of fundamentals about capacitors. Once it's charged up, is there any more room to charge it more? Take a look at those plates. They have a physical size. So once you've charged it up, can you put more in it?
No.
No. So you basically have a capacitance, a capacitor. It has a physical limit of how much charge you can put in it. That's known as its capacitance. We measure that with the letter F. That is also known as farads.
A ferret, yes. Ferret,
right?
I remember.
So a farad is a lot of charge, a lot of ability to store charge. Usually a farad is absolutely huge. We either do millifarads or microfarads or picofarads. We usually use very small prefixes. For instance, like a 22 picofarad capacitor. Pico is 10 to the minus 12th.
Is the battery a capacitor?
No, but a capacitor can function as a sort of battery. I mean, a battery is only like a capacitor because it has a charge, but it's stored as a chemical reaction. All right, so this is micro. This is 10 to the minus 6th. Milli, 10 to the minus 3rd. We don't use nano, which is 10 to the minus 9th, just because we have pico.
So I learned something about capacitors.
Yeah.
I'm a boat builder, not an electrician.
And by the way, get closer to the mic.
My boat strobe light had gone out. I turned all the power off and did the stuff I knew I was supposed to do, and I climbed my mast, took off the globe, and I was going to replace the bulb.
Oops.
And I touched it.
Oh, yeah.
Down below, they said they watched my hair stand up.
Mm-hmm.
I toppled over, and my knees caught the mast, and I did not get dead.
Was that like a xenon strobe?
Yeah.
Okay, a xenon strobe is typically going to operate in the neighborhood of 4 kV, maybe up to 20 kV. Sure. Not a lot of current, but got a lot of voltage to it.
You know, I had something happen. I want to know if this is what we're talking about because I don't know if I'm understanding correctly. So
get closer to the mic. Hey, Noah, get closer to the mic.
I'm getting there.
Okay, there we go.
Okay, so I live in a 50-something-year-old mobile home, and I went out into, or I walked up to my box because it popped off. The electric popped off. It was in the middle of the night. I walked over. I got within a couple feet. It arced and sparked me. And it turned out that outside the ground wire had come loose and wasn't there anymore. So was I in that space between the two things? Because there was no ground?
Pretty
so
much,
just
yeah.
my own personal,
it found
my personal electric field?
It found a path to ground through you. There wasn't.
Okay. Well, we don't have a ground here to show us where that would be anyway, but that was what happened then. Okay. It was not fun.
Yeah. I mean, it's okay. So air has a dielectric constant of about 10,000 volts per inch. Dry air has a gap, essentially like an impedance of 10,000 volts per inch. So 1 inch of air will not arc until you get about 10,000 volts across it. So if you have a 20,000 volt, let's say something gets charged up by somebody rubbing their feet on the carpet, and then they come over and they get within an inch of you, they can give you a shock from that. Not a lot of current, but certainly a lot of voltage.
Right. So actually, in the way our math is going, if I had measured, it was dark, but if I had measured how close I was, I would know how many volts jumped out of my electric box and shocked me.
Well, part of it, because was it raining? Was it humid? Was it?
Oh,
there's a lot of other.
Talking ideal when we're talking.
There's a lot of other factors too.
Okay. All right.
Okay. So let's see. So capacitors, we basically have the ability to store energy in an electric field. As Noah said, if you have an electric field and the voltage across the field exceeds the dielectric voltage of the dielectric, you get an arc. Once you arc across a capacitor, what does that mean?
You get a shock.
Yeah, what else does it mean if you arc across a capacitor?
You completed the circuit.
You completed the circuit. So if this is air, it's probably okay. If this is a piece of like plastic and you arc through it, what does that mean?
Shoot it out.
It means it's time to get a new capacitor because it's got a hole in it. So yeah. Okay. So some interesting things about capacitors. Number one, if I take a capacitor and I do this with it, this is the schematic symbol for a capacitor. If I take another capacitor and do this with it, the overall size of the effective capacitor is actually bigger. These add together. So two capacitors in parallel will add. However, if I take two capacitors and I put them in series, let's say I have two resistors, and I have 10 ohms and 20 ohms.
Yeah, 30.
These turn into 30.
They add.
Yep. Okay, if I take these in parallel, like this, and I have 10 and 20, the net resistance is actually R1, R2. We can do Ohm's law to do this, but we're not going to. Is equal to 10 times 20 divided by 10 plus 20 is equal to 6.7 ohms. It's actually smaller than either of the above. So resistors in parallel end up getting smaller, the overall resistance, because your current has two different paths to follow. So the net result is that it's a bigger pipe in a way, which means your overall resistance is lower. So resistors in series will have a higher resistance. Resistors and capacitors, by the way, resistors in parallel will have a lower resistance. All right, so now if I take my if I take my capacitors again and put them in series, this is actually
subtracting
C1, C2 over C1 plus C2. They actually, series capacitors actually behave like resistors in parallel. And because, if you think about it, basically there's this extra space, C1 and C2, the overall plate size is bigger, so the capacitance goes up. It's C1 plus C2. So that's series and parallel for capacitors. Here's the other thing. If we take a capacitor and we do this with it, we hook it up to our battery, what will happen is this will charge up. All right, once it's charged, okay, when it's uncharged and you hook it up, okay, so when it's uncharged, all right, everybody keep the chat down. Okay, so when it's uncharged, you'll get a current flow that will charge up the capacitor.
Once it's charged.
Right? So when you first hook it up, you will see a current flow. But then when it's fully charged, there's no more room and the current will completely go away. So once the current completely goes away, what will happen to your capacitor?
Stays charged.
It stays charged up, exactly. So now, what happens if you take your battery and you remove it, and you take the rest of your circuit and remove it so that you're just left with a charged capacitor, and you were unlucky enough to come along and put one hand over here and one hand over here.
Everybody's got to do it once.
Yep.
Shot.
It probably won't kill you, but you'll get a nice little zap going across it, and you will feel it. So way back when we had a television, which was a CRT, a television screen looks like this. Here's the screen, and here's the back of it, and here's the front, and you would have basically two plates. You'd have the front of the TV, and you'd have the yoke, and these would be essentially a 20,000 volt capacitor. And it would charge up to 20,000 volts. And what would happen is that you would come along and you'd be working on a TV and you'd suddenly get a 20,000 volt static shock. And it would really hurt.
That would wake you up.
That would, yes. And so how do you prevent that?
Plug it and disconnect it every time.
You find a resistor and you go like this. And what happens is that it then finds a path through which to push current, and your capacitor is then discharged. All right, so here's your charged capacitor, but now instead of doing that, I'm going to take my battery and flip it upside down. Okay, so this is negative and this is positive. So where are the plus charges on the capacitor going to go? to the negative terminal of the battery. The negative charges are going to go to the positive terminal.
So it's going to drain the battery.
It's going to drain. No, it's going to drain the capacitor.
Oh, okay, capacitor. Sorry.
Right. So now the capacitor is no longer charged. And what happens is now, after that has completely discharged, you're going to get a situation where this now charges up to negatives and this charges up to positives. Well, that's opposite of the way it was, right? That's backwards. Okay. Well, what if you manage to, before that completely happens, you change it out again? So that you always stay ahead of the capacitor's ability to discharge. You never let it fully charge and you never let it fully discharge.
There'll always be current flowing.
There will always be current flowing. Okay, that is actually pretty profound, because what is this thing that I keep flipping the polarity on? What does it mean if I keep flipping the polarity on the battery?
Oh,
That is AC. That is not DC anymore. So that is AC. And we just showed by virtue of the fact that if we don't ever let the capacitor completely discharge or completely charge, when we have AC, there's always current flowing to a certain degree. What carries current all the time?
Transformer? I don't know.
Wire?
A piece of wire. Also has a name.
Conductor. Oh.
Circuit. Okay. So
That's a
you
short
short
circuit.
circuit the system.
So AC in the extreme makes a capacitor look like a short circuit. If I were to take DC instead and make it look like this, and the capacitor completely charges up. So here's my new capacitor. Capacitor charges up. Here's my plus, here's my minus, and I never change anything. How much current is flowing into that capacitor once it's fully charged?
None.
None. What's another name for something that is never carrying any current?
No.
Open.
That's an open circuit.
Oh,
That's an open circuit for
open
DC.
circuit. Okay.
For DC, a capacitor is an open circuit in the extreme.
Hmm.
All right, so now it's time to add another device. Here comes the other device. Capacitor stores current in an electric field. We're talking about electromagnetics. What is that?
Coil.
A coil, also known as
Inductor.
Inductor. We measure its ability to store energy in a magnetic field when we run current through it, like this.
And that's a Henry, right?
That's a Henry. We measure that in henries. And these are usually measured, again, a Henry is very large, so we'll usually measure this in millihenries or microhenries. If we run current through here, what is this coil made of?
Copper. Likely.
It's copper wire, okay? What do you know about copper wire? Pretty good at doing what? It's good, yeah, good at it's a pretty good conductor. All right, so we now have current flowing through here. If you hold up your right hand, your thumb is the direction of current, and your fingers, as they roll forward, is the direction of the magnetic field that is generated. And notice it makes a loop. So if my current is going this way, it's going like, we use this to measure to show coming out of the paper, and use this to show going into the paper. It's actually making a magnetic field that goes like that. Through a coil, those actually cancel and add at certain points, and you actually get a magnetic field that looks like this. That has these rings.
For antennas, you have a coil, you can have that increase magnetic field, right?
There's more to it. We're going to get to that.
Oh, okay.
All right, but importantly, with an inductor, this actually forms an electromagnet. You have a north pole and a south pole. So, some things you can do with this. You can do this. And what can you do with this end if you hook it to a nail? Anyone ever done this as a kid? You've run a nail through this? What can you do here?
Electromagnet.
You make an electromagnet and you can pick up paper clips.
Ah, okay.
You can do all kinds of fun stuff with electromagnetics. When you disconnect the battery, it goes away. The reason you use a nail is because a nail is made of usually iron or steel, which has a lot of iron in it. It's a ferromagnetic material, which means that it tends to concentrate the magnetic field inside it. So when it gets to the outside, it's still carrying it. It's carrying a very big magnetic field. It makes a nice, strong electromagnet. We use these for things like coils, for moving speakers, converting electrical energy into sound. We use them for microphones. We use them, we're going to get to transformers in a second. We use them for filters. We use them for lots of other things. We use them for relays, where we basically hook a switch up to one, and when we turn it on, this is connected to a piece of copper, and then up here is something that gets pulled down by the electric field, and it closes the switch. That's called a relay. Okay, so now that we have this thing called an inductor, we have these magnetic fields. Once we have current flowing, what's going to happen? It's just a piece of wire, right? What's going to happen? Nothing.
A short circuit.
Well, right. Does anything stop the current?
Nope.
No. Okay. So for DC, what does a coil look like? Looks like a short circuit. Okay, but now we're going to do something a little funky here. We're going to take this coil, and while we have this nice stable magnetic field set up, we are going to suddenly take this and remove it. Or even worse, we're going to do this. And we're going to switch the polarity on it. Well, this magnetic field has what in it?
Energy.
Potential energy.
It's stored as energy. Yeah, it's potential energy. Well, okay. What does the inductor think about that? It's being said, it's basically being told you have to give the battery back its energy and start up a new field which goes in the opposite direction.
Lapses.
That sounds like a lot of work, right? Yeah, and in fact, it is. Inductors don't like that change. They resist it. And in fact, they actually, in doing so, they generate a very large back EMF, as it's called. And what that does is, let's say you take the battery completely out of this, you have all that energy, and now where does it go?
Fingertips.
Can it stay out in space? No. Where does it go? There's only one place here that you can see where it might go.
Back into the circuit.
What circuit? There is no circuit anymore.
Into the inductor?
Once you put a load on there, it's going to go back, it'll complete the circuit.
Except there is no load. I just took the battery completely away and there is no load. The inductor was the load.
If you put another coil next to it, it will induce that current into the other coil.
Yeah, except that I don't have the luxury of doing that. I just took the battery away. This is what I am now left with. Where does the energy go?
It goes into space.
It can't.
No, like as the radio wave, right? Like that's the part that.
No, because there's no electric
It's
portion to go with it.
Does it go into heat?
It doesn't go anywhere.
Well, ideally it goes into heat, but where? There's only one place. It needs a circuit. You guys see a missing part of a circuit?
Ground?
Where's the missing part of the circuit here?
Core or something?
The battery's gone.
Battery's gone. That's the missing part of the circuit. Well, that looks like a convenient place to get rid of all that energy, doesn't it?
Yeah.
How do you jump that gap? It's a physical gap. How do you jump that gap? You make a high voltage. And you make the high voltage high enough so that what happens?
Works.
Bridge the gap.
You get a spark across it. Yeah, okay.
Okay.
So where do you find this being used to our benefit?
Spark plug.
Engine.
A spark plug. Yes,
Yes.
this is how a spark plug works. You generate magnetic field energy and then you quickly pull the circuit away and make it so the only path that it has to follow is down the wires into your engine.
So
This is how a spark plug works. Okay, so for AC, an inductor is essentially an open circuit until it figures out a way to close the circuit.
Okay.
All right, so capacitors and inductors operate kind of opposite of each other. So we can use this to our benefit. In fact, for a capacitor, we have to bring in a new term. We have to bring in the new term X for reactance. And then we have to bring in another term, which is Z, which is known as impedance. Okay, so when we look at, everybody remember what resistance is? What's resistance?
Measured in ohms.
In ohms,
Resistance
yep.
to DC current.
And it's
To
yes,
electric current.
it's how something reacts to DC current. Okay, so a resistor, a perfectly non-inductive resistor, will have resistance, right? It will also have reactance and impedance. For a resistor, as it turns out, resistance is equal to impedance. And here is why. This is not covered on the exam, but again, it's something that has very profound implications. Okay, so we have two axes here. We have our resistance, and we have our another axis, which is X, which is reactance. The impedance, let's say we have resistance that's this big and reactance that's this big. This is the impedance. You're like, wait a minute. What? How does that work? Well, it turns out that it goes back to phase angles. Resistance and reactance operate in different worlds that are perpendicular to each other on this graph. So if I have a resistance of 3 ohms and a reactance of plus 4 ohms, those are perpendicular to each other, right, on this graph? What is the length of this by the Pythagorean theorem? This makes a 3, 4, 5 right triangle. My reactance, my impedance is now 5 ohms. But I have to also indicate the fact that it's rotating this, that there's an angle involved. Well, that's about 57 degrees.
3, 4, 5 triangle.
It's a 3, 4, 5 right triangle. Pythagorean theorem. So what's important here is to note that my impedance is how something behaves in the presence of alternating current. It is a device's reaction to alternating current. Something that is purely inductive will look like this, an inductor, and it will have an impedance that goes that way. Something that is purely capacitive will actually have an impedance that goes that way.
Oh.
It's actually negative.
Okay.
So, do you think it would be possible, for instance, if I were to take a capacitor and an inductor and do this with it and put them in series? Now, it turns out that these add together. But this one is going to be negative, and this one is going to be positive. Could I pick them so that they're actually opposite each other? And they cancel each other out?
It's like an oscillator or something.
Sure.
Oh, I heard that. I heard that. What was that?
Look like an oscillator or something.
Yeah, okay. Well, what ends up happening is that it turns out that it's not completely accurate to say that one's an open circuit and one's a short circuit and vice versa. What happens is that ZL is equal to 2 times pi, we're dealing with circles, times frequency times inductance. And for a capacitor, it's minus 1 over 2 pi FC. Okay. Well, notice that they're opposite signs. And what is the other thing that shows up in both of them besides the 2 pi? What letter?
F.
There's a frequency.
F.
Which means that if I change the frequency, those values change, don't they? Those overall values change. They are frequency-dependent things. The higher the frequency, the more one thing starts to take over. The lower the frequency, the more that one thing starts to take over. If I were to pick them so that they are equal and opposite, what happens? They disappear.
They cancel.
They disappear and they become a short circuit. Magic. Right? That is magic. And what is the overall? If the resistance is very, very low, what is the overall impedance? 0 plus something very low, which is basically what?
0.
0. So what's important about this is the fact that now I have a graph which is impedance versus frequency, where it starts at 0 and goes to infinity, where the impedance is really, 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 really high, and then all of a sudden I get this.
Drop.
And what happens if a circuit does not resist the flow of a current? It passes right through. But notice it changes for every possible frequency that I could put in. And that is known as resonance. And why is this important?
Oscillators.
You can use this for an oscillator. You can use this for a filter. You can use this for a million different other things.
Just turn on and off a transformer.
Yeah. So this right here is the resonant frequency. This is the analog of you tuning your clarinet. And so here's your clarinet, here's the reed, and here's lots of other things. There's a little bit of a bell at the end. I know it's a little bent, more of a bass clarinet. But let's say that this is your clarinet and you plug a certain number of holes and you have it tuned and it makes a note. Why does it make that note?
Because you blew AC into it.
Well, essentially, yeah, you're causing it to oscillate, and it has a natural resonant frequency based on what you have done as far as closing the holes. When you have chosen a capacitor and an inductor, and you have selected the sizes of those devices, what you have done by comparing the two together is you have selected where that resonant frequency is for that circuit. So now, let's say that instead I do this. This means that it's variable. That is a tuning knob. What can I do with the resonant frequency if I have a tuning knob?
Change the channel.
I can move it here. I can move it here, or here, or here, or here, just by changing one of those things. Why is that important?
Frequency.
Why is that important? Where do we use things like that?
Changing frequency, a tuner on a stereo.
Tuner on a TV, tuner on a stereo, tuner on anything that is an electric device that receives or transmits a circuit. At the heart of this is this. The other reason that we would do this is because when we take our two devices and we run them through a transistor, which we're about to get to, we can selectively pick a frequency. We want to make a frequency that looks like this at 9.141625 megahertz because we've designed our circuitry to be able to mix things and filter things at that frequency. We can pick those two devices so that they have a resonant frequency at exactly that. It's really cool stuff. This is the basis of all of it. Resonant circuits are how we are able to change frequencies. We're able to selectively pick certain frequencies. Okay. So anyway, that's known as resonance. The other place that it shows up, we're going to see it everywhere. It shows up in antennas, shows up all over the place. And now we're going to move to another thing. Anyone know what this is called?
Transistor.
That is a transistor. And in particular, this is known as a bipolar junction transistor. The reason that a transistor exists is because of this thing called semiconductors, typically silicon. And what you do with this is you have three terminals. This is known as the collector. This is the base, and this is the emitter. And if I were just to look at the bottom part of this, what does that look like? That is a diode.
Diode.
Okay. So what do you know? What did we discuss about a diode? It conducts energy. It conducts current in the forward direction, right? Okay. So that means if it tries to go backwards, it won't work. So it conducts energy in the forward direction. A transistor is a very special application of a diode, where if I get current to move in this direction, let's say one unit, what I'll call little letter I, little current, I will get a multiple of that current on the order of, let's say, 200 times.
Gain.
Right? And that would be known as gain. And that is known as the beta of the transistor. And what is the point of being able to do something like that? Why would you want to make a 200 times bigger copy of something ever?
Countless
Which?
Countless things.
Amplification. You want to make a big copy of something. So when you are amplifying something, you are not making it bigger. You are making a bigger copy of it. Okay, so that's a bipolar junction transistor. It is made of, usually, as we've drawn, N, P, and N materials. These are just like in a diode. You have silicon that's doped with another element that makes it a little more negative, a little more positive, a little more negative. That basically opens up a gate that allows it to flow this way, and that allows it to flow that way in a much bigger way. There's another kind of transistor that we can build, which does largely the same thing, but what I'm going to ask is, why would we pick one over the other? And you will maybe see in a minute. Okay, so here we go with our other transistor. This is known as a FET, or a field effect transistor. Now, this is something called the gate, and this is the source, and this is the drain. So, when I apply a voltage here, across from here to here, I get a proportional current that flows through the transistor.
Big switch.
Yeah, okay, but it's also linear. The question is, why would I choose one over the other? And think about efficiency. What do I have to do in order to get this transistor to work? What do I have to dump through it?
Oh, current.
I have to put current in it, and current does what?
That you just need a voltage drop.
Current makes heat. How about with this? I just need a voltage to exist, because what is this? We just drew it a minute ago.
Junction.
What does that look like to everybody?
It's a capacitor.
Looks like a capacitor, doesn't it? Okay, all I have to have is a voltage between the two plates, and my transistor will work. Well, if I have a voltage between two plates and I don't let any current leak through, I don't waste any power. This is what we use in microprocessors.
Or motor speed controls and all kinds of stuff.
Because they're a lot more efficient. They don't get hot. Anytime you use power, you make heat. The fact that you have 2 billion transistors on your integrated circuit in the computer that you're using right now. I did say 2 billion transistors. If each of them made a millionth of a watt times 2 billion, your computer would melt. Right? And that's why we don't do that. However, a field effect transistor, the efficiencies are really high because they don't waste power. They don't get really hot. They still get warm, but they don't get hot. Okay, so gate, drain, and source, that's known as a field effect transistor. Okay, so now we're going to talk about how these things look when we actually use them. Okay, so we have our input and our output. So when we change our input, that is supposed to make a change on the output. Ideally, the output is going to be 100 to 200 times bigger than the input. If we get a very small change on the input, we expect a very big change on the output, don't we? So really, I need to redraw this graph. In fact, it actually looks like this, if they were on the same scale. But that's not easy to draw. So what I'm going to do is I'm just going to stretch this axis out so that we can actually make sense of it. Okay, so here's our input and there's our output. Up to a certain point, the input doesn't really do anything. It doesn't create any change in the output. And then all of a sudden, it starts to come up, and then for a while, it stays in a basically straight line. But then you get to a point where you keep dumping stuff in and making the input signal bigger and bigger, and eventually you get to the point of no returns. No, completely diminishing returns, where you can dump 10 times as much input in and you don't get any change in the output. You've essentially exhausted the transistor's ability to do anything useful. There are 3 regions of operation. This is known as the linear region. What does linear mean? What does the word linear come from, everyone?
In a line.
In a line. Okay. So if I have a proportional change here, I would expect a bigger proportional change here. And in fact, that is what happens. That this is in the linear region, I get a nice even proportion. That in this entire region, any change of the same size generates a similar change in the output. However, down below, this is known as the cutoff region, where the transistor when I turn it on, it doesn't really do any good, right? At least not until it gets to a certain point. And up here, oddly enough, this is called saturation because I've now completely saturated it. No matter how much more I dump in, nothing happens. So these are the three regions of operation of a transistor, or any amplifier for that matter. Vacuum tubes also. So we use these different regions for different things. Oops. Okay, the linear region we use for linear amplification, such as who has that nice audio amp?
Oh yes.
Okay, we want to be able to make a larger copy of somebody's voice. We don't want it to be distorted. If at some point we managed to get into this region, when it got higher than a certain point, we would be distorting the voice that was coming out of it. So the linear amplification is where we do amplification. That's what we usually think of as an amplifier. However, let's say that we were doing a digital computer. What realm do digital computers work in? 0 and 1. 0 is off and 1 is on. All right, so if we have off and on, and that's all we have, why would we want something that says, oh, we're 50%? Well, that would just be confusing, right? I mean, when we look at it like we're at 70%. Well, all we care about is off or on, so these values don't mean anything to us. And in fact, they just make things worse. So when we're dealing with digital circuitry, our 1 translates to operation in here, in the cutoff region. And our on, which is our 0 is cutoff, and our 1 is saturation. And we ignore the section in the middle. So the cutoff and the saturation, this is our digital use. So this is where we use our transistors for storing digital data, 0s and 1s. This, linear amplification, this is used for analog purposes. So there you go. Questions about that before we move? Questions? No? Everybody totally gets it?
So,
Maybe not completely?
couple more run-throughs.
Okay. All right, so now we're going to move into a couple of practical circuits. Here we go, practical circuit. All right, we're going to start with this.
Coil.
What is this?
Transformer.
Okay, why would we use a transformer? So let's say we have 100 volts AC on this side. We have 100 turns of coil on a piece of steel that goes through both of the coils. On this side of the coil, on this side of it, we have 10 turns of wire.
Step down transformer.
We will get 10 volts AC. Can anybody see a practical reason for doing that? Anyone live in a neighborhood?
Yep.
Can anyone think of any practical reasons for doing that?
Bring down line voltage.
Yeah,
Transmission voltages are much higher than what we use.
Right. So outside on your power pole, you've got 12,800 volts. And you want to bring that down to, let's say, 120 volts or 240 volts. How would you do that? You'd run it through a transformer that had a turns ratio that was appropriate to transform 12,800 down to 240. Now, one interesting thing about this is that if, let's say, I had a device, we'll call it a load. Here's my load. that were consuming 500 watts at 10 volts, what would my current be?
50 amps.
Yeah, what
on
do
the
we
right
use?
side.
What do we use to calculate this? Everybody?
Ohm's law.
Ohm's law for power. P equals I times E. We don't know the current, which is then 500 for power divided by 10 volts is 50 amps. That's some pretty fat wire, isn't it, to handle 50 amps? This is actually like number 6 wire. Some pretty big wire. Heavy gauge. Okay, so why would we not want to hook that up all the way to the power lines and have them deliver power at that 10 volts?
Because if the line gets broken, you're going to be
I'm pointing to it right here.
50 amps.
50 amps. What's Ohm's law?
Equals I times R.
E equals I times R. If I have 50 amps and my resistance in my wire is not 0, I'm going to drop some of my voltage just in the wire.
Yep.
And if I drop the voltage in the wire, what's the other part of Ohm's law?
The wattage power.
P equals I times E. I'm going to drop a ton of power in that wire, which means how much power is left for my load?
Not so much.
Almost nothing, right? Depending on how heavily loaded that wire is. That's why we don't like to run high currents and low voltages whenever possible. Higher voltages, if you can make them safe, are a lot easier to work with because they don't have a lot of losses. The power company. So let's go to the other side of this. If we have 500 watts here, because we're assuming 100% efficiency. At 100 volts, we're only drawing 5 amps. Which one do you think the power company would be happier delivering, 50 amps or 5 amps?
5 amps.
5 amps, because they can deliver more power to more people at higher voltage. And they just they're just pushing 5 amps. What if they could do it at 1,000 volts? Then it'd be 0.5 amps. What if they could do it at 10,000 volts? Ohm's law definitely favors that, doesn't it? Because it still follows the rules that say that E equals I times R, and if our current is really low, our voltage drop is really low, and P equals I times E, which means that our power loss is very low, which means they don't have to use really big wires. Big wires cost a lot of money. Copper's really expensive.
Then you burn down force.
Yeah, exactly. So that's why that's why transformers are so useful. So the next thing about transformers is that if we have a transformer that looks like this, and we can prove that this is true if we really want to, but let's say this is hooked up to an impedance is 10 ohms. And we have a ratio of, let's say, 10 turns to 100 turns. Well, we have over here, we have high voltage and low current. And over here, we have low voltage and high current. Okay. And it's actually 10 times. So over here we have voltage, and we have 1/10 of the voltage over here, and we have current over here, and we have 10 times the current over here. Okay, so what's the impedance or resistance here? What law do we go back to?
Ohm's law.
Ohm's
10
law.
times as I.
Yeah, okay. Well, no, it's not 10 times. R is
Oh.
equal to E divided by I. We'll just use the letter, we'll use the letter V. V divided by I. How about on this other side? This is my voltage, and this is my current. Use the same Ohm's law. R is equal to 1/10 of voltage divided by 10 times the current. V over I is the same as R. We have 1/100th of the resistance. Well, that's pretty trippy, isn't it? Because that means that we see a value R over here, and over here it's really only 1/100th of R. Which means that if we have 1 ohm over here, we will see 100 ohms over here. Just looking in, if we didn't know what was on the other side, we would see 100 ohms. So this is important because let's say we have an antenna. This is the first time we've mentioned antennas, isn't it?
Yeah.
Okay, let's say we have an antenna with an impedance of 2,500 ohms. And we have a feed line that is 50 ohms. Ideally, these are going to be the same to get power to get maximum power transfer from one point to the other. We're trying to transfer power this way up into an antenna so it can radiate into space. This is a problem, isn't it? Right here. That is a big problem.
Yeah.
What is our ratio of output to input, roughly?
1 to 5.
Yeah.
1 to
500.
Yeah, 20. It's about 50 to 1. Well, okay, but we just said that for a transformer, a 10 times ratio gives you 100 times resistance or impedance change. So if we put this into a transformer that looks like this, and we have a value of 7 over here, or let's say 700 turns, and 100 turns over here, that's a 7 to 1 ratio. What's 7 squared?
49.
49. Well, guess what? Guess what you can go out and buy? You can also wind one yourself. This is used for matching high impedance to low impedance. We also use this for, if anyone has ever seen something that looks like this, that goes over your ears.
No.
Pair of headphones.
Oh.
That these will now connect to a stereo system or something. And these will be rated like 600 ohms impedance, and the stereo is rated at 8 ohms impedance. How do you match those? Well, 600 divided by 70, but divided by 8 is 75. Square root of 75 is about 8.5. So 850 to 100 turns ratio. That gives you an impedance match so you can use one thing with another thing. And what is the base of all of this? The humble inductor. The humble inductor is the basis of all of that. So, okay, so you're probably saying, why am I torturing you with all this stuff, right? Right? Are you saying that yet? Why am I torturing you with all this stuff? Okay, so what we're going to do is now draw another practical circuit which we use all over the place. Okay, so what's this thing called again?
Transformer.
A transformer. Okay, so let's say it's 120 and 12 volts. These are volts AC. A transformer does not work on DC ever. Okay, so what would the turns ratio need to be to get that voltage change?
It's 10 to 1.
10 to 1, very good. Okay, so we have 12 volts AC on this side because it doesn't work with DC. Okay, and now we're going to run this through something that looks like this.
Diode.
That's a diode. Okay. So this is a sine wave. What does it look like coming out of the diode?
Like pulsating DC.
Inverse.
Pulsating DC. Right? It's not correcting it. It's only half wave rectified. Okay, so now we're going to take this and run this instead through a capacitor.
Smoothing filter.
So what's the capacitor going to do? The capacitor is going to charge up, and then when this goes away, what's the capacitor going to do?
Discharge.
It's going to do this and discharge, but not completely. So what does that look like?
Smoother.
Smoother DC. Okay, so what is the capacitor acting as?
Shock absorber.
A filter. Yeah, the capacitor now is making our voltage look like this. Okay, and now we're going to run this through another device that looks like this.
Zener diode.
That's a Zener diode. This is a special diode that actually likes to be run backwards.
So limiting.
And what happens is it is designed so that, yes, it'll work forward, but it also likes to run backwards. It has a breakdown voltage of, let's say, 5 volts DC. So that anything above 5 volts DC just causes it to carry more current. So we might do a little bit of this to protect it, a little bit of this to protect it. And what ends up happening here is that this generates a voltage reference. And let's say that our peaks over here are 12 volts and our valleys are at 6 volts. What happens if we now say anything above 5 is going to just disappear?
It'll be 6 minus 6, so 0.
We end up with 6 minus 5.
Oh, was that
right?
okay.
Except that it's not really. It just burns off that extra volt. So here's our Zener diode in pink, and this is what comes out of it.
It's like a voltage regulator.
What does that look like?
DC.
That looks like DC, and it's at 5 volts DC. What do we use 5 volts DC for?
Everything. Yeah.
So what did we start with over here on the left?
120 volts.
Volts AC, and what did we end up with on the right-hand side?
5 volts DC.
5 volts.
5 volts DC, which we can use to do what?
Charge your phone.
Charge your phone. Yeah. This is a very basic cell phone charger.
Damn.
And what's it made out of? A transformer.
Copper.
A transformer, a diode,
And a filter.
a filter capacitor, and on the right is a Zener diode, which provides the voltage reference. Just a completely basic circuit, really 4 or 5 components. When next time you look at your little wall wart for charging your phone or your iPad and you plug it in, that's basically what's in it. Now, it could also be that it's even less than that because a lot of that can be done on a circuit board and built into an integrated circuit. So it's quite likely that the diode and the capacitor and the Zener diode and any resistance are actually all built into a single chip. That's just soldered to a circuit board. Pretty cool stuff, if you ask me. So, can I break down why you need to? Oh, you don't need to know why. That is a good question. But you do need to know. All right, so this is a good question. Okay. It's a good time to talk about it. Okay, let me close that. All right, this is a good time to talk about that because we've now done capacitors and inductors, and we've done a little bit of units. We haven't done decibels, but we haven't also moved into antennas yet. Okay, so let us talk about what amateur radio isn't and what amateur radio is. All right, let's hear what you all think. Things that amateur radio isn't.
Oh.
Not broadcasting.
It's not broadcast. You can't make any money. Okay, good.
Yeah, it's not a means. That can't be used by businesses to communicate with businesses.
Right? It can't be used for business. Other
So
things that it's not.
Private or encrypted?
It can't be encrypted unless you're controlling a satellite or a remote control craft. Yep. So you can't hide anything. We also don't pay for it. All right. Other things that it's not.
Not private.
Certainly not private. Okay.
I have a question on the encryption when I was reading that earlier, because a lot of these handhelds come with scramblers.
Yep. So you can, well, a scrambler is only a scrambler if, okay, so you can encrypt something so long as the decryption algorithm is well known.
Oh.
Okay.
Now, really, actually, the rules say you cannot do anything to obscure the meaning of a message. That's the technical, the technical stuff from the rules. That means you can't speak in code if no one else knows the code. That is not permissible. That could be plain English, but you're not allowed to obscure the meaning of the message. So if everybody knows what the code is, then you're fine. If no one else except for one other person knows what it is, then you're not allowed to do it.
So we could talk in Pig Latin?
Sure. Yeah, I mean, Pig Latin's a well-known thing. I can speak in Spanish. However, if my friend and I created a language that was based on English where words meant other things than they do, that would not be okay.
Okay. What about slang?
If everybody knows it, it's fine.
Mm-hmm.
Like, I've had a conversation with somebody where I'd say, oh, that's pretty sus. There's a lot of people who don't know what that means. I was ashamed to say it, but I said it anyway. That's pretty sus. So that's fine, so long as it's well known. So, okay, other things that ham radio is not.
You can't talk politics.
Actually, you can. It's just recommended that you don't.
Oh, that's good.
You don't really want to talk. Okay, you really don't want to talk politics or religion. You really don't. You're not allowed to curse. You have the same rules as anything over the air, so you're not allowed to be profane.
It's not 100% of the time available to talk to somebody or get to somebody anywhere.
That's right. That's true. Okay, but now let's talk about. And the other thing is that ham radio is not what we would call an appliance user service. Does anyone know what I mean by that? Okay, think about what an appliance is.
Your phone.
Think about a bigger appliance. Refrigerator. Do you have to know what's inside your refrigerator in order to use it?
No.
Do you have to even care? Not really,
but it
right?
is nice to know how to get a leak from the freezer.
Yeah,
fixed.
right. But you don't have to in order to be okay to use it. You don't have to understand everything about how your car works in order to drive a car, right? Now, so what is amateur radio? Think about all the things that it is. And there's really a couple of things that make it distinctly different, which answers the question, why do I have to know this crap?
Well, for a way to share skills.
Experimentation.
Okay,
You wouldn't be on a cell phone plan.
I heard experimentation. What was that about a cell phone plan?
You don't have to be on a cell phone plan.
Yeah, but that all goes into part of it.
I mean,
Ways
to
communicate.
Charged by the month for that.
Fundamental in nature, other things.
Public service.
Public service. I mean, you can do public service with GMRS. GMRS is an appliance user service. It is. You have 22 channels or 38 channels or whatever it is. I think it's 22. And you pick a channel. Are you allowed to go to channel 18 and a half?
When there's a natural disaster, you have a way of communicating.
Yeah, but you have that with GMRS also. You have that with cell phones if they keep working.
But those towers don't always work when
Oh,
you
that's
have.
true. But GMRS will from point to point. Other things that amateur radio is.
Could be a hobby.
Yeah, it can
It's
be a hobby.
proprietary. You have to have a license.
You have to, yes, okay. But now we're getting closer to it. You have to have a license. The question is, why do you have to have a license?
I'm thinking it's because there's an unlimited spectrum of potential points to communicate on.
It's not really unlimited. I mean, you looked at what Kent showed us, and it's not unlimited. It's big.
Well,
That's
wide.
part of it.
You can also injure.
It's regulated by the FCC.
So is GMRS. Ideally, I mean, they decide what's legal and what's not. They decide what equipment is legal and what's not.
You're allowed to build the equipment.
There you go.
Oh.
What do you say?
Go ahead, say it again.
You're actually allowed to build the radios and the antennas and all the things that you broadcast on.
That is exactly it. That is exactly right. Okay. Now, so here's my GMRS handheld, right? Okay, we're going to put a bunch of buttons, and here's my antenna. Okay, now I can take this radio and I can hook this up to a bigger antenna up to a certain point. We are allowed to run 50 watts. Everything is very tightly regulated by the FCC as far as the fact that you can go from channels 1 to 22. You have a very tight spectrum. Are you allowed to go to channel 18 and a half?
No.
You are not.
No.
No. Could you go into the radio and modify it so that you can run on channel 18 and a half? Not legally. No. Okay, because it's a channelized service. Are you allowed to build your own GMRS radio?
Yes.
No.
No.
Because it would have to be type accepted. It would have to be type accepted by the FCC. And that can cost tens of thousands of dollars, and nobody's going to do that. Okay? However, if you let's say want to build let's say you go out and you buy you buy a radio, 2-meter radio. So here's your 2-meter radio that runs 10 watts, right? It has a small antenna. You want to replace that antenna with an antenna that looks like this, up on your roof. With an amateur radio, are you allowed to do that?
Yes.
Yes. Okay. Let's say that you decide 10 watts isn't enough, and you want to take this system and you want to buy an amplifier that takes 10 watts in and puts out 1,000 watts. Are you allowed to do that?
I don't think so.
Oh, yeah, you are. The legal limit for most operation is 1,500 watts on the amateur bands.
Are you talking about building onto this?
Yeah.
With this?
You can do anything you want. So, okay, let's move on to, let's say that instead of that antenna, which had, let's say, 2 dB of gain. We're going to get to decibels very shortly. 2 dB of gain. I want to replace this antenna with a different antenna. I want to take my 1,000-watt amplifier, and I want to hook it up to an antenna that is 8 feet wide and looks like this. You may recognize this. Which I want to use to point up at the moon. And this has a forward gain of 30 dB. Am I allowed to do that? Yes or no?
Yes.
Yes.
Yes. Okay. Now, in doing so, let's say that I decide that I don't really like this 10-watt transmitter anymore, and I want to build something that will run 8 watts, but it will be my own design. Am I allowed to do that?
Yes.
Yes, you are. What you have to do in order to do that is show that at certain frequencies your spectral, your harmonic content and spurious emissions are at least minus 40 dB down, or minus 50 dB down, or minus 60 dB down from the fundamental frequency.
Scott, I need to ask this question. What in your diagram is the thing in the antenna that looks like a lampshade? I couldn't hear the word.
That's a microwave dish.
Thank you.
That's like an old satellite TV dish. Are you allowed to repurpose one? Sure. You can do anything you want. Okay, so When you go and you buy a piece of equipment, let's say a GMRS radio, right? All of this is already done. By virtue of the type acceptance, they've taken that design and they've run it through the test equipment and verified that it already meets all those things. But what are we allowed to do? We want to build that radio. We can build our own stuff. The assumption is that in doing so, we are going to not only understand but be able to implement all of those things, those technical things that allow us to coexist with all those other services that we showed you on that diagram without causing interference to anybody else and without causing interference to anyone who's on in those other services. Here's another part of this. If I go through and I run if I have an 8-watt transmitter and I amplify that up to 1,000 watts, at, let's say I'm doing moon bounce at 1.296 gigahertz, which is the frequency one of the frequencies that you could do that on. And I have a 1,000-watt amplifier and I have a 30 decibels of gain. All right, 30 dB of gain is 1,000 times 1,000 watts is an affected radiated power of 1 megawatt at 1.3 gigahertz. If I did something wrong and this was pointed at my neighbor's house, do you think I could have hurt somebody?
Yeah.
Okay.
So you'd be interfering with their reception.
Well, they're not going to be on that frequency. But at this frequency, you can cause some serious bodily harm. Is what you're doing
like a microwave.
Like a microwave oven. Yeah. Is what you're doing legal?
No.
No. Is your setup legal?
Yes.
It is how you apply that setup. Okay, so I believe the question was, let me unshare that. I believe, Talisha, does that make sense? As to why you have to go through this entire process? Why is this actually important? I think I lost you.
I think it's important to understand how, microwaves and radio waves and everything work, and how it's all interconnected. But I was hoping to start learning about, the FCC and
we're getting to that.
What to expect on the test and all the other stuff. And so I
We're
kind of feel
getting to
maybe
that.
behind schedule.
No, we're getting to that.
With much power comes much responsibility.
Yes, that's exactly right. And amateur radio started over 115 years ago? Ham radio operators were the ones who experimented with literally everything. That is how we have this thing today that allows us to actually build our own stuff. The rules have not changed appreciably to the point where we can't build our own things. You want to build an amplifier? Okay, you want to go source a 3,000 watt, a 3,000 volt transformer to run your amplifier? You want to wind it yourself? Okay, you can build all this yourself. Does it mean that you will?
No.
It does not. But the license gives you, even a technician class license, gives you permission to do any of that. And if you choose to, you can. If you don't choose to, the FCC is not looking to see whether or not you are going to or not. There are other services for which those are, that's what GMRS is for. That's what Citizens Band is for. It's for people who just want to use a radio. But amateur radio is and always has been different. It is for people who, even if you don't choose to do anything else, you still have the ability to. And because you have the ability to, you at least have to go through and prove a certain degree of technical competency so that, number one, you don't interfere with anyone. Really, this is what it comes down to. Number one, you don't interfere with anyone. And number two, you don't kill anyone, including yourself.
Yeah. Makes sense.
I mean, that's really fundamentally what the exam is for. You know, having this knowledge and being able to understand what it is that you will keep you from hurting yourself or killing somebody else or causing bodily harm
That's
is a
called
really big part of this.
responsibility. That's
Yeah,
called being responsible.
that's right. So yeah, so I think that was actually a really good question to ask at that question. And really what it comes down to is the license, the FCC issuing the license, they don't care if you're not going to do it, right? By virtue of going through this license and passing this exam, you have the ability to do all these things, right? Even a technician class license, a quote entry level license, has an immense number of of openings for you to try. I mean, you want to do moon bounce, right? That satellite dish that I drew. There are people who do that all the time. They
Well, I
will.
looked at the test bank and none of them really asked questions about building a radio.
No, but you do know. But a big part of it is the fact that you have to understand what decibels are, and you have to understand what power levels are, and this really comes down to understanding what it is that makes a radio system function and radio system safe. How
Well,
not
I
to
think
how not to interfere and how not to kill anyone.
I think that it also has to do with if we have a natural disaster, like say a flooding, and we're trying to reach our family members, and part of the radio equipment is shot from the water, but you have other parts that you can add to. You can do that to get.
Well, you
Am I right
can.
on that, or
Yeah, well, but that's not the fundamental reason. That is actually, and I think, um, give me 1 second. Part 97 rules. I'm going to open up the FCC Part 97 rules right here, and these are the things that indicate why we are allowed to exist. And I guess we will see if what you say is correct. Okay, here we go. Notice this: basis and purpose. These are the 5 things in the very first paragraph of the FCC rules that indicate why amateur radio is even allowed to exist in a world where everybody else has to pay big money for all of those things that they're permitted to do. Recognition of the amateur service to the public as a voluntary non-commercial service, especially with regard to emergency communications. Okay, so that's number 1 right there. There's your emergency communications. We're going to help the public when need be, right? We have to give something back. Continuation and extension of the amateur's proven ability to contribute to the advancement of the radio art. Single sideband exists because a bunch of hams were interested in doing it. There are a lot of other operating modes that exist because hams were interested in doing it. There's no commercial reason to spend money on a lot of things that end up in commercial use. And vice versa. There's a lot of commercial changes that make their way into amateur radio that make our service better. Encouragement and improvement of the amateur service through rules which provide for advancing skills in the communication and technical phases of the art. This works well with expansion of the existing reservoir within the amateur service of trained operators, technicians, and electronics experts. I would say that if you understand what are in the rules and what's on this class, if you know how to at least look at a schematic and not say, I don't know what that is, or to understand what a piece of coaxial cable is and why it works the way it does, I'd say that makes you more of an electronics expert than the person sitting next to you. And finally, goodwill, international goodwill, right? We're non-political, we're apolitical. We are allowed to communicate with other people from other countries independent of what our governments think of each other, for the most part. So, I don't know. Does that kind of answer the question? I think it answers. I think it fits in well with what you said. So where does that fit into helping out and being able to contact your relatives? Specifically, contacting your relatives is not in there, but helping the public is. Because there are other ways to contact your relatives. Now, how is it different from FM or AM? Oh boy. Okay. Well, we're going to get into that. Not yet, though. Okay. So we did transistors, we did some schematics, resonant and tuned circuits. Okay, the most common place that you will find a tuned circuit is right here. Let's see. Okay, here we go. I will show this. I will share this right now. Okay, and okay, let's see. All right, so what does everybody see in that picture?
Oh, variable capacitors coil.
Yeah, okay, so those things on the right of that box, those are air variable capacitors. You basically vary the amount of plate that's meshing. That changes the value of the capacitance. Okay, how about that big coil in the center? Does anyone see an inductor?
Yep.
Anybody see a whole bunch of wires hanging off the inductor to the right?
Yep.
Yep.
Those are taps. There's a switch on the outside that allows you to short out a certain amount of that inductor, thereby changing the inductance. What would be the purpose of something like that?
Specific frequencies.
Yeah.
Pick certain impedances and
You got
frequencies.
you got a tuned circuit between the coil and the capacitors.
Yep.
And you can have all kinds of different values for that resonance.
How about that big black thing at the bottom?
Resistor? What is it?
That is a big resistor. Why would a resistor be that big?
Output?
No, why would you want to pick a resistor that big?
Well, you got a lot of power.
You got a lot of power. That is a power dissipating resistor. It's speaking specifically for it's looking specifically at not all this other stuff. It's so dated. This is an electronics thing. This is amateur radio. Okay, so let's see.
Isn't that the output part of the circuit?
No, actually. Okay, so the way this works is that you have something that looks like this. Tanisha, you got to run before you can. You got to crawl before you can run. Or Talisha, sorry, you got to crawl before you can run. And people do use the internet to talk on amateur radio. How does that work? There's a lot of hybridization that exists, but fundamentally it's still radio. If you don't understand the radio portion, you don't get any of it. Okay, so let's say that we have a resistor here, and let's say this is a 300 watt resistor. And so here's your circuit. So here's your antenna. And here's your transmitter, and here's your antenna. So, these are all variable. That's what that arrow across it means. Now, instead of the antenna, I could actually do this and use my 300 watt 50 ohm resistor and eliminate the antenna. The reason for that would be that I know that this is a 50 ohm load, which is what I am aiming for all of my equipment. That is a standard impedance of coaxial cable. Yeah, this is a dummy load. Now, importantly, a dummy load is a non-inductive wire wound resistor. Non-inductive wire wound resistor. So that being said, why would it be so important to have it be non-inductive?
You use it as a test.
It's not involved with frequency.
Because it's frequency independent, exactly. So you have 50 ohms resistive and because if it were inductive, depending on the frequency, you'd be either this big or this big or this big, and then your triangle would look like that, or your triangle would look like that, or your triangle would look like that, and those are not 50 ohms anymore. So in order to keep that from happening, you use a non-inductive resistor. It's still wire, but the wire internally looks like this. It never completes a full loop. Because it never completes a full loop, it has no appreciable inductance. Okay. Moving right along. I think we are now into antennas, and let's see, we did integrated circuits, we didn't do meters, but a meter is a way of showing a value. Okay, so I think it's time for a 5-minute break. Everybody stretch and go to the bathroom, etc., etc., etc. All right. I know we've got questions. I know people have questions.
Flip your mic down.
Oh, good answer. I know people have questions. I have built a transmitter from a kit. Actually, a couple of them. And you know what you learn when you're building something?
What you don't know.
You learn what you don't know, and you learn how to debug it and fix it and make it work right. You also learn who your friends are who can help you.
To do.
You also learn how to not to do things.
Well, yeah.
Okay, so I have a question.
Yep.
And that is, even though I read the material, all of it is so foreign to me that I got lost sometime this morning. And what I am hoping for is that with the recording, it's something that I can go back and cover and cover and cover the material again until I start understanding or start grasping it enough to even take the test.
Go look at the book. Look through the
Okay,
book
just keep reading the book.
Well, the book is basically. Let me share the book.
Well, I got it. I printed it out.
I just wanted to bring it up. Basically, most of the examples that I gave,
yeah,
are right from the book or have analogs to the book. Like, okay, if I ask what electrical component stores energy in an electric field, you know the answer from these?
Yep. Capacitor.
Yeah.
Capacitor. We covered that, right?
But it's, I guess for me, what it is that everything is so foreign that it is rote memorization. And
that is fine.
That is not something I am good at.
But that is fine. It is okay to do that.
Right, but that's why it takes me so long, because that is not a strong suit of mine. Whereas, it's like being at the beginning of something that when you don't know what you don't know, you can't ask. And after a while, you get to a point where you can finally start asking questions. Well, I'm at the front end of that.
Kind of like when I went to Chile for the first time and didn't speak a lick of Spanish.
Yeah.
And I'm like, I'm completely lost. The next time I went, I had done about 3 months of studying and listening to Spanish language news and listening to baseball games and speaking and practicing with a few people. And at least I knew enough to know what I didn't know and could ask.
Right. And so to me, for somebody who is, this is so foreign, is that even in the literature, in the book, because I've been through that there are so many assumptions of leaps that I can take that I'm not able to do, that are there other places that fill in the gaps, or because one of the things that my real question is, you're recording today. Is that recording, will that be available to us?
Yes.
Okay. That's the bottom line.
Yeah, this evening.
You go, I think you're an excellent instructor.
It's a lot of material.
And well,
trust me, there's a lot of material.
So I'll just stop taking up time, but thank you.
Yeah, there's a lot of material, and that, I tried to warn everyone there's a lot of material.
Right.
And but at the same time, I think if you were to take a practice exam, let's say having taken a practice exam before starting today and going back and taking a practice exam after, you will do better. I mean, just by having even heard the words at all, you will do better.
Well, and that's why I continue to watch rather than bailing.
Yeah,
because
right.
Just showing up and listening to everything, that's a great place to start.
Well, and you are not expected to be an expert at any of this stuff at any point. You're expected to learn enough to pass the exam. And then if you hang out with some people if you hang out with people and you do things and you are active, all this stuff will start to make more sense. And you'll be able to say, okay, well, what cable do I use for this? Why would I use this cable? Why would I do this? Why would I do this? And the answer will not necessarily be obvious, but at least you'll be able to have a reference point to say, oh, I know where to start, and this is why.
Right. And that's, yeah, I understand that. And I hang out with some ham people, and there are reasons why I am here.
Yeah,
So,
no, I'm sure. So, all right, well, what does my shirt say? It says, if ham radio was a sport, I'd be a jock. Yeah. All right, so we are into numbers, okay, and powers of 10 and how that feeds into decibels. Somebody wanted to hear decibels. Okay, so we represent things like 3 times 10 to the 8th meters per second, right? I could write that out, 300 million. That is a lot of zeros. Zeros don't really do anything for us except fill up space. The number 10 is very important, right? Because it represents an order of magnitude of something, but there has to be a better way to represent it. So 300 million, we count 1, 2, 3, 4, 5, 6, 7, 8 times. Okay. So that's 3 times 10 to the 8th power, which is the same as 3 times 10 times 10 times 10, 8 of them, and then we get our answer. So we have another form of shorthand. We have all of our shorthands, which say 10 to the 3rd power is a kilo, little letter K. 10 to the 6th power is mega. 10 to the 9th power is giga. And 10 to the 12th power is tera. And then going smaller, 10 to the minus 3rd. By convention, when you go negative, that means that you're moving your decimal point the other way. You're moving it towards something smaller. So let's say that I have like 5 times 10 to the minus 3rd, or 0.005. Well, I could go 1, 2, 3. Now I get a 5, and I absorbed 3 decimal points. That means 10 to the minus 3rd, or 1/10 times 1/10 times 1/10. They're the same thing. That would also be little letter m for milli. 10 to the minus 6th is micro. 10 to the minus 9th is nano. And then to the minus 12th is pico. And we're not going to go any further than that because we don't really have to. So one of the important things about this, however, is that we are dealing in powers of 10, which are base and exponent, right? The base is always 10, and the exponent is the number up above to which 10 is raised. This does not have to be an integer. This can be 10 to the 4.6. It could be 10 to the negative 3.9. It does not have to be an integer. So the way that decibels work is taking all of these mathematical constructs that we have with all the 10 to the minus 12th and 10 to the minus 9th, etc., etc. Alexander Graham Bell came up with a way of trying to simplify big numbers. So he created this thing called the bell. And it's the log base 10 of something. Some ratio, which basically means you have a starting point and you have an ending point. It looked to demonstrate what the difference was between the starting point and the ending point. What did you have to do to it to get to the end? Now, a simple ratio, we could say we started at 1 and we ended at 372. How did we get from 1 to 372 by multiplication? We multiplied by 372. Everyone agree with that?
Yes.
Okay. Now, let's say that we wanted to get to 372,946. All right? That's a lot more stuff. Now, could we approximate this by saying it's 380,000? Yeah, probably. Could we approximate by saying it's 400,000? Yeah, approximately. What the bell gave us the ability to do is come up with orders of magnitude of things. How much bigger something is than something else, more or less, without going to those exact numbers. So let's say that we have something that is, notice the convenience of base 10. It is important to write down what is 10 to the first power.
10.
That's 10. What's 10 to the 0 power?
0.
No, it's not 0. It's 1.
1.
And 10 to the minus 1?
1/10.
1/10. All right, those are the three fundamental things that are important. So if we want to look at the log base 10 of 1,000, this is the inverse of the exponent. So this basically says, to what power did 10 have to be raised to get 1,000?
3.
That would be 3. So log base 10 of 1,000 is 3. We could also go the other way and say log base 10 of 1,000th. It always has to be positive. Can't be a negative number. The end result, though, is negative 3 because it's 10 to the minus third power. Agree with that?
Yes.
Okay. All right. So, and this one is 10 to the third is 1,000. Okay, so it's basically taking a logarithm, which is an inverse of an exponent. Okay, so now we have this. Log base 10 of, let's say, 1/2. So that means that 10 to the something is 1/2. This is where you just have to accept the fact that you don't have your calculator out there. Right? This actually is negative 0.3 approximately. So log base 10 of that would be minus 0.3. Well, as it turns out, again, that was something called a bell. And Alexander Graham Bell was not dealing with all this big stuff, big numbers and things like that. And it turned out that the bell was just too small of a number, 0.3. So it was decided that the bell was too small, and they created something called a decibel. And a deci means 1/10. So a dB is 10 times whatever that bell was. 10 times log base 10 of the ratio. So this basically takes it and just makes that value 10 times bigger. So let's say I start at a value of 1 and I go up to 2. Okay, so this is my start point and this is my end point. Okay, so that would be 10 log base 10 of end point divided by the starting point would be 2. Well, we already said that log base 10 of 1/2 is minus 3 minus 0.3. So it also turns out that log base 10 of 2 is 0.3 with a positive. So this is 0.3 roughly. 10 times that is 3 dB. So what that means is that if we double something, that translates to 3 dB. All right. So if we double something, that means we go up by a factor of 3 decibels. Okay. So that also means that if we cut something by a factor of 1/2 and we go from 2 to 1, that actually turns into minus 3 dB. Because these are really just exponents. If we're multiplying, that means we actually just add the exponents together. So 10 to the 6th times 10 to the 3rd, we'll just do a little demonstration. What is that equal to?
10 to the 18th.
10 to the 9th.
Oh, we add them.
You add them. So in decibels, when we multiply those things, we get 6 plus 3 is 9. We just add our decibels together because we're just working on the exponents, which is an incredibly powerful and very easy thing to do. So what happens now is, let's say we have a system where we start out with a value of 0 dB with respect to a watt. We'll call it dBW. Right? So we're starting with 0 dBW. Okay? So now we go up through a feed line. This feed line we have measured as having a loss of 6 dB. Right? So let's say we've started with a loss of 6 dB, and we go through and we have an antenna up here which has a gain of, let's say, 8 dB. Let's make it 9. A peak gain of 9 decibels in the horizontal direction. Okay, so what would 0 dBW mean? That's 10 to the 0 power. What's 10 to the 0 again?
1.
That'd be 1. Okay, so that would be, we are really starting at 1 watt. That's what that means. Okay, so now we can just add these together. We start at our 0 point, 0 dBW, minus 6 dB, plus 9 dB. And where do we end up?
3 dB.
3 dB. 3. And what did we say that 3 dB equals?
Double.
Double, 2 times. Which means that if we started with 1 watt, how much power do we have coming out? Equivalently, 2. In those directions?
2.
We have an effective radiated power of 2 watts. We actually, because of the gain, we combined the gain and the loss, we managed to improve our signal by that much. We put 1 watt in. If we had no gain in the antenna, we would have considerably less power going out. So let's say that we were able to do a magic trick and spend a little bit of money, and instead of minus 3 dB, instead of minus 6 dB, we went to minus 3 dB. All right, so we're going to go and add them up. Equals what?
Minus 1.
Plus 6 dB.
6
well,
dB.
Okay, so now because we add decibels, we can represent this as 3 dB plus 3 dB. Hey, everybody, I'm gonna say this. Just everybody study and keep it to yourself. So if we have 3 dB and 3 dB, every time we go up by a factor of 3 dB, that's 2 times. And we have 2 times here. So what's 2 times 2?
4.
Which means that our 2 watts effective radiated power has now improved to
4 watts.
4 watts. By changing our feed line and reducing the loss in the feed line, we've increased our effective radiated power by double.
Okay, I got a question right here. We have 3 dB over 2x plus 3 dB over 2x. Why did you say 2 times 2?
It's not over.
Because it's 2 plus 2, right?
Well, no.
You said 2 times 2, but it was up.
Well, because decibels add and they translate to something that multiplies. Every time you have 3 decibels, that is a doubling.
Right. But when you spoke out loud about this, I think you maybe misspoke. But 2 times 2 is the same as 2 plus 2. So I just want to be sure. We should have added 3 and 3 and got, but 2 and 2 is 4 for plussing and timesing. So is that a plus between the 2 x's?
I'll do another one. So let's say we have 0 dBW. And we have a loss of, let's say, minus 3 dB. And we have another box up here, which is an amplifier that gives us 10 dB. And then we have our antenna. All right. So let's see what that would be. That would be 7. And this gives us another 9 dB. Okay. So where do we go? We start at 0, minus 3, plus 10, plus 9. What do we get?
22.
16.
Okay. All right. So
Oh, -3.
so we're going to see, okay, how do we, there are two things that we know. 10 dB is how many times?
3.
10 times. Because 10 dB is 10 to the 1th power. 3 dB is how many times?
2.
2 times. Okay, how can we break down this 16 into 10s and 3s by addition?
Ten plus 3 plus 3.
10 plus 3 plus 3. 10 dB is how many times?
10x.
10 times.
1.
3 dB is how many times?
2x.
And 3 dB is how many times?
2x.
So 10 times 2 times 2 is?
40.
40.
Yep. So now we're at 40 times. So if we have 1 watt down here, we have an effective radiated power of 40 watts upstairs.
Are these decibels the same as when you're doing hearing tests?
Yes.
And they have a certain
Yes.
volume?
Yes.
Okay, just making sure.
Yep. Decibels are decibels. Now there's a decibel with a the basis is a little bit different. Then there are decibels with respect to volts and decibels with respect to power and watts. So it can change a little bit, but essentially it's just a way of representing orders of magnitude.
Okay.
So it's a okay. So like for instance, the place where decibels really come into play is, let's say that you have a receiver that has a noise floor of minus 130 dBm. How much is minus 130 dBm? 1m, the little m, is a milliwatt. A milliwatt is how many decibels lower than a watt in the first place?
3.
No, it's not 3. It's 10 to the minus 3. A milliwatt, milli means 10 to the minus 3.
Oh.
That's 30 decibels smaller already than a watt. And what does minus 130 dB mean? 10 to the minus 13th power. So if I were to look at this receiver can hear something that is 10 to the minus 13th times 10 to the minus 3rd is
16.
10 to the minus 16th watts, or 0.0000000000001 watt.
No wonder it's abbreviated.
That's why we use decibels. That's why we use decibels.
Yeah.
Decibels take away a lot of extra zeros. So that's decibels. The most important thing to remember, really the only thing to remember, is that 10 times is 10 dB. 2 times is 3 dB, which is actually approximate. A half is negative 3 dB.
Negative 3.
Right? And 1/10 is equal to negative 10 dB. And really, just to know that if something gets bigger, it's plus, and something gets smaller, it's negative. These are really the only two things that you need to know. The reason that I say that is because let's say you have an amplifier with a gain where you measure the input of, let's say the input is 26 watts, and coming out you have 1,372 watts. All right. The only thing you need the calculator for is to figure out 1372 divided by 26, which is 52.7, 52.8. Okay, so we want to figure out how many decibels it is, approximately. So how do we multiply something by 52.8 using nothing but 10s and 2s? Because remember, this is a ratio. Everything that goes in gets 52.8 times bigger.
50
We can get close, right?
Yeah, 50.
Okay. Well, we can start at 1, and then we can multiply by 2 or 10.
And
Okay, so 1 goes to 10. Next one wouldn't go to 100. That would be silly. We could go to 20,
2.
and then we could go to 40. And then the next one would take us up to 80, and not really, because we need to land at 52.8. But we could probably say that, well, okay, that's a difference of 3 dB. So 52.8 is maybe 1 dB. So this right here, this factor of 10 is 10 dB. This one is 2. This one is 2. So, yeah, we're probably close to 15 dB. And if we were to take the log of, let me share this if I can. Hopefully I can. I don't see it. Okay, you're gonna have to assume that I did it right. Okay, let me grab the calculator, unless somebody else beats me to it. Okay, 52.8, and we want to take the log base 10 is 1.7 times 10. Oh, sorry, this should be 3 dB. That was a mistake. So every time we go up by a factor of 2, it's 3. So 10 plus 3 plus 3 plus 1 is, I got 17. And the actual answer is 17.226 dB. So you can you can approximate almost anything with decibels just by rounding it. And it's going to be pretty close to the point where you're not going to really notice the difference. Okay.
Is there a difference in if it mattered? Is it more important if if you're halfway between? Is it more important to go up or down? Which would affect it more?
It depends. It doesn't really matter. I mean, it's plus or minus 1. It's not going to matter.
Yeah.
I mean, unless you're doing engineering calculations that have to be exact, it's not going to matter. Okay. Let's see. Okay. So this is going to lead us into antennas very well. So here we go. This is a piece of wire, and a piece of wire is carrying a current, I. What forms around this current carrying piece of wire?
Magnetic field.
Magnetic field. Well, it goes like that. Okay, so as the current is traveling that way, it forms a magnetic field. What happens if I have another piece of wire that's sitting in this magnetic field?
You have an induction of another current.
It's called mutual induction, and the existence of the magnetic field will induce a current in this wire. So what happens if this is connected to a microphone and you have a signal, which is microphone signal, voice, going this way, and this is allowed to couple with another piece of wire that had another microphone signal traveling through it?
And amplify?
They will crosstalk with each other.
Oh.
That is why we often do this with our wires.
Twisted pair.
You can do twisted pair because they neutralize each other eventually. You can also take your wire and you can do this with it. You can basically
shield it.
you can shield it and essentially now make a grounded Faraday cage around it so that any magnetic field will induce current, which is then sucked down into ground. Okay, let's see, another thing with, let's see, so if you're curious where we are in the book, we are now at page 41, antenna polarization. So we have graduated the other part and now we're into antennas. Okay, so we know how to make a frequency. How do we make a frequency?
Resonant frequency.
Resonance. Right, we have this and we have this. if we take this and we excite it and we run it through a transistor amplifier and we take our feedback and run it back into here or something like that, we can actually make it oscillate at a given frequency, which is good. We can make a frequency that we desire. Now, the question is, what do we do with that frequency? So we can take that frequency and amplify it and run it up to, let's say, an antenna through a piece of feed line. Okay, so it's important to note that there's something called an output impedance, which is for AC, and it is a characteristic impedance. We're going to get to that with antenna feed lines. And right here, most equipment is designed for an impedance of 50 ohms. Most coaxial cable, which looks like this, there's an inside and an outside. The inside is a single conductor and the outside is a braided conductor. What you'll end up with is a voltage that exists in between the two. You'll have an electric field that exists here in between the inside and the outside. It's carrying a current, so it generates a magnetic field which spins around, and it carries power outward based on that. The distances inside there look like this. And each section of this actually represents a section of feed line. You can split this inductor in half, and then you have this little T network, which is an L and an L and a C. Then you can have the same thing over here, where you have an L and an L and a C. That has a characteristic impedance. It's not actually an impedance, but it is a characteristic impedance of that particular design of cable that is then frequency independent. That is known as a Z in this case, and it's usually Z0. For most coaxial cable today, you will find that it is 50 ohms, which is a perfect match to what most transceivers do. They look for a match of 50 ohms to transfer power from inside to outside. It also works the other way. Power from outside to transfer it into the inside. So this cable, independent of how long it is, has a characteristic impedance of 50 ohms. It is defined by the ratio of the center conductor's size and placement to the outer diameter. Okay, so that being said, if I were to make this a bigger conductor, I would change the characteristic impedance of the cable. So you can have a cable that is literally this big, that has the same ratios from inside to outside as a cable that is this big. This would be a 50 ohm cable, and this would be a 50 ohm cable. How are they different? Can you use them interchangeably?
Probably, yeah.
To a certain point. Okay, when do you start to see things go wrong? When do you think you would start to see things go wrong?
When there's a high voltage going through that?
Oh yeah, high voltage. Yeah, you could arc through it. What else?
Length.
When your feed line gets long.
It gets really long. That's right. And the reason being, why does it make a difference? And the reason is because your conductor sizes are just the ratios are the same, but some are a lot bigger than others. And if I have a conductor that's this big versus another one that is this big, which one is going to have a higher resistance?
Smaller.
The tiny one, yeah. And if it has higher resistance, that means that it gets hot faster, and it means it can't handle as much power. It also means that the signal loss for a given length is much, much greater. So you lose a lot of your signal, measured in decibels, oddly enough. So if you have these two cables, which cable is going to be the better one for handling more power?
The bigger one.
That would be the bigger one, yep. So if you had a high power system, you do this. If you had a low power system, you do this, like that. Both of them are valid. Both of them work. But again, if you have, 400 feet of cable going out to your antenna, you probably want to use the bigger one. Now, the amount of loss is also frequency dependent, it turns out. So for a given cable, the higher the frequency, the worse the loss. And these are actually available in all kinds of charts. So another reason to look at these charts is because you have an intersection of frequency versus length and cable. And you find the intersection of all of these, and it gives you a certain loss at a given length for a particular cable. And it might turn out that one cable you get for that particular length and frequency, you have 10 dB per 100 feet of loss. What if your cable is 10 feet long? Do you care?
No.
No, not really. 1 dB is nothing. But what if you have a cable feed that runs up the side of a tower and it's a 1,000-foot tower? You have 100 decibels of loss. That is not a good choice. You'll have nothing coming out the other end. So you go and find something bigger, something that's a lot more expensive, unfortunately. Something that has to be moved with a crane to get the power up to the top because it's so heavy. Okay, so now we are now at characteristic impedances and looking at 50 ohm cables and antennas and things like that. So we're going to start to draw our basic antenna. Okay, and remember this morning when we were talking about musical instruments and length and resonances and stuff? Okay, so there's really only one rule. This is a center-fed dipole. It's fed in the middle, and it's broken in half. Ignore the fact that it's broken in half. It has to be in order to feed power into the two sides equally. There are only two rules. Actually, there's really only one rule. There's really only one rule. And it comes from the fact that we looked at current and wire and Kirchhoff's current law. What is the current at the end of a piece of wire?
Zero.
It has to be zero. Our current has to be zero. Why is that? Unless it's leaking off into space, it has nowhere to go. Yeah, exactly. So our current has to be zero at the end.
The voltage is the highest, though, isn't it?
Well, it depends. We will see. So the question then is, if the current is zero at the end, does it really matter how long the antenna is? No, not really. I mean, yes, it does, but that's the main rule. The current has to be zero at the end, period. Physics says so. Okay, so now, what kind of waves are we dealing with? What do they look like? That has a name.
It's a sine wave.
That's a sine wave, okay. Now, does it not make sense that the current distribution on a piece of wire would follow the pattern of a sine wave? Sure, why not, right? It turns out it does. Okay, so looking at this particular wave, how much of this wave, if it were extended or shortened, shrunk, whatever, would fit correctly onto that antenna that I drew? How many pieces of it? That is the simplest one, isn't it? How much of a wave is that? That would be a half. That would be a half. That would be a half wave center-fed dipole. That is the basic antenna upon which most other antennas are built. because it meets the criterion that says that the current has to be zero at the end. And what else do you see in the center?
A break.
Yeah, but what do you see all the way up there?
What's the highest
It
voltage?
goes to the highest possible point. And what generates a magnetic field?
Current.
Current. So does this have a spot where the current is actually the highest it can be?
In the center.
In the center. That's a pretty good antenna. It does what we ask it to. It's making lots of magnetic field out and sending it out into space. Now, as it turns out, our voltage tends to go like this. So we have our peak voltages at the end, and it goes through, it's not zero, but it goes through the lowest point at the center. So Z is equal to V equals IZ, V divided by I. And this is our I, and this is our V. So where would our impedance be lowest? Where on that antenna, if I were to look at it at different points?
At the end.
Well, no, at the end it would be very high because our voltage V would be very, very big and our current would be very, very low, which means that we'd have something, it would be right in the center. So that is the simplest way to feed a half-wave dipole. It would make it center fed, and it turns out that the impedance is about 72 ohms for a half-wave center-fed dipole. Now, what that also means is if I connect this up to a piece of cable, I can use 50 ohm cable, and I have 72 ohms up here. That's actually a pretty good match. It comes close to transferring all the power in. I can do a little bit of creative matching up here. I can go like from here to here and make it, add a little bit of a gamma match or a delta match or something like that and change the feed point impedance slightly. And what that can do is it can bring the antenna feed point down to 50 ohms, in which case then I now have a pretty perfect match with my feed line, which means that this is a very, very simple antenna that happens to work really well. So what we're going to do is look at this antenna and see how long it has to be. Does everybody remember that formula that we did this morning? Everybody remember that like hours ago?
Yeah.
Everybody remember that? Well, now we're going to get to use it. So what's our frequency? Let's say that we're going to pick a 6-meter half-wave antenna. So I'm going to erase that mass right there and get rid of that. We're going to make a 6-meter half-wave antenna. Okay, how long is a half-wave antenna in wavelengths? Not a trick question.
3 meters.
Half a wave, exactly, half a wave. Okay, but in order to figure out a half-wave antenna, what do we have to figure out? We have to figure out what a full wavelength is. Okay, so we're going to take a look at our frequency charts and say how long does this antenna have to be, and excuse me. And here's the band plan. Hopefully that shows up. No, it didn't. Shoot. Okay, it's still wrong, isn't it? Actually, is it right? It is right. Okay, so we're going to look at the 6-meter band, and we're going to make we're going to pick the bottom edge of the 6-meter band. Okay, how many megahertz are we talking?
52, 53.
Well, we're going to go with 50. Bottom edge is 50 megahertz, so we're just going to go with 50 megahertz. We're going to make it for DXing. So we're going to pick 50 megahertz. We want to do weak signal work, which is CW and sideband. Okay, so our frequency is 50 megahertz. What's our wavelength? Oops. What's our wavelength going to be?
Wavelength is 6 meters, right?
Yep. Oddly enough, it's called the 6-meter band. That makes sense, right? Okay, so Now we have to say, okay, how long is our antenna in wavelengths? It's a half wave. Yep. So a half wave is
3 meters.
3 meters long. Okay. So if we cut this antenna for a half a wavelength and make it 3 meters long, what will happen? It will not work.
You need about 112-inch antenna.
Or what? Right. Except that this is too long. And it turns out that 1 meter is about 39.4 inches. So this antenna, by that calculation, would be about 119 inches, which it turns out is too long. Because what's an antenna actually made of?
Sorry, Scott, are you intending to show us the band plan or your whiteboard?
Whiteboard. Sorry.
Thank you.
There we go. Okay, so half wavelength would be 3 meters. That's about 118 inches. But that would be too long, as it turns out. The reason it would be too long is that what is an antenna actually made of?
Metal.
It's made of wire, which is made of typically copper. Could be aluminum, but basically it's metallic. It exists in the real world. And it has self-inductance, it has some capacitance thrown in there, and it turns out that you end up with an antenna that's about 5% too long if you do that. So you have to take this number and you have to multiply it by 0.95 to get rid of the extra 5%, and you get 2.85 meters long, which you can then convert to inches. You get 112 inches, and then you get an antenna that is resonant at 50 megahertz. Which you can physically then build and put up in a tree or do whatever, and it'll actually work. This is how you make a functioning antenna. Now, this antenna is 112 inches long, which is about 9 feet? Not very big, is it? Okay, so now what we're going to do is we're going to take a different antenna, and it's still going to be a half wave, except that now we're going to cut this antenna for the 80-meter band. All right, and we're going to pick a different frequency, obviously. And we're going to go down to the 80-meter band, and somebody pick a frequency down here. Notice it goes from 3.5 to 4. And the technician class band goes from 3.525 to 3.6. What would be a good place to start?
3.5.
Right in the middle.
Yeah, let's go 3.56. Right kind of in the middle. 3.56 megahertz. Okay? By my calculator, I'm gonna do what? 300 F and lambda. Does everybody agree with that?
Sure.
Here's our frequency. Okay, 300. Let me grab my calculator again. Unless, of course, I closed it, which would be dumb. 300 divided by 3.56. And I get 84.27 meters long. Now, what is that a measure of? How many waves?
One wave.
That would be one full wave, so that's my wavelength. And if I were doing a half wave antenna, how long would it have to be?
42.13.
135.
Close enough. We'll say 42 point something. All right, but it's still too long.
Is it the 0.95?
Yep.
Times
0.95 gives me 40.02 meters, which is almost exactly 40 meters. So we'll just say 40 meters long, and then multiply by 3.3 feet gives us 132 feet. So on 6 meters, we were at a 9-foot long antenna. On 80 meters, we are at a 132-foot antenna. Which one's easier to put up?
Yeah.
6 meters.
6 meters is a lot easier. But if you want to operate on 80 meters, you've got to find room to put it up. Now, another thing you can do is you can take that antenna and you can fake it. right? This is a half-wave antenna. You can make a half-wave antenna that isn't really a half-wave antenna anymore. The way that you would do this is you would take your half-wave antenna that looks like this, fed in the center, and what I'm going to do then is mark my endpoints like here and here, but then I'm going to get rid of the element in the middle, and I'm going to take the center point, like the center section like this, and I'm going to make these like, I don't know, 25 feet long and 25 feet long, and then I'm going to do this.
Yeah.
Except now my total length is not that same 132 feet. It's maybe 60 feet long. Okay, why does this work? What do I gain from it? And what do I lose?
Where you're looping the wires.
Yeah,
you're increasing the.
You're electronically lengthening the
and
antenna.
I probably need to do a little bit of that to make them resonant. Or maybe not. I don't know. I'd have to see. But yeah, okay, so what I'm doing is I'm taking some of the length of the antenna and doing what?
Loading the antenna.
I'm coiling it up on itself, right? Okay, what's the benefit of doing this? If I remember my big
shorter
antenna
distance, but you still have the same amount of wire.
if you remember this pattern where I have the maximum current and I do this and I can take this section and move it right here. I still have my maximum current right here. But then what happens when I'm inside that? This is called a coil or a loading coil or a trap, by the way. This is more of a loading coil. So I'm going to take the capacitor off. I don't really want it there. So what would happen inside that loading coil? Every time I loop around, the magnetic field would change direction and it would cancel. So my current drops off really, really drastically in that section. But to be honest, I'm okay with that because I've shortened it, and then I have a little section at the end that might work. So what I've managed to do is I've managed to maintain my maximum current, which is the thing that launches most of the signal or a bulk of the signal, and I've managed to stuff it in a smaller space. What have I lost?
Your radiative power. I mean,
yeah, you lost your efficiency.
Yep.
But if you live in a space-constrained place, maybe by doing this you went to minus 6 dB. All right. So what is minus 6 dB? By threes and tens, what's minus 6?
4.
Minus 3 dB and minus 3 dB. Right, so that's a half is a fourth. So if I put 100 watts into it, how much power will I get out?
75? No.
Nope. I only get 25 watts out.
Oh.
Not very efficient. Where does the other 75 watts go?
Heat.
It goes to heating in those coils, yeah. But let's say that this is enough for me to get by. I might be okay with that if I know that it's not going to set fire to the house or anything. The other thing I could do is instead of running 100 watts, what could I do?
Drop it down to 50 watts.
Yeah, but that would make things worse. What can I do to overcome that loss?
Increase it to
I could use a small amplifier.
Take out the coils.
I could use a small. Well, no. If I take out the coils, that'll make it worse. I could use a small amplifier and run 400 watts, in which case my 25 is now 100. Right, but then these things are burning up how much power?
Yeah,
300 watts. So they better be rated for it. So there's all kinds of games to play when you're designing an antenna system and building it. Okay, here's another one.
How does a log periodic work or something like that?
Well, we're about to get to Yaggies in a second. So, okay, so this is another form of antenna, which is a quarter wavelength tall over a ground plane.
Very popular on CB.
Very popular everywhere because this is typically a magnet.
On the
So you
roof
can
of a
just
car.
stick it on the roof of a car. All right, so the way that this works is that if I am, let's say, way over here, and I'm looking at this car, I will see a quarter wave antenna, which has current on it, but I will also see reflected down here another quarter wave of the antenna, which is merely a reflection of the actual antenna. As far as I'm concerned, what am I seeing from afar? I'm seeing this whole thing, which is what?
A half wave.
That's a half wave dipole, yeah. This is actually a very popular antenna. This actually has about 3 dB of gain compared to a dipole.
Get the SWR very accurate.
And the feed point impedance is about 36 ohms. About half of a dipole, as it turns out. So one of the tricks about this, though, is that it only works if it's placed over an actual ground plane. When I say a ground plane, that is a large reservoir of available electrons. Because what's happening down here is that you basically have your cable going in, it splits here, one part goes up and the other part goes to this metal plate, which is separated from the ground plane. This is usually steel, which is nice because the magnet that's in this little mount can stick down to it. So looking at this very closely, it is actually this. What is that? Electric capacitor. What is that? That is a capacitor. So you are basically capacitively coupling the other half of the antenna to the frame of the frame of the car. So now what you've provided is when the antenna is looking for current, there is now this giant source, this giant resource of available electrons that can then make the other half of the antenna look like it's actually there. It's imaginary, but it actually works really well.
Except on Corvettes.
Okay, the other thing is you can actually take an antenna and make it a 5/8 wave, which is considerably taller. You can also make a half wave. If you can feed power into it, you don't need a ground plane. This is useful for, if you can feed power into it, this is useful for situations where you have like a fiberglass body on your vehicle. A 5/8 wave antenna is popular. It requires a ground plane, but the thing is that like a quarter wave antenna will have a radiation pattern that looks like this. A 5/8 wave will have something that looks like this, a lower angle of radiation. The reason to pick a lower angle of radiation is where are most of the people that you're going to be talking to, considering this is going to be on the roof of your car. Are they in the sky? Quarter wave antenna will have a lot of signal launched into the sky. A 5/8 wave will have a lot of signal launched along the ground. So that's why people use 5/8 wave antennas instead of quarter wave antennas. Now, oddly enough, the only knock against it, if you're using a 2-meter 5/8 wave antenna, is that this is about 43 inches tall, and on certain cars, it smacks the garage door every time you pull in. This is only about 19 inches tall, and you can do the calculation for that tonight if you feel like it. Okay, let's see, where are we on to now? We are on to we are on to polarization and how all this works together. Okay, so the direction of the wires determines the polarization. The electric field goes back and forth this way. on a horizontal dipole. On a vertical antenna, the electric field goes this way. So the horizontal dipole, this would be known as horizontally polarized, and this would be known as vertically polarized. Polarization is the direction of oscillation of the electric field. And most cars, when they're using FM modes, such as 2 meter FM, 70 centimeter FM, will use vertically polarized antennas and frequency modulation. The reason being that a lot of people, when they're in their cars, they are expecting to be operating into and through repeater systems. A repeater system basically is, let's say, on a hilltop, and looking at it from above, it looks like this. Just a dot if you're looking down at the antenna, which means that it does not know which direction is which. It sends out signals omnidirectionally along the horizon, vertically polarized. A car which is driving around the neighborhood will look like this, with a vertically polarized antenna, which will have a radiation pattern that looks like that. As far as they are concerned, they are talking the same language. And it doesn't matter which way your car is turned. If your car had an antenna on it that looked like this, depending on the direction which the antenna was turned, it would fade in and fade out. When you start to deal with polarization of antennas, if you are cross-polarized with the target that you're listening for instance, you are using a horizontally polarized antenna, and so here's the repeater station, and here is you, and you are horizontally polarized, and they are vertically polarized. You have a signal loss of greater than 25 dB, just from the fact that your polarizations are wrong. This is roughly, 10 dB and 10 dB and 3 dB is 10 times 10 times 2 is 200 times. So your signal is attenuated by a factor of over 200 just by virtue of you having the wrong polarization. However, if you're dealing with, let's say, weak signal work, which is single sideband or digital modes, or Morse code or things like that, meteor scatter, you're typically using horizontally polarized antennas. So this would be used for weak signal work, as it's called.
So is that where radio signals go in and out? As you're traveling along, you lose it?
That's another thing. No, but yes. All right, so we're almost there. Okay, so we're going to draw an antenna that has a dipole in the center, and then we're going to create an antenna, create an element that's a little bit longer, and another one that's shorter and shorter and shorter and shorter. This is known as the reflector. This is known as a director. This antenna, which is a dipole in the center, these are known as parasitic elements. The reflector is a little bit longer and the directors are a little bit shorter, and they create a net gain in the forward direction of the antenna. This is known as a beam. This is also known as a Yagi. It's a specific design of a beam. And this could have a gain of, let's say, 10 decibels in the forward direction. These also have, because they have a small signal coming out the back and a big signal coming out the front, these also have a front to back ratio, because if you're pointed one way, you don't really care what's behind you. You also don't care what's to either side. So you have a front to side ratio. Any idea what these things are measured in?
dB.
In decibels. Everything's in decibels. When you go to look at an antenna, everything is in decibels. There's also something where if I have something called dBd, that is decibels in gain compared to a dipole. There's another thing which you have to look at very carefully, which is dBi. This is compared to an isotropic radiator, which is an imaginary device which transmits energy in all directions equally well, which does not exist. A dipole, to begin with, a dipole is 2.15 dBi. So if you buy something, if you find an antenna that has a design that has a gain of 4 dBi, that's only 1.8 dBd. Not a great antenna. If you have an antenna that says 4 dBd, that's considerably better. So that's a little distinction that you have to make. Okay, now somebody mentioned a log periodic, and I think this is going to be the last thing. A log periodic is a series of driven elements, which are dipoles, which get smaller and smaller and smaller and bigger, but they're all fed like this. They're all fed power. And what happens is that at any given frequency, only 2 of the antennas are going to be even close to working. The other ones, because they're so far away from the frequency that you're operating on, are essentially non-factors. So on the lowest frequency, you'll have these 2 guys working. On another frequency, you might have these 2 working only. On another frequency, you might have these 2 working. And the other ones are non-factors. So really what you end up with is how many elements working on any frequency?
2.
2. That gives you a gain of, let's say, 4 dB, 5 dB. So what that means is you don't have a lot of gain. You have a big antenna with not a lot of gain, but what does it get for you?
A lot of frequencies.
A lot of frequency coverage. This might work from 3 to 30 megahertz. Well, that's, if you're not looking for a lot of gain, you have it up on a really big tower, that's going to be helpful in and of itself. And that's a really nice factor, having that much frequency coverage to be able to cover that many different things at once. All right. Let me just make sure I didn't forget anything important, because now we looked at how to actually make this work. Antennas, feed lines. We didn't get into connectors yet. So connectors are going to be first thing in the morning. And the other thing is that I wanted to just briefly bring up, remember this morning, like a long time ago this morning, before we even started, I had shared let me unshare this. I had brought up a web SDR. Everybody remember that? It was like days ago, it seems.
Web SDR.
Yeah, it was a web SDR. And okay,
the digital modes. We were listening to the digital modes.
We were listening to Morse code and digital and some voice. And
Yeah.
okay, so let me bring this up. Okay, so I would like to point out that one of my favorite events of the whole year just started. And I'm going to go over to the University of Twente, hopefully, and bring up their web SDR. And hopefully it works. You know what? Everybody in the world is probably using it right now. Oh, there it is. Okay. And it was a little busy this morning. And right now, like I said, one of my favorite events of the whole year just started. And Bruce, I expect you to make at least 1 Q today. Let's see, we're going to go to 21. Now we're going to 14. Come on. Nope. Nighttime in Europe. There we go. It's nighttime in Europe. You have to remember that. This is the CW band. CW is Morse code. In Europe right now. Notice all of those parallel signals at the same time. So this is something called CQ Worldwide. It's a worldwide Morse code contest. It runs for 48 hours and it just started 4 minutes ago. Look at all those beautiful signals on the air. This is one of my favorites. ER6T.
I'm hearing a lot of CQs, but they're really fast.
They are really fast.
I was just going to ask, there are people who actually operate CW that fast?
Me?
Yeah.
All right, you want to see a trick? I can show you a trick. You don't have to hang around for this if you don't want. But let's see. YouTube.
You're using a computer to do it.
I can't go that fast without it, but okay, here we go. Let me share this. Give me a second to go find it. And this is what can happen if you spend a lot of time doing something. Let's see if I can do this.
Under.
45 words a minute.
Go, dog.
Dog.
C.
C.
Also.
Also.
Five.
5.
Wood.
Wood.
So, could you hear that?
Oh yeah.
Yeah, I can go faster than that. I can do 50 in bursts. it's something that I was not able to do until I was.
Like how long is that? And I was going to ask, like, so you were very young when you got your ham. Could you do
15?
You were 15, and you can still. You were back at 15. You could do. You knew Morse code, or did that come later?
Not that fast.
But you did know Morse code back then.
Yeah, I learned it when I was 15. You had to do Morse code to get a license.
Yeah.
Oh, that's changed.
I had to do Morse code.
Yeah.
Morse code.
I got my ticket in 71, and the extra class
was 20.
Guy who trained me, he had a sked with the guy. He was in the Santa Rosa area, and he had a sked with the guy in Seattle, and they would start off with a straight key,
I can only go 25 with a straight key.
They would start off about 18 words a minute, and then they kept getting faster and faster, and then they switched to paddle, and then after that they were doing like 32 above. I couldn't believe it. I couldn't even make sense of it.
I do 30 plus with paddles like every week.
Yeah. Oh man.
And I can't send above about 35, but I can copy like. Okay, let's see. Let me share this and see if I can do it. Okay, ready? 50 words a minute. Complete.
Complete.
Cone.
Come.
Oh, come. I missed that one. Big.
Big.
Yeah, so it's just learning another language. I don't even have to I don't even have to think about what the letters are. They just come into my head.
Right.
So
like playing the piano.
But they just form there. It's kind of cool. It took a long time and a lot of hours of doing this.
Hey Scott.
Yeah.
This is Bruce.
Bruce, you gonna do some? No code yet, do you, Bruce?
How much more time you got in the class today?
None.
Oh, okay.
It's over. We're just shooting the breeze now.
No, I've been trying to address some of the comments for you on the chat. I probably got a little too wordy on a couple. I apologize for that.
I haven't been watching. I just know that it got
a good thing. But
I just know that it got a little busy.
You do know me.
Yeah, I do.
If I could, I wouldn't mind taking a shot at a couple, for the group that are remaining here, or at least one anyway.
Yeah.
Yeah.
All right. So I guess I'll introduce myself. My name is Bruce W7BTM. I'm a friend of Scott's, and he was the one that helped me get my license.
You're a retread too, weren't you? Didn't you have a license when you were a kid, or no?
I had a license when do I have to admit that?
You do.
I had a license when I was about 16 or 17, back in the mid 70s. But as you'll hear a lot when you get your license, college, family, work, all those have
kids travel.
Yep. But anyway, I told myself I'd get relicensed, and I took Scott's class, this same class. And
everyone's a little bit different,
What's that?
Everyone is a little bit different.
Yeah, I know, but the basic concepts.
Yeah.
Yeah. Anyway, to make that story short, while I was studying for the technician license, I also studied for the general license, which is the next step up. And I used apps for my phone and computer to help me, along with books and the class. And I was able to get both in the same sitting. Once I sat down I passed the technician, and they immediately asked me, "Would you like to take the general?" And I said, "Well, sure." I wasn't quite as confident. But I took it and I passed it. I didn't get as many right, but I still got 85%. So I got 2 in 1, which was awesome. I want to address a couple questions, if you don't mind, Scott.
No.
Talk about,
just don't make me look bad.
No, you're awesome. There's questions about why do I need to know all this stuff? Why do I need to know about all these deep down, dirty technical things, to talk on my radio? One student mentioned, the idea of a chat room, and that's okay, but those concepts they come from the internet. And while it's true that you can connect a modern radio to the internet,
I do. I use Echo
all
the time.
It's actually a tremendous amount of fun. It's really fun. But you're still using a radio, and you're still sending signals out the air, because connected to the internet are other radios that are picking up your internet digital stuff and retransmitting it out into the wide open. And because of that requires a license. And to get a license, the FCC wants you to know about the basics of radio theory. And that is what these classes are all about. So even though you might decide once you get a license to sit on the internet and chat with people that way, if you're going to be using any form of radio or bands, like a little handy-talkie thing, we call them handy-talkies, then you still have to understand these basic principles. And that is why the FCC requires you to take these tests.
I have like 10 of these. So,
What? Oh, the handheld?
Yeah, I have like 10 handhelds.
Yeah.
We have I have 2 kids. My wife and both kids are hams.
Yep.
So we have six of these and a handful of others.
And they're very inexpensive.
Yeah.
The other thing I would mention about those, while they are fun, and it's a great way to get started once you get your license, and very inexpensive. You can buy one of those for $30, brand new. It's
actually $20.
Or $20.
You can get a cheapo Baofeng for $20 now.
That's right. So while they're a great way to get started, those radios are by no means the last word in amateur radio. The world of amateur radio is far bigger than those simple radios. And when you get into that part of it, you really can talk to somebody across on the other side of the world without going through the internet. To do that requires a much different kind of a radio and an appropriate antenna and some understanding of how all those pieces and parts go together. That's where the real fun of ham radio comes from. And the last thing I'll say here is that the start of your learning journey is when you get your license. That's when the real learning begins. You get your license, find a club, find what we call an Elmer, right? I would consider Scott my Elmer, or one of them anyway. An Elmer is somebody you know personally who's a ham radio operator who can help you understand and answer questions that you might have. And these people are in every single city. And the best way to find them is through a club. And once you find one, they're going to be your friend. They're going to help you with everything. They're going to answer every question. They will not, no question is too simple for these people.
There's no such thing as a stupid question.
No such thing as a
I
stupid
have
question.
one. So I don't understand the practicality of antennas, because what I'm hearing is that you have to have different length antennas
Yes.
for different frequencies.
Absolutely.
So if I come to your house, is it covered in antenna?
No, I have two compromised antennas that I feed with ladder line, which is parallel wire feeder, and I have a tuner which modifies my feed point impedance for each one.
Or just
Well,
an antenna like the one you showed in the last example, right? That you have the different,
Well,
many
I'm
different
not going
frequencies
to
you
be
could hit
able
with on
to
one
have
antenna,
one of
right?
those. It's too
You could
big.
build it yourself out.
Hey Scott,
yeah.
I'm going to if you don't mind, can I share?
Yeah, you should be able to now.
Okay, so let's see. I think yeah, let's try this and this. Okay, can everybody see this?
Yeah.
Okay. So these are my primary antennas. I live here in Tigard, Oregon, up in the Portland area, and I have a small lot, with a cul-de-sac. I have, my lot is 100 by 50 or 100 by 80 feet. I do happen to have some big trees, which is fortunate for me. And I don't live in an HOA, so I don't have to worry about that. I realize that not everybody will have that situation. You might live in an apartment, you might live in a rental house, you might live in a neighborhood that has an HOA, and those are all different challenges when it comes to putting an antenna out. This is where your Elmers will help you. They can give you ideas on how to make it work, even in those types of situations. I don't have an HOA, but I do have a small yard. So these are my antennas, and this is 50 feet long. And because I have big trees and a son who is a tree climber, he helped me put those up at about 45 feet. But these antennas are what we call multi-band antennas.
AKA compromise. But they work.
Well, they're all, everything other than a pure dipole is a compromise.
That's right.
But compromises are fine because they give you a way to talk on a whole variety of frequencies, and it's worth it. So when Scott showed you a picture of a dipole, he showed you the feed point was right smack in the middle. Remember that?
Mm-hmm.
Well, look at mine. The feed point is over here off to one side. It's not in the middle. And that's what's called an off-center fed antenna. And that's part of the technology that allows it to work on multiple bands. There's more to it than that. There's a special little electrical transformer device right here and some other stuff. But when you combine this with a tuner, which is a device that's built into your radio or separate, it can match your radio to that antenna at a specific frequency.
And we covered that.
Okay, I missed that because I had to come in late. So, these are what my antennas look like all curled up. And I've got pictures of it. I've got a weight system that keeps them tied up in the trees. Here's my son climbing up in the tree and helping me put pulleys up.
That's not a very big trunk he's on.
Oh, it's big enough.
I guess.
So, yeah. So, mine is like this. It's up in the air. You know what? It was really fun figuring out how to do that and finding a way to put that up and getting help from friends and family to do it.
Okay, I'm going to take over the share for a second.
Yeah, go for it.
So,
I'm done with this. I wanted to show because it came up about antennas and one frequency, and this is one of the ways you can do that.
So my daughter and I and 4 friends just came back from Wallis and Futuna. One of your homework assignments is to look up where Wallis and Futuna Islands are. And so this is us operating antennas. This is a place where we went where there were no antennas and no equipment. We brought all of this stuff with us with the intent of operating and making contacts around the world. And there's me, there's some more equipment, there's more stuff, lots of contacts. And this is what the antennas look like when they're all boxed up, ready to go, bagged up and ready to ship. There were six of us. We had what, 100 pounds of gear each, including all our luggage. That's all our luggage and all of our clothing and everything. And we basically managed to put together a station at this guy's house. He rents it out, and we traveled to a faraway place and took 600 pounds of stuff with us and operated for 13 days and made over 38,000 contacts in 154
Whoa.
countries from this tiny island in the middle of the Pacific. For
Okay, I have
us,
one more
that's fun.
question before I have to go cook something.
Mm.
I have lots of questions. In fact, I feel like I'm drowning. But other question has to do with the coils on that antenna to make the whole thing shorter.
Uh-huh.
Lots of questions having to do with that. But those coils look like what inducers look like. How are they different?
Inductors, they are. They're just inductors.
Sorry, inductors.
It's a homemade inductor.
It is an
The
inductor.
thing about antennas, you can buy an antenna, but you can build your antennas too. And antennas, they're just wire.
Yeah.
And you can I have so here's a good rule of thumb. A really expensive radio with a crappy antenna is a crappy station.
Mhm.
A cheap radio with a killer antenna is a really good station. Your station, your equipment is only as good as the antennas that they're connected to.
Okay.
Hey, Scott.
Mm-hmm.
I don't have a license, so I operated for years on 11 meter.
Yeah.
But I'm in Apple Valley, California, but my cabin is about 45 minutes from here up near Big Bear, California.
Mm-hmm.
And I'm 500 feet up with an Antron 99.
Yeah.
And every day in the evening, I can talk to Guam,
yeah.
Australia, New Zealand, Japan, Hawaii, like these guys are next door.
Yep.
That's quite a way. And by the way, that covers that island you're talking about.
Yeah.
And if I'd known you're out there, I could have tuned in and listened, but I couldn't transmit, obviously. But it's a daily thing in my area. But being 6,500 feet up helps a little bit.
Oh yeah. Yeah, absolutely. And I've made contact now with, at last count, 277 countries or 277 entities around the world, and there are 340 to do. And I've been at it for 41 years. So
I have a commercial video license. I'm smart enough not to stand in front of the antenna.
yeah.
By the way, that's with the 1978 President Grant.
Mm-hmm.
So I have a question.
Yeah.
So Scott really hints at what he did traveling to a faraway place. That's called a de-expedition.
Bruce, did you work us?
Yep.
Not in that one.
Oh man!
No, wait, no, I did. I got you a couple times on FT8.
Okay, good.
I couldn't hit you on phone for some reason.
Okay.
But what I was going to say is, that's a special one. It's called a de-expedition. DX stands for distance, and so it's a distance expedition, right? But there's so many other ways that are a lot less expensive that you can get out and have fun. One of the most popular today, which has really blown up in the last few years, is something called HOTA.
Congratulations, Bruce. There you go.
Hey,
you're in the log.
You're going to call me on that.
You're in the log.
So another one that's becoming incredibly popular is called POTA. And what POTA stands for is Parks on the Air. And what people do is that they bring a radio to a designated park that's on a list of master parks. They're U.S. parks.
There's only 12,000 of those.
12,000 different parks. And they try to see how many people they can talk to while they're sitting in a park on a bench, with a radio on a bench and an antenna stuck in the ground or the tree. Or maybe they have it in their car or a motorhome. If you see my picture here on the Zoom, I have an old ancient motorhome. And I bring a radio when I go camping, and I throw a wire in a tree, and just have some fun. So you do not have to have a system that's at your house or your home. You can get out and bring a relatively inexpensive radio with you, and power it up with a battery on a park bench and have a tremendous amount of fun.
Can I ask, why can't we just make the antennas, the really long ones, into like an S shape?
because the fields will tend to cancel each other out. You can certainly try it. It'll be, it'll be, I mean, it will be, what's the word for it? It will be greatly compromised.
So it's the band that does it, or do they cancel each other because they leak electrons or something?
No, the fields that are generated they end up canceling each other out before they get launched.
Okay. All right. Thank you.
But that's a big part of antenna design. You are certainly capable and able to, using modeling software, do some very complex calculations using software that is now completely free. And you want to see what your pattern looks like, you just model it up and tell it to go run it and scan it at different frequencies, and it'll print out a 3D graph that shows you what your antenna patterns look like.
This is what I meant by experimentation
Oh yeah.
for amateur radio.
Oh.
Yeah, I mean, we're not limited in any way to any one particular type of thing. Like, so there's something called a hex beam, which is a hexagonal, excuse me, it's a hexagonal two-element Yagi that operates typically on multiple bands. One of my friends said, "You know what? I don't like the two elements. I want to make it bigger and make it a three element. And I don't want to. I have lots of bamboo in my yard, so he cut down a bunch of bamboo. It'll all grow back anyway, and he made all his antenna elements and spreaders out of that bamboo. And he said, I don't want to put up a tower, but I've got a 120-foot tree. So he hooked up some ropes and pulled it up in the tree.
Wow.
His rotator system is that he's got a rope that he can go outside and move the rope.
A lot of people.
It works very well, by the way.
There, if you pay attention to like Amazon or other places like that, you'll see these low-cost handheld radios for sale everywhere. As I said, we call them HTs or handy talkies. It's like a walkie-talkie, but we call them handy talkies. And you can buy them for almost nothing. And they are fun, and there's a lot of fun things you can do with them. One of the funnest is something called repeaters. And a repeater is another radio transceiver system that's usually centrally mounted. For example, here in Portland, there's a powerful repeater 500 feet up on a giant tower looking over Portland. And those allow you, and oftentimes they are linked to the internet. There were some comments about internets, right? So when I talk on my radio, like this one right here, here it is. So I can talk on this radio, and it transmits to that transceiver on the hill 500 feet up, and then broadcasts it around the Portland area so that people farther away can hear me, even if they can't hear me directly. They also connect my voice to the internet where somebody in England can pick me up through his repeater, right? So even though this radio cannot transmit across the ocean, through that linked technology, I can get across the ocean with it.
Okay, my turn.
Let's do that. Go ahead.
Okay, so with regard to POTA, this is something that I wrote about a recent trip to Alabama that I took. I always take some equipment with me, and this was a park in the city of Birmingham. There's all my gear that I bring, packed away, sitting in the front seat of the car, and here's what it looks like on the roof of the car. I made 25 contacts using that little loop antenna, running 5 watts of power using Morse code, the farthest of which was about 1,500 miles.
What bands were you using, Scott?
I believe that was exclusively 20 meters.
Okay.
But that loop antenna, I've used that all over the world, made thousands of contacts with it, and the whole thing folds up into a couple of bags that are literally that big.
Did you make that one or did you buy it?
That one, I've bought one and I've built one. That's the one that I bought.
You sell plans to build them? You got any plans out there?
There's really not much to it. I mean, almost any size will work. The most important part is the capacitor, the tuning capacitor in the base. And if I zoom in, I think I'm still sharing. Am I still sharing?
No.
No, I'm not. Okay, let me reshare.
Is there
There
a
we go.
Guinness Book of World Records for contacts?
I have no idea. But this little tuning knob right here, this box is where the tuning capacitor is. And when you look at this whole thing, you can see the tuning capacitor. So interestingly, the power is driven to this small element up top, this small loop, and the big loop that actually goes through the capacitor. It's called a magnetic loop because that small loop up there, it basically is a kind of a shorted loop, and it creates a large magnetic field which induces current on this other big inductor, which then radiates into space. So there's actually no electrical connection between the inside one and the outside one. By virtue of that inner loop being inside the outer loop, it induces a magnetic field, it creates a magnetic field which induces a current to flow on the big one. And the capacitor down at the bottom just basically tunes the big loop so that it resonates on the desired frequency. It's a really clever design, and it's very, very compact. I mean, this whole thing is just it's made of cable with a selfie stick.
What do you run?
Is
You
it
don't
really
mind
a
asking?
selfie stick that you repurposed?
Yeah.
Oh, that's cool.
Yeah. What were you asking?
What did it run you about one like that when you bought it on Amazon or what like you talked about?
I built
You actually
one
do
for
about-
100. I built one for $125.
Okay,
The
there we
one
go.
that I
That's my
bought,
speed, yeah.
I think I got it used for about $250. And
Okay,
again,
yeah, let's go with option one. Yeah.
most of the
Anybody have
cost
plans
is in
for
the
me?
capacitor.
Okay.
Those capacitors, a good air variable capacitor is really expensive because
I got you.
even at low power levels, you're still going to be seeing 700 to 1,000 volts in there. So it's got to be big enough to withstand, 1,000 volts. That's a pretty good sized air gap.
That's another quick question, just if you don't mind me asking. Do you have that run directly to your car battery in your car, or you use the cigarette lighter?
I use the
yours?
cigarette lighter for that one. If I'm operating out of my own car or like a hotel or something, I'll just plug it into the wall. If it's if it's like on a park bench, I've got just a 12 volt lithium iron phosphate battery.
Oh yeah, I'm gonna get one of those.
And yeah, I mean, at the kind of power levels I'm running, that lithium iron, like a 20 amp hour lithium iron phosphate battery will run for like 2 days.
Wow.
How long is tomorrow's class, Scott? What time does it go from?
9 to 1.
9 to 1.
9 to 1.
And what happens after that?
We give a test. We give a test. Does everybody feel a little bit better about the stuff that they learned today?
Yeah.
Oh yeah.
It's a lot of material, right?
Remember, though, that the real learning starts when you get licensed.
Yep.
The background helps you pass the test. Studying for the test, using the study apps to help. I mean, there's a memorization aspect to this.
Yep. You got to practice. I mean, you want to make sure you pass. And I can't help you pass. I can teach you the basic stuff underlying all the questions. That's my goal.
Yeah, and I put it in the chat, but thank you for taking time out of your weekend and putting together this opportunity, this free learning experience to.
Well, my family actually
thinks learn more.
I think my family actually appreciates me having something to do other than deal with them. So it's embarrassing, but it's true. Like, I believe my wife actually told me, "Go find something to do." So, so 50 something classes ago.
Did she change her mind?
No. I just know if I have a long weekend, I'm probably going to teach a class. Because why not? I mean, there are a lot of ways to waste a lot of time. This is not a waste of time. So, And I still get
It's
work done around the
appreciated.
house.
Yeah.
I really appreciate learning. When I was a kid, my dad was a ham radio operator, but he was the only one in our family, and we could go on trips and he would carry this, I think it was a WT way back when, but it was much bigger. And we could
Yeah.
make phone calls from anywhere back long ago, decades and decades ago, before there was any idea we'd get cell phones one day.
What do you remember his call?
I don't know if this is right or not because it's been decades and he's passed, so I can't ask him. But when I think of it, I think N7JI.
And what was his name?
N7JI. Is that even a handle?
Oh, yeah.
Is that right?
That's a
So
call
it might
sign.
be. I heard it all the time, so it might be correct.
Could you bring up QRZ?
Yeah, it's not in there.
Oh.
Yeah, this would have been like the late 70s, early 80s, I think.
Let's see. We can look him up. If I know his name, that helps.
William Leonard Miller.
William Leonard Miller. Where did he live?
What was that call sign again?
Minnesota.
Minnesota?
ULEN. Ulen, Minnesota.
Okay.
Minnesota.
Snowden.
Okay, so you said
Land of
late.
10,000 taxes.
Let's see.
Did he have a license in 1963?
No, I don't think so. I don't know. I just remember it when he started carrying around the handheld thing. It changed our world a lot because we no longer had to worry when we were on the road. It was a big deal before cell phones. What to do if you had an app? If something went wrong, there was no way to reach anybody.
Yeah, auto patch was a great thing.
What was that call again?
What year did he?
Auto patch.
What year? Oh, auto patch. That was a telephone
So
patch.
let's try 83. I think I remember being somewhere in 83, and we've been doing it for a little while, maybe.
The book I have is only up to 1963, so it's going to be.
I'm looking in the Internet Archive.
It was really fun to learn all this. He's passed now, and I have no other. But this is like connecting me back to him and my kidhood.
Okay, let's see. So here's the. What was this call? You thought? Let me see.
N7JI.
Okay, well, it came up with the zeros first, so let's see if I can download that and do a good search. Get PDF. I should be able to do a search. So this is 1983.
Yeah, N7JI.
Okay.
So the book that he's looking up that's on the internet is something called the Call Book.
Radio Amateur Call Book.
And before there was internet, they printed like a telephone directory of all the call signs.
I still have copies.
Wow.
They're enormous.
And they're all
2 inches thick.
Yeah, I have one, but mine's even older. But you can get to most of them online.
So my friend Bill his license has run out and he wants to get one again. I was excited. I was taking this class and I talked to him and he wanted to know, will he get his same call numbers?
No, unless he asks for it.
Oh, he can ask for it though?
After the fact.
Oh, okay.
It kind of also depends on how long it's been.
Yeah.
Oh.
Somebody else might have it. Okay, what's his last name?
William Miller. William Leonard Miller. He sometimes went by Bill. But his legal name was William.
Okay. I'm looking up Miller. I don't know how good this thing is at.
Right.
We'll find out. And GCQ did not come up in 1983.
Oh.
There are a couple of GCQs, but
not his.
Nope. Well, let's see. There's only 23 Millers.
Oh, well, I'll sit here and if they come up big enough.
Can you zoom in on that? Hit Control Plus, Scott.
Yeah.
There we go.
Huh.
I want to zoom out a little bit.
Not Kevin.
Oh, now you're up to 85.
Oh, God,
those are all eights.
Oh yeah, it's a bad. You know what? I'll ask my brother.
Oh, wait, hold on. What's his middle initial?
William Leonard.
Oh, wait. There's one William L. Miller.
Oh, that's us. That's him.
WB, Overland Park, Kansas.
Oh, no.
Nope. Okay.
Miller is too common. I'll ask my brother again for his call sign and ask him to help me remember which years.
Okay.
So thank you so much. I mean, and then I'll try to. I can get the link and look for it for myself.
It's kind of fun to look. It's kind of fun to look into the history. I mean, we found out that my my daughter's call sign was actually held by. We live in Eugene. My daughter's call sign N7JI was specially allocated by the FCC upon request of her dad in 1937, and she was like 13 at the time. And we looked her up and we found her, and it turned out she lived in Portland and then moved to Eugene. And my daughter was a student at the University of Oregon. She lived a block from the University of Oregon, and at 96 was still alive.
Wow.
Oh, wow.
And we went and visited her.
Wow. Wow.
Can't you look up people's
Wow.
licenses on the FCC website? You
Only
just
if
need...
they've existed in the last 25 years.
Ah.
Basically, the ULS system started equivalently in about 2000 as a thing. If it's anything older than that, the FCC kind of just doesn't know about it anymore.
Well, if I can find it, I'm going to take his.
Oh yeah, for sure.
To be able to touch my dad like that would mean a lot
Yeah.
to my heart. He's a blessed memory.
I wonder if my call sign would be up there.
What was it?
KA6NSA.
Give me a year.
I got my license in 71.
Let's see. Was it ever a KN6 or anything? Or
No, KA6NSA.
Okay, so because before that they used to assign KNs for novice.
I was technician.
Oh, okay.
And then general.
Okay, so how long did you have it?
I got it in 71, and I'm 3 months overdue. I'm trying to get my license renewed.
Oh.
I thought I had to retake the test, but I guess not.
Well, no. Yeah, you shouldn't. I mean, here's QRZ.
Yeah, I just have to send my money in.
Yeah, if you're within the...
Yeah.
And it's KA6 NSA?
Uh-huh.
Yeah, I think if you're within the 2-year window, you can still renew.
Yep.
Yeah.
Yep, there you are.
Yep, that's me.
Oh,
Yep.
Oregon City.
Oregon City.
Yep.
And you're still in the window, so you just fill out the form and pay them your money, and you can't operate until it shows up as live, but you don't have to reapply.
It has to be on the website, correct?
Yeah, your license has to show up in the database. All right, I'm gonna turn